Welcome to APEC. It's June 8th, 2024, and I'm your moderator, Tim Ventura. I want to thank everybody for joining us on today's call, along with everybody who is watching us on YouTube. Russell Anderson is going to discuss Spintronics Generators. Shiva Meucci will discuss the Vortex Model of Spacetime. David Chester has a lengthy presentation on longitudinal electromagnetic and gravitational waves. And Daniel Davis has a quantum warp drive presentation for us. We're also going to be hearing updates from our lab partners and finishing off today's event with an open discussion by conference attendees. So I have some quick notes on what we were up to. It is busy, busy, busy this summer, and it's all good stuff. If you haven't seen it yet, all of the video and photos from my trip to visit Jared Yates and Isaiah Ritchie are now online. I have step-by-step test videos of Jared's Graviflyer replication, along with amazing high-speed test footage of Isaiah Ritchie's Searl effect generator. So that's all up on the Alt Propulsion channel, and I will drop links into chat as well. Really exciting stuff. Last week, Mark Sokol and I hit the Scientific Coalition for UAP Studies 2024 AAPC conference in Huntsville. So I just put up over 300 photos of that event online. Most of those are just the people and personalities and speakers who were there. And I had the opportunity to spend time with Ross Coulthart, Kevin Knuth, Matthew Sadagas, and our very own Gary Stephenson and Glenn Tony Robertson. So again, really exciting stuff. For me, it's really, there's a tremendous reward being able to capture the personalities that are involved with this innovation. And so that was the big takeaway for me. Next week, I am going to visit Drew and Charlie Bueller's lab down in Florida. I cannot express how excited I am about that. They made global headlines a couple of months ago for their work with reactionless thrusters. So it is so exciting to be able to go down there, and I'm going to try and capture as much as possible and, of course, put that online for you guys. Then after that, Mark Sokol and I are driving up to his lab in Hawthorne, New Jersey. And again, my hope there is to capture as much as possible about his dynamic nuclear polarization testing. And I should mention that in addition to his many, many lab updates, there have also been some documentaries. Wayne Ojala created a really lengthy 2-hour one that is on his channel. So there's a lot that's already there. We're just trying to kind of continue capturing info. So my goal is, again, more photos, more videos, as high res and as detailed as I possibly can. Mark also just got back from George Hathaway's lab in Canada. So we're all just super busy this summer, but it's all good stuff. I want to do a shout out to our theorists also. I am incredibly excited to be able to showcase Shiva Meucci's model for vortex dynamics today. This offers a ton of great ways to visualize deformations and energy flow in the fabric of space-time, and I think it is highly relevant to some of the experiments that we're working with. Dr. David Chester has been digging into a ton of theoretical work, including tremendous recent explorations into longitudinal waves. And I do not want to overlook or discount the work of Daniel Davis, who is going to be walking us through warp drive dynamics. All three of these gentlemen are presenting today. So just one more quick note before we get into it. We have upcoming APEC presentations on July 6th, August 3rd, August 31st, and September 28th. So we do have two of them in August. I guess that's just because it's like a 5-week month or something like that. And I have folks lined up to present at all of these. So if you have a presentation and you haven't reached out yet, if you have something that you want to share, we may be able to squeeze you in, but ping me now because we have a full house. And again, this is all wonderful. I want to thank and congratulate all of you for these remarkable achievements. APEC is your conference. It showcases your work, and our goal is to help inspire people with your vision. So APEC is about you. And it is a community. And right now, everyone in that community is pushing forward to make the dream a reality. So thank you. Thank you. I just genuinely cannot say that enough. Okay, so just the usual updates. Today's event uses StreamYard. We're broadcasting through the Alt Propulsion YouTube channel. If you haven't subscribed yet, please do so now. You can ask questions using the live chat feature on the right-hand side of the page. Those scroll up pretty fast, but we will try and get them as we go. Questions for the webinars, we squeeze those in if we have time. Again, these are 1-hour speaking slots. Dr. David Chester will probably go closer to 2 hours, and that is just because he has so much to share on longitudinal waves. This is all new research that he's done. So I'm just going to put that out there. You can also view conference replays, details, and speaker info on our website at altpropulsion.com. Okay, so that was a mouthful. Let me get started with our first speaker, the indomitable Mr. Russell Anderson. Russell, welcome, sir.
Hi, Tim. Good to see you. Good to see everybody.
Yeah, well, let me thank you for coming back in. So you went through and described a lot of Searl-based technology. I think it was last webinar, and we didn't go through all of your stuff. So right after you finished, I was like, wait a minute, there's a ton more. Russell, can you come back? So thank you for coming back to share that.
Yeah, sure thing. Yeah, glad to be here.
Well, let me do this. I am going to start with the Spintronics Generator STG, and this is, again, based on the Searl effect generator. Just say back or forward when you want me to change slides. I'll take myself out and take it away, sir.
Okay, yeah, thanks. Well, everybody can probably see the, I don't know if the picture's still up, the video's still up, the mock-up of the Spintronic Generator SEG right here to my side here. I don't know if you can see that, but maybe if I tilt up a little bit, you can sort of see it running. All you need is one plate, plate 0, the innermost plate, and one runner to demonstrate the effect. But anyway, we got a lot of work done 10 years ago in Florida, so let's take it away. Yeah, I have been working with Professor Searl since October 2007 when he invited me on the team. And basically, I learned the technology. Even before that, I was well aware of everything involved. Hold on a second. Let me turn off the demo unit. All right, because it's making a lot of noise. The actual unit itself, the nominal prototypes, will be silent because of the Hall effect. The runners will fly over the place instead of having any kind of direct contact. But anyway, let's go to the first slide. Or second slide. But anyway, what is a spintronic generator? Well, we have patented, Spintronics has patented the technology of Professor Searl. It's called the Spintronic Generator because Professor Searl copyrighted his name in 2014. So since this deals with the field of spintronics, we decided to call the company Spintronics, which we have since 2013, 2014. So anyway, it's this self-contained, frictionless, noiseless generator, or I should say converter of electricity, of ambient electrons and electrons from neodymium, from 15 kilowatts to upwards of 2 megawatts. And around 2 megawatts, we figure, was the output of Paul Brown's SEG. Paul Brown was a scientist who successfully built one and tested it. And it was so successful, it melted and blew up the wiring, which caught fire, burned the lab down, almost just about. And our late president, Phil Talbert Sr., was on hand for that. But anyway, it produces nominally about 100,000 volts. And whatever the output voltage, it's 1.5 milliamps current. And the more you draw from it, the more load you put on it, the more you can get from it. So it's perfectly in accord with Thomas Bearden's principles of anenergy or anti-energy, which is really ether energy. Ether is just little pieces of vacuum, submicroscopic pieces of vacuum, which house enormous quantities of hard electrons that we use in our culture to power our culture. Anyway, STG, spintronic generators, do not overheat. In fact, they run cold. And the more load you put on them, the colder they get and the faster they run. Because of the boson current going through it, Cooper pairs of electrons instead of single electrons bumping all over the place, creating heat. So they're totally safe to operate in any environment. They operate cold. They put out copious negative ions. So it's like a negative ion generator on steroids. Household, offices, factories, buildings, shopping centers, motor vehicles, more hospitals. Of course, they should have one in every burn unit. Professor Searl was in a lab explosion at his home lab and had to be taken to the hospital. After less than a day, he said, "Take me home. Can't stand this anymore." And while he was in the environment of the STG, running STG, which was powering his home, it was built into the wall. It put out so much negative ions that it healed his face up really quick with no scarring. Only a dermatologist could tell which side of his face was burned. And in fact, we have lots of research now showing that electricity applied to wounds makes wounds heal faster. So there's confirmation from all sides on this technology. And it's totally non-polluting, will not contribute to global warming. And the mechanical parts do not wear out because in the actual prototypes, there is no physical contact between the plates and the runners. And all you need is one plate, plate 0, and one runner to demonstrate the effect. And in the nominal unit, there are 3 plates and 3 runners, and 3 concentric sets of runners. And the inner plate, plate 0, must have at least 12 runners for a power generating apparatus. Next slide, please. Yeah, and these are photos of the work that we did in Florida, in Fort Lauderdale, actually Oakland Park, which was right next door to Fort Lauderdale, when we had access to a lab down there. STG consists of 3 large ring-type stators, generators about which or in which a rotor rotates, and it's basically a segmented rotor, which is what the rollers are, the runners are. They're specially magnetized with patterns designed, special magnetic pattern designed to generate continual motion of similarly magnetized cylindrical rotors. And it's not 2 waves, one wave on the plate and 1 wave on the runners, a sine wave on the plate and a cosine on the runner. It's actually 4 waves. And we'll get into that a little later. So you guys, you need to think in terms of 4 sine waves. The rotors are free to rotate around the stator rings with mutually interactive eddy currents of induction that form frictionless magnetic bearings. And the actual units, the prototypes, they'll be frictionless, no physical contact, like there is in this very simple mock-up right behind me, right to my side. Induction that form frictionless magnetic bearings between the moving parts. And in the process, electrons are paired, bosons, and accelerated outward and harnessed for their kinetic energy before they eject out to the ionized air, because there's a field of ionized air and reduced atmospheric pressure around the device. The higher the voltage, the stronger the vacuum around the device. An STG unit will convert random energy at the quantum level into a coherent flow of electron currents ideally suited for the world's demand for green energy, as is benign to the biosphere. It's as benign as a solar cell or a hydroelectric power plant. Next slide, please. Yeah, why a spintronic generator works. This is our Amy and Neo video. I don't know if that's going to work on this presentation. These videos tend not to work on StreamYard rather. Yep. Nah, it won't work. Anyway, this is from the patent. The patent pending. The patent has been issued by or published by the USPTA January 16th of 2018. Professor Searl died December 18th, or sorry, December 4th of 2018. So he has passed on, unfortunately. So we got a patent with our president on behalf of Professor Searl, Mr. Kirk Miller. And the present invention provides electrical power with motive force of natural electron spin. And the utilization of natural electron spin can be enhanced with carefully matched materials, weights, and magnetic waveforms, which provide precise pulsed frequencies in resonance with the materials. This resonance of the magnetic pulses coordinates the newly defined spintronics, MTJ and MEG. That's a motionless electrical generator to provide clean, abundant power. A utilization of zero-point energy results in a local environmental temperature drop. That's very important, which can be one of the sources of the motive force. And the date of the document was September 25th, 2014. And it took about a little less than 3.5 years to get that patent. And I was really, really happy about that. Next slide, please. Yeah, well, the secret mixture of the spintronic generator, it's no secret if you studied the work, and it's a lot of work, a lot of the papers available on Rex Research, rexresearch.com. Both the stator and the rotor are made with the smallest size particles. It's like minus 425 mesh or 450 mesh, 435 mesh, something like that. And of an elemental recipe, basically like you're baking a cake, developed by inventor Paul Brown, which was the STG mixture for the flying device, for the levity disc, the IGV, inverse gravity vehicle mix, 6 elements instead of 4. You need basically at least 4 elements for power production. But the 6-element mixture is what was analyzed by Professor Paul Brown and reproduced successfully. Aluminum, iron, sulfur, neodymium, titanium, and a binder. You need a thermoplastic binder like nylon 6,6, it's nylon with a negative charge, or Teflon, which is also highly negative on the triboelectric series. And the particle and shape size are extremely important for electron transfer, and therefore you need a quality powder grinder, or if money is not an issue, you can get them pre-ground from the suppliers. And ideally 325 mesh, 44 micron or smaller, and jagged particles, not rounded, but jagged particles. So it's very, very, very small particles make everything happen. And basically that increases the surface area for reactions to occur if you have the small particles. Next slide, please. Yeah, so we will need, when we get funded, we're still trying to get funding. So here's a call. This is a call to all you people out there who are qualified investors. We need funding to make this happen. And so if you're looking for a return on your investment, obviously the Searl effect generator is your baby. Anyway, high quality microscope is needed to examine the particle size and shape. And the particles will be mixed, pressed, metal plated to preclude oxidation. That's important. And magnetized and assembled here. And then they'll be sintered. And then basically sintering just makes everything more durable. Next slide, please. Yeah, this is what the molds look like. And then the magnets, once they're pressed and then coated, need about a 400-ton guided press. That makes sure we get about 7 grams per cubic centimeter of density. That's what we need. And those are the pressing dies right there on the right-hand side. Next slide, please. Yeah, I went to a facility in Pennsylvania that also isostatic hot presses things like magnets that you want to, or anything that you want to press. It increases the density and ohmic contact between the elements, and also holding pressure and heat for 20 minutes that makes the parts more stable and more durable. Next slide, please. Yeah, metal plating, you want to plate everything with nickel or some other type of plating that will not oxidize. Next slide, please. Yeah, and those are what, from the patent, what the waveforms basically are going to look like. You have a sine wave on the plate and a cosine on the runner, but it's even more complex than that. You have 2 other waves, so you have 4 total waves. So you have to magnetize the stators and rollers in a unique wave pattern as part of the key to the spintronic generator. Next slide, please. Yeah, and then you have surrounding the spintronic generator, pickup coils, which are C-shaped and wound, depending on your winding, for AC power production or DC power production. And then you have 12 pickup coils. And all you need is one plate, plate 0, and plate runner for a nominal, one runner for a nominal Searl effect gyrocell or spintronic generator gyrocell. And the combination of a ferromagnet at ferromagnetic resonance in ohmic contact with the conductor is basically a spin battery, which produces power. Each one of these, if we go back to my video, to me for a second, each one of these magnets is basically a battery. It's basically a spin battery. You could put probes on the inner part and probes on the periphery, and you will get a deflection on your battery meter anywhere from 5 to 12 volts, DC, of course. And spinning enhances that effect. And all you need is 6 volts to get everything running. This mock-up runs on 6 volts. Next slide, please. 6 volts at 500 milliamps. And there's what the waveform looks like on a scope in the lab. Next slide, please. And we want to recognize and thank Nikola Tesla, inventor of modern alternating current, electricity and supply systems, and a whole lot more. AC motor, radio, radar, radio control, scalar technologies, scalar electromagnetics, like Tom Bearden mentions. Space is filled with isotropic kinetic energy. There is therefore no such thing as an empty vacuum. Highly recommend everyone read The Secret of the Creative Vacuum by Dan Davidson. The electromagnetic sea is in the ether. And that's Paul Brown, who also reproduced the SEG successfully, Spintronic Generator, SEG. And of course, our late mentor and friend, John Roy Robert Searl, inventor of the Searl effect generator. And I think that's it for this slide group. Now, if we could go to the next slide group. Yeah, anti-gravity devices. Yeah, the great thing about, which was totally unforeseen about the Searl effect generator is that it is an anti-gravity drive when it's overloaded and superconducting. And the more load you put on it, the colder it gets. And about 4 Kelvin, and develops a vacuum. 4 Kelvin, that's about 256 degrees below zero, the materials making up the SEG start superconducting, and the Earth's field repels it with great force. It develops no inertia, and the Earth's field pushes it away with great effect. Now, anti-gravity devices, they developed the Searl effect, the levity disk, because the thing wouldn't stay on the ground and they had no control. So the whole idea of the levity disk is a control flight frame so you don't lose it and you have something to experiment with. So anti-gravity devices, German past. The next slide, please. Yeah, I've been at the Nikola Tesla Club in Philadelphia demonstrating the B-Field-Brown effect with 4-foot flying devices, U.S. public schools, global breakthrough energy conferences, and out on a farm with a couple of 2-foot B-Field-Brown effect flying saucers, which I demonstrated in Reno, Nevada in the year 2000. Can't believe that's almost a quarter century ago, but yeah, there I am on a farm in Chester Springs, Pennsylvania. This technology is very much at home in a rural setting, in a farm setting, because there's no noise, there's no pollution. It is totally green energy. Next slide, please. Yeah, that is a beam ship, what the extraterrestrials themselves call a ray ship or a beam ship, anti-gravity device, electromagnetic propulsion, which is basically a very similar technology to the Searl effect. In one configuration, they have 2 inner tubes of ferrofluids that are pumped by basically Tesla turbines going in opposite directions, and that develops a very, very, very high voltage for electrogravitic flight. In another configuration, they have 12 lasers, at least 12 lasers that are either pointed inward or outward in a circle like wagon wheel spokes. And they're very powerful lasers. And that produces a bending of space and an anti-gravity effect as well. And all these photos and films have been checked by the computer, and no trickery was ever found. Next slide, please. Yeah, and there's the 7-meter craft. They're 7-meter going around a weather pine, and it's so close to the weather pine that it's spreading the branches, For a time after this demonstration, the top of the tree glowed in the dark. So obviously it picked up some kind of dangerous ionizing radiation. And I guess the tree eventually died. But anyway, that is a fully grown tree. That's not a bonsai tree. And Edward Meyer, has only one arm. He doesn't know how to build models. He operates his camera with just one hand, rides a moped to each of these contacts. He gets a contact as he gets a telepathic signal, which is like a cooling sensation on his forehead. And the whole idea for him to take pictures was, number one, for proof that he was having contact with extraterrestrials, and number two, to open up debate about the possibility of extraterrestrial life, that the Earth is basically not the center of the universe. Next slide, please. Yeah, there's another further out photo of a beam ship, 7-meter diameter beam ship, basically exhibiting the Biefeld-Brown effect, which Thomas Townsend Brown discovered back in 1923, 101 years ago. Next slide, please. Going around that tree, it's a very highly polished surface of the disk, 7 meters in diameter. Very comfortable. Gets from here to the Pleiades, or from the Pleiades constellation, and it's actually in another dimension. It's another star system that we can't see in this dimension. It's basically shifted a fraction of a second into the future. So we have to invoke interdimensional travel and very high energies when we're talking about these type of craft. And flight voltage for the Searl effect generator is something like 10 to the 12 or 10 to the 13 volts, and the current never exceeds 1.5 milliamps. High energy electrostatics is the same thing as a gravitational field. Next slide, please. Yeah, this is real. These things are real. And the main reason that these craft and extraterrestrial contact was covered up in the first place is because these craft do not use fossil fuels. They don't use nuclear power. They don't use centralized energy. They use free energy that's all around us. You don't really see free energy advertised on the local news for obvious reasons. People stand to lose fortunes. Those are controllers who have their thumb on top of us, basically. They want to hold on to their fortunes, and they want to squelch any talk of free energy and free energy devices and systems, a la John Searl, Otis T. Carr, Nikola Tesla, and many others. Next slide, please. Yep. From a distance, there's your proof. Next slide, please. Going around that tree, actually spreading the branches of the tree so you can see that it is not a model and not a composite, not a fake. Next slide, please. Yep. Going around that tree, totally silent, completely silent drive system, like the SEG, the Spintronic Generator, completely silent drive, extreme high voltage, same thing as a gravitational field. High energy electrostatics is the same thing as a gravitational field. Next slide, please. Yep, going around that tree, just flying around it, hovering around it, hover around. Next slide, please. Now that is a 7-meter craft also, but was an experimental craft from 1981 that was given to the Pleiadians, from a group of humans that are in another universe, a parallel universe to ours, a universe that borders on ours, called the DAL universe, the DAL universe. Our universe is called the DERN universe, the DERN universe. And basically, This was an experimental ship. Notice that those spheres are at different layers, basically giving this vehicle the name of the wedding cake ship. And it bears some resemblance to the Adamski craft also. 7 meters in diameter. This craft was taken out of service at a comparatively short time because Earth's atmosphere started to corrode and oxidize the surfaces. And you can see that those spheres are very much like Wardenclyffe Tower as envisioned by Nikola Tesla. Those spheres basically increase the surface area of the device. And the greater the surface area, the greater the effect when you're talking about the B-field bound effect for electrogravitation. Next slide, please. Yep, and there's Wardenclyffe Tower with those aforementioned spheres to increase the surface area of the electrode, the main electrode, which propagates the electrical energy. And you have some anti-gravity craft flying around, some cigar-shaped craft. Nikola Tesla came up with the idea of the anti-gravity craft in terms of cigar-shaped craft that was powered solely by electricity. Next slide, please. Yep, and there it is from a different angle. The wedding cake ship from 1981. There's also video. You can go to YouTube and see video of that. You see Billy Meyer walking out in front, and the ship way back about 100 yards in the distance around a pine tree. And it has, unlike the Plejaren beam ships, this one has a rock steady hover. Next slide, please. Yep, and that's over Bachtel Hornli in Switzerland, another configuration craft. I think they said the modifications to the cupola or dome on top are for interdimensional travel and also time travel, which is the same thing as interdimensional travel. Next slide, please. You should see the films of these that were taken on Super 8 and video are just stunning. And no form of trickery was ever found. They were checked by computer back in 1979, 1980, and just a few years ago, no trickery was ever found. Next slide, please. Oh, by the way, that the bottom craft is a drone craft that was radio controlled from the top craft, which is 7 meters. The drone craft is about 5 meters. And notice the 3 spheres on the bottom of the drone craft. Those are basically spherical capacitors, single plate capacitors for electrogravitic control. Next slide, please. And these are the various classes and configurations of extraterrestrial ships that were noted by the witnesses, and more than one witness in this case. And this is a contactee case, basically, from an ongoing case, like a few of them others. Another one was from Dr. Fred Bell, also had contact with these extraterrestrials, and they gave him pyroponics technology, which he then distributed and sold. Yeah. Next slide, please. Yeah, there's Thomas Townsend Brown on the right-hand side with one of his famous flying saucers that he flew around the Maypole. And of course, I built them starting back in this January, end of January of 1990, and they worked fantastically well, better than what was even claimed in the patent. And on the bottom is a theoretical model of a Searl effect generator, which is in layers. The actual first generators that also that flew were homogeneous mixtures, not layered mixture. The layered mixture is a theoretical experimental design that Professor Searl said should work better than the original homogeneous mixtures. Next slide, please. Yeah, and we see some various anti-gravity devices. Victor Schauberger's device, which is called the Repulsine. Otis T. Carr's device. Mark Tamian's device, which Mark said he got the idea from Professor Searl's Searl effect generator. And he got a patent for that too. The Ducrochet disc, which is a mica disc, which is mobile on a point. And you have 2 output spheres from a high voltage generator, such as a Wimshurst generator. As soon as the generator is active, the disc, which is on the right-hand side, starts a very rapid rotation and then just flies off. There's a major secret to anti-gravity propulsion. Also look at the French patent by Marcel Page, Pages, and Searl effect generator at the bottom. And in the middle bottom is a theoretical warp drive craft that NASA has come up with. And they've gotten a lot of breakthroughs. They now have an electrogravitic system that gives 1 G of acceleration. So that is huge breakthrough now going on down here in Florida at NASA. Next slide, please. Yeah, gravity is just a push of space fabric, a push of space fabric to the center of the Earth along the plumb line, which is the local vertical. And you have the traditional wireframe model, which is 3 dimensions, and a 2-dimensional model on the right-hand side. Yeah, gravitational attraction is caused by a perturbation of space, which is caused by a converging flux of ether or space fabric. Next slide, please. Yeah, you have an equilateral triangle, electricity, magnetism, and gravitation, 3 fundamental forces. Of course, that leaves out electro-weak and electro-strong gravitation and force. But on one side, you have electrogravitation. The other side, you have electromagnetism. And the other side, you have magnetogravitation. Next slide, please. Now, you have groundbreaking research since 1923, the anti-gravity research of Thomas Townsend Brown, which I've done a little work on, and it works extremely well. Next slide, please. Yeah, this is Thomas Townsend Brown, I believe, in Los Angeles, California. Notice his discs, which were basically the same thing that we built back in the 1990s. You have a disc, a flying saucer, made smooth, as round, as smooth as possible to preclude arcing. If you get arcing or sparking from a sharp point, the device basically shorts out and the field collapses. And if you have a flying device, and this has happened, where the conductors touch, or you get a spark between the conductors, and at that point the field collapses and the device drops like a stone. Notice you have those plexiglass insulators and a thick piano wire with balls on the ends to preclude arcing. And those whip around at very fast speeds around the maypole. And I built that custom tower and rotor apparatus, and it works even better than what is claimed in the patent. It's patent number 2949550 from August 16th, 1960, the electrokinetic apparatus by Thomas Townsend Brown. That's basically a warp drive because there's no inertia. Since there's no inertia, the speed of light should not be a barrier any more than the speed of sound was a barrier to Chuck Yeager's Bell X-1 rocket plane back in 1947. Very, very important year, 1947. Next slide, please. Yeah, that book used to be available through let's see, the TeslaTech.info Research Center bookstore. And I will be speaking at Tesla Tech this August. Go to teslatech.info, and I will be speaking there on disclosure and what they're not telling us. What they're not telling us. They're not telling us about this technology. You hear all about disclosure in the news media, but they're not telling us that these devices are more efficient than any devices, any form of propulsion known, which obviates the need for internal combustion. But they're not telling us that they're free energy. In these electrokinetic apparatus, there's more propulsional force being generated than was traditionally going in terms of electrical power, in terms of watts. So it is breaking the conservation of energy law, clearly breaking it, and Newton's first and third laws of motion. It's breaking those laws. Next slide, please. Yeah, so what you have in front of the disk is a positive pole. The disk is negative, so Coulomb's electrostatic attraction makes the disk fly toward the positive pole. So there's a G-well. What we know from quantum electrodynamics is that positive charges are attractive on matter. Negative charges are repulsive on matter. So what is generated by the high voltage is a polarization of the vacuum, polarization of the ether, and a wave effect is created. This is a two-dimensional depiction of the wave, but it's a three-dimensional wave that alternately pushes and pulls the device without any freight cars effect of transmitting the force from a point on the device and the force gets transmitted atom by atom by atom. No, it doesn't work like that. Instead, the entire device and anything inside it moves in response to the applied external force field, the electrostatic field. So the device is a wave rider, riding that wave of electrically modified space-time into infinity as long as the charge is maintained. And the higher the voltage, the stronger is that force. And the force can just be incredible. Next slide, please. And that's what the rubber sheet model looks like of the electrically modified space-time. It's basically the Alcubierre warp drive metric. And it permits the existence of faster than light travel within the framework of general relativity because the craft is traveling inside a bubble of normal space. Space is only modified, basically contracted in front of the ship and expanded behind it, simply due to the high electrostatic voltages. You need maybe some tens of microamps. The rest is all high energy electrostatic potential, high voltage. That's all you need. Next slide, please. It's warp drive, yep. And there is the depiction from the patent, and then the devices going around the maypole, and a generator set up with Thomas Townsend Brown, T.T. Brown, in the middle, somewhere in Los Angeles, California. Next slide, please. So early 1950s. Yep, there it is. And we built that. I built the tower and rotor apparatus back in the 1990s, and it works fantastically well. And you can see the videos of that on YouTube if you go to T.T. Brown Electrokinetic Apparatus. And there I am demonstrating it, supporting a lecture. Next slide, please. And there's what I built, the high energy electrostatic apparatus of T.T. Brown. And this is warp drive. No fuel, no moving parts, no noise. This is where we ought to be right now, but this technology has been held away from us. A colleague, Larry Davenport, who I met a few years ago, I guess at Tesla Tech in Albuquerque, where I'll be lecturing this August, teslatech.info. He said he learned about this in school in the early 1950s when he was a kid. And by 1956, it had seemingly disappeared and was no longer taught in schools anymore, which is extremely weird. Well, we all know what happened. Can you guys say cover up? I thought you could. Next slide, please. And that's supposed to be a video of it, but I can't figure out how to get videos running on StreamYard. And there's the video of the vertical lift device I call the beam ship because it's utilizing basically the same technology for anti-gravity propulsion. Very efficient, silent drives running where I used to live up in Pennsylvania. And that video will not work either, I don't think. I can't get videos to run on StreamYard. I think it's a bandwidth problem. Next slide, please. Yeah, that's on top is a photo of me and my colleague Dave R. in Reno, Nevada, at the Reno Library back in June of 2000. So this was almost exactly 24 years ago. Amazing how time flies. And then on the bottom is someone's replication from YouTube with smaller devices. And those devices that we built, first I built 2-foot devices around 1990. By 1999, I built 3-foot and then 1-meter devices. Those are 1-meter flying saucers. And the force field comes off of that, ionizes everything within 100 feet, and it seems to be a constantly expanding flux of ionization. Next slide, please. Yep, there it is. Just a parallel plate capacitor with a conductor in front that's given a positive charge from the high voltage generator. And you're going to have that high voltage generator on board the craft, of course, and the negative or chassis ground going to the saucer itself. Next slide, please. And there's an article from the Los Angeles Times, Flying Saucers Explained by Men of News Research University here. And that was the New School for Social Research. And Dr. Mason Rose did a paper on that. You can look that up on Google. And yeah, a lot of prominent people in Hollywood area came to see those saucers. And right after that, we got a whole wave of flying saucer movies, basically, which depicted the technology very correctly. Next slide, please. Yeah, this is electrogravitic propulsion, same as Professor Searl's electrogravitic propulsion methodologies, electrogravitics for lift and attitude control and steering. Next slide, please. There's electrostatic flying motors. And another 4-foot diameter prototype that I built in '02 using inefficient copper wire. I've since switched because of Tim Ventura's suggestion right after that to stainless steel wire and got less noise and even better results with lower voltages. I was only using about maybe 40,000 volts there, current limited to 1.5 milliamps. Next slide, please. And that's a 6-foot diameter beam shift variation 3. That's 6 feet in diameter. It's unbelievable. It's just really cool to see. And you can see the YouTube videos of that too. Really cool to see something that huge flying and floating with no noise whatsoever. No visible means of propulsion. Very cool. Next slide, please. And there's a 5-footer in a laboratory down here in Florida, in Altamont Springs, Florida. And that was 4 years ago. Next slide, please. And there it is up in the air doing its anti-gravity thing with no noise, no fuel, no moving parts, no emissions, just what the world needs. Next slide, please. And the basic calculation equation for calculating your electrogravitic force, your force is going to be in newtons or dynes, V m1 m2 over r squared. V is obviously the voltage, m1 is the first electrode, m2 is the second electrode, and r squared is the area of the device. Next slide, please. And there's Coulomb's law of electrostatic attraction, very important for this form of propulsion. F is the electrostatic force between the charges in newtons. Q is the magnitude of the first charge in coulombs. That's Q1 rather. Q2 is the magnitude of the second charge, opposite polarity. R is the shortest distance between the charges in M, in meters. And KE is the Coulomb's constant. Next slide, please. And there's a theoretical explanation and elucidation of the Adamski flying craft, which is a very popular UFO seen in the from the early 1950s to the mid to late 1960s. Next slide, please. And that was from Agnew H. Banson Labs. And this is another similar flying saucer, which was patented by James Frank King and a couple other people at Agnew H. Banson Labs in the late 1950s in Winston-Salem, North Carolina. They did a lot of really important vacuum chamber work there too, proving that you don't need any air. In fact, it works better in a vacuum, which is also confirmed by work in a vacuum chamber in Paris, France in 1955. Next slide, please. Yeah, you have a vacuum around the device because of the high voltages. No air can come near it at that voltage. At that voltage, also, no matter can come near. It's from the rim, especially micrometeoroids, cosmic rays. You can go at any speed you want, many times faster than the speed of light, and not have to worry about the ship being destroyed by something that it might encounter in the universe. Positive on top and negative below, and double plate, or you can have single plated capacitors for additional propulsion and attitude control. And running through the center of the device is basically a transformer coil to help generate the high voltages. Next slide, please. Yeah, they found out that very low voltages, the craft can lift more than its own weight. Next slide. Yeah, positive on top and negative below. And the Earth's surface is negative at its surface and very strong positive charge at the core of the Earth. Earth's gravity field is basically electrodynamic. Next slide, please. Now, this is very important. They did experiments with double-sided electrodes, positive electrodes on either side of the saucer. Of course, the saucer is basically has a negative charge going to the center. They could reverse polarity instantaneously, and the device would instantaneously switch direction with no speed up or slow down, proving that inertia has been isolated totally by the electrostatic force field. And Professor Dr. Gabriel Lippmann discovered, I forget exactly when, in the 1940s or 50s, that inertia is solely dependent upon net charge, not mass or concentration of a local material. And he called it the inertia of static electricity. Basically, bodies that are very highly charged, negatively charged, have less inertia. Bodies that are positively charged have more inertia. Very important. Next slide, please. B-2 bomber could be thought of as a flying capacitor as well. People have reported it just, standing still in the air, rotating on its axis, and going in another direction. This is very important because it shows that the government knows about and has utilized T.T. Brown's electrokinetic apparatus for electrogravitic flight. Next slide, please. And there's basically a more advanced, larger version of the B-2 for electrogravitic flight called the Telos. The Telos. So basically a black boomerang, which has been seen all over the world. Phoenix, Arizona, 1997, sorry. And Westchester County, New York, 1983, 84. Very important. Next slide, please. And there's a device that I was working on, still want to get working on again. That is the Graviflyer from Alexei Chekhov. That is also a heavy lift device. Could not get it working. But people are still working on it all over the world, and Alexei is still selling kits to scientists all over the world. 2 or 3 weeks ago, I was at a NASA scientist's house. I was on my way to Palm Bay, and he was in East Orlando, Eastern Orange County, and I assembled a device that he had just gotten from Alexei, and he needs a voltage converter. So the device runs on European current, which is 250 volts, 230, 250 at 50 hertz instead of our 110 to 120 at 60 hertz. Next slide, please. And there it is. No one has been able to duplicate it thus far. Those are just computer fan motors. You have to have everything in resonance. And you have an ultrasonic generator at the top with a parallel plate transducer, fan motors, a center plate, which is just a thin piece of aluminum. Well, that gets a charge from a Tesla coil with one wire. And you have 2 counter-rotating spinning capacitor plates, circular magnets on the bottom plate. And he has many videos of that flying indoors and out. Next slide, please. Yep, there it is, flying, hovering flight, heavy lift, anti-gravity, resonance-based, but a lot of the same effects and same type of apparatus you see in Searl devices and Biefeld-Brown devices. Next slide, please. And there's a device by Viktor Grebennikov, which is a flying platform. Inside, strategically arranged, are beetle wing covers, not wings, but the covers. The covers have all these pits and pores, which are cavity structures. Cavity structures seem to exhibit a repulsing force, which is primarily electrostatic force. Next slide, please. And there it is. It's just a simple painter's case. And there's basically no power going into that. It's self-powered. Next slide, please. Nature's anti-gravity. Yeah, There's the beetle wing covers, positive on top. There are all these pores on the inner surface. There's chitin on the outside, which is a very high K factor dielectric. And then the hairs, all those little hairs on the insect's body are negatively charged. So you get an electrogravitic flight. This is how bumblebees seem to fly in defiance of aerodynamics and other insects. Also spiders, certain species of spiders fly electrogravitically. Next slide, please. Highly recommend everyone get this book. I got it at Barnes & Noble's some years ago. I guess 2008, 2009, something like that. Secrets of Anti-Gravity Propulsion by our late friend, Dr. Paul A. Laviolette, which I saw him lecture in 1990 in Colorado Springs at Tesla Tech in Colorado Springs, and he totally rocked my world. Amazing. It was a huge loss to science, and he really had some great reference material. Highly recommend everybody run out and buy this book right away. And chapter 10 is all the Searl effect generator or spintronic generator. It's completely on chapter 10 devoted to Professor Searl's technology. Next slide, please. Also, electric gravity. Next slide. As Otis T. Carr's Eutron-powered craft, that's also an electrogravitic craft. Our late friend, who I breakfasted with every morning 12 years ago in Hilversum, Holland, at the Global Breakthrough Energy Conference #1, which you can see on YouTube. He rode on a manned version of this, basically much faster than the speed of light, almost like a kind of teleportation. And this craft is also thought controlled. It's controlled by intention. So your intentions have to be pure. Your aim has to be true to fly this thing or even build them. Next slide, please. And there's Otis T. Carr with a model of the Eutron. Inside the central Eutron, which is that center cone, that's cones at both ends, is mercury, liquid mercury. Next slide, please. Yeah, anti-gravity and warp drive based on the work and teachings of Nikola Tesla is the Eutron. Next slide, please. And there it is. That's a plan from, or a line drawing from the patent. Yeah, you have basically single-sided capacitor plates, and then neutrons on the periphery that are passing through electromagnets. So it's a very high-powered electrostatic generator. It's an electrocraft, basically. Next slide, please. You can download all these photos online and start building. This is our future that was denied us. Back in 1960 or 61, a year I was born in 61, a whole bunch of armed men in flak jackets came to Otis T. Carr's lab, held everybody at gunpoint and said, "We have to shut you down because your work is threatening the monetary system and our economy. So bye-bye." That's the kind of society we live in still to this day, although things may be loosening up a little bit in terms of disclosure. I hope so, because we should be going to the stars right now. In fact, the breakaway civilization has already been going to the stars since the 1940s in Germany. Next slide, please. Yep. There's I believe that's a 2-meter diameter model, flying radio-controlled model. And underneath it is a smaller demo model, 6-foot prototype, the OTC X-1 electrogravitic spacecraft, but never did because the inventor was driven to illness and repeated harassment by the government. They didn't want anyone to have this technology. Next slide. Oh, are we out of time?
Yeah, we're out of time. Actually, Russell, I want to thank you so much. This is amazing history. And so the folks watching can't see this. You've got, let me see, this goes to 200 slides. So what we might be able to do is,
yeah, we'll have to pick it up later. I know we started a little after 3, but we'll have to pick it up later.
Yeah, no, Russell, let me thank you so much. In fact, I want to bring everybody in and give you a hand. This is absolutely tremendous. I was putting in the private chat, I love the fact that you were documenting the history of this. It is so important to preserve that, So let me bring, oops, I'm going to bring everybody in here. I got too many folks going on. There we go. Okay, so everybody, please put your hands together for Mr. Russell Anderson. And Russell, let me apologize for not, I just didn't realize how much you had in those presentations. The Spintronics one was amazing. And thank you for running through just this history of photos of all of this stuff. It's absolutely tremendous.
Yeah, now I've got the mock-up running again behind me. You can see it. That basically demonstrates, gives you an idea, plants an idea in your brain and in your soul of what this technology is supposed to look like when
Well,
it's operational.
and again, I've already got tickets to visit Drew, and so when I'm down there, I will email you in just a moment. We'll try and coordinate. I
Yeah,
would
we'll
love
get
to get.
together, coordinate, and have a powwow. That sounds great.
Awesome. Okay. Well, Russell, thank you one more time, sir. And again, we're on a tight schedule, so I'm going to go right to Shiva. Thank you again.
All right, I've got two of my slide deck. I've got my slide deck shared in two different ways because I wasn't sure which ones would work and which ones wouldn't there.
Oh
So,
yeah. And then you can thumb through those also, right? So I will
right, exactly.
completely stay out of your way.
Yeah,
Shiva,
so
I genuinely cannot thank you enough for presenting the vortex fluid model. I mean, it's super important for visualization, but also just from what I've studied, like every time you discuss that, it just for me it clicks. I'm like, yes. And it's one of those things that gets stuck in your brain. I think it takes a while to kind of sink in, and once it does, it's just this incredible visualization tool.
yeah, I have to go over it a number of times with people generally because there is so much to it. But it is something that I've been calling the neoclassical revolution or the neoclassical interpretation for some time now, and I've given my published papers. I think you're going to have to actually put it on the screen for me to be able to manipulate it. So
Okay, there we go. And I will take myself out and go for it, sir.
actually, let's try the other one. I just want to see if it actually shows the animation. Okay, it does not show the animation. That's why I brought the other one. All right, that's good. Let's go back to the other one.
Okay. So I'll go back to the other one then.
Yeah.
Yeah, StreamYard has a lot of advantages. It does have a couple of quirks. It makes you do videos and animations and stuff separately, unfortunately. But to be honest, the benefits of it kind of outweigh the minor drawbacks that it does
It
have.
really does. Yeah, it's a great tool.
Okay, well, thank you again, sir, and take it away.
All right, thank you very much. All right, so I'm going to try to run through my slides as quickly as possible because this is sort of an overview, and I plan to do more deep dives in the future. But this is basically to introduce a set of concepts and show you that there is basically this single through line for revolution within modern constraints. And so, for some time, people have known about the issues with the vacuum energy catastrophe, all of the various issues that we're having in physics. There's quite a lot of them. As much as we would like to downplay them, they are very, very big. Matter of fact, one of the ones I like to point out is with the cosmological constant problem is it is equivalent to expecting a measurement the size of all atoms in the universe and measuring one atom. That's the difference between our expectation and measurement when we're talking about that particular problem, and there's quite a few others. So let me move over to my slides here and move to the next one. Okay, so one of the things I first want to point out, as a historian, I am not trying to put myself as the origin of the neoclassical revolution. It's been around for a very long time underneath the surface since, for over 100 years, but I'm going to try to bring you to some of the history so you understand where I'm coming from, and so you can kind of dive into it yourself, and hopefully, after you've allowed some of this presentation to bake a little bit, you'll be able to go back and look at, and when we deep dive again, you'll have some ability to look at some yourself. So I want to bring up some of the most recent names in what I call the neoclassical interpretation or the neoclassical revolution. Ross Anderson, I wanted to bring him up first because he recently passed away, and he's one of the people that introduced me to a more modernized version of soliton models in fluids. He worked with Robert Brady. He consulted with Steve Moffat, I think, is the other physicist there at Cambridge. But he was a security engineer at, or the head of security engineering, and so he was a software engineer, etc. Much more than that, of course. And he wrote a paper that you can find in the archive called Maxwell's Fluid Model of Magnetism, as well as a few others. Unfortunately, for some reason, these papers that were very, very powerful are not found on his Wikipedia. Then I wanted to introduce you to Yves Coudet. He's responsible for one of the most one of the biggest recent developments in what I call the neoclassical revolution. And he invented the silicone oil drop experiments. And we're going to talk a little bit more about them later. Then John Bush, he took these experiments, which were being performed by a number of people in the community. He's in the fluid dynamics department at MIT, and he has now published something called Pilot Wave Hydrodynamics. And then the other person I tend to think of, and this is just a very small subset of the people working behind the scenes for a very long period of time, and these are the recent ones, and that is David Delphinnick. I hope I'm pronouncing his name properly, but I just want to point him out because he's owned neo-classical-physics.info for quite some time before I actually decided to coin this interpretation by that exact same name, and ended up finding that he is the original translator of the Kosrat paper. And that's the Kosrat sort of book in 1909, and that it now has led to what's called micropolar elasticity, and that is a big part of the picture that I'm going to introduce you to, but we'll get to that in a moment. So what is the neoclassical revolution? It is revolution via interpretation. In other words, so the biggest question that you have to ask yourself is, how can we have a revolution when we have these measurements that are so perfect? We have so many experiments. How is it possible to have a revolution? How is it that we can have such perfect, such, absolute, finite calculations that are working perfectly, and then also having these ones that are so incredibly out of whack? And that is why I'm saying that we can do this via a change in interpretation. And now, a lot of people are going to have a problem with the idea of trying to make a change in interpretation. And so what I want to point out is the map is not the territory. And what I mean by this is that whenever you're doing mathematics, what you're doing is an analogy. You are representing something. You are cutting it down, and being able to match the map to the territory is what makes real metaphysics. And it's that is the intellect type that lies beyond calculators and stochastic parrots. The ability to map those things, to figure out what math should be used, not just simply calculating, not simply memorizing and regurgitating. So that's very important. And I wanted to point out a couple of things to basically get us back on the track of the value of real metaphysics. And that is, how do you map this analogy of a mathematics and what it is that you're modeling, and not losing yourself in the mathematics as just some sort of pure pursuit, but a real actual pursuit of modeling. So what is the value of theory? And so I want to talk about what I could call the pragmatic validity limit. And a story I often tell is that there is a tribe in Papua New Guinea who prays and sings to the fishing tree, and in response, fish rise to the surface. This is basically an empirical science, because you can go watch them do the ceremony, and fish will indeed rise to the surface almost every time. And so the thing about that is that it is a neurotoxin that is in the root that they beat as part of the ceremony that goes into it. Now, the thing about this is, so what they have is an experimental science within the limits of their knowledge, and it is functional and actually is, has its own type of validity that is very important. Not only does it have validity, it has extensibility. In other words, you can take your theory and extend it. It's also a very important part of being able to use a theory. So their theory of the fishing tree, the way in which it's extensible is the fact that neurotoxins, insects are very susceptible to neurotoxins. And since it is a neurotoxin, they could then believe that it is, somehow bringing them food. They could burn the root, and that would very likely poison bees and things like that, and they could gather honey better. But the problem is that they will then hit a wall at a certain point in their extension of theory. So the point here is that some theories are greater than other theories. They match more of reality. They are more extensible than other theories. And so, but there are theories that function within their limits. So, for instance, what I'm saying here is that the same thing is true of our current theories. They are very, very valid within the limits that they currently have on them. So, what else is it that theory does for us? What it does is it allows us the difference between acting like evolution, in which you're by trial and error, you eventually come to a some sort of conclusion by just slamming things together. A lot of mathematical physics, actually, which in the Kuhn cycle was called the normal science. That actually is that banging things together till something sticks. But then there is, instead of that, there is projection into white space. There is the ability to know that these things go together in a certain way, and so you can actually have a limit on your infinite search. You don't just bang anything together in any way at all whatsoever. You test within borderlines defined by that projection of your theory. So the theory is extremely, extremely important in actual real innovation. In other words, that is the difference between understanding and what evolution does, which it does develop extremely complex systems via trial and error. And instead, by limiting the search space, theory brings us much faster to an answer that gives us innovation and engineerability. So I wanted to go through a couple of quotes here. History shows clearly that the advances of science have always been frustrated by the tyrannical influences of certain preconceived notions, which were turned into unassailable dogmas. For that reason alone, every serious scientist should periodically make a profound reexamination of his basic principles. That is Louis de Broglie. And he is, of course, a father of quantum physics. And then the longer quote, I'm just going to say, science advances one funeral at a time, Max Planck. And you kind of can get the point here that a lot of scientists, going right up to Kuhn's structure of scientific revolutions, understood that there is an issue with the fact that you cannot stand on the shoulders of giants without having some level of faith in the evidence and the interpretation of the evidence and that the people before you have done their job. It's the only way you can specialize and spend a lot of time moving forward is by having some level of faith, and that faith is hidden from you. And that is why dogma appears in science and why there is a semi-religious sort of behavior, because it is a requirement that you not go and re-examine absolutely every prior axiom, otherwise you will not progress. So that is part of the reason why we have these revolutions being necessary. So I want to go into a little bit of the highlights of the timeline for ether that are relevant to this discussion, because it is important to note that there is not just any ether that you can use. You can't just hand wave. There is only a particular, very specific development of ether that leads to all of the other aspects of science. There's a very narrow path, extremely narrow path that can fit our current experimental regime and our current physics. So in 1818, Augustin Jean Fresnel, I'm butchering his name, of course, publishes a memoir on the diffraction of light and establishes the coefficient of ether drag. So in this, he actually is proposing the speed of ether through a medium like glass. And one of the things that he does is in using the wave equation, and this will come up later, he uses increased density inside of a medium causes light to slow, was his presumption. However, it is exactly equivalent to presume that decreased rigidity inside of the medium is actually responsible. So those two things are equal. I want you to keep that in mind for much later on. But the important thing to note here is the coefficient of ether drag. Von Laue shows is equivalent to relativistic velocity addition later on after relativity. So 1839, James McCullough publishes an essay towards a dynamical theory of crystalline reflection and refraction, and in which he proposes a new form of elasticity for the ether, and it is held to be non-physical. So that is one of the claims, one of the understandings that happened at that period of time, is that this sort of ether is they can't think of a type of our typical elasticity has to do with crushing and moving of particles in a very particular way, and we are still at this point in history developing our theories of elasticity. And that's something that Kelvin will do a lot of work on. 1851, Fizeau performs his famous experiment to determine the actual drag component of ether, and he proves Fresnel perfectly. Okay, in other words, what Fresnel predicted was exactly the amount that that light was dragged along by the water in the tubes where he shot light back and forth across it. That is very important to understand. Fresnel predicted it. Fizeau showed that it was absolutely true. Then in 1855, we know James Clerk Maxwell, he uses inviscid fluid mechanics, it's very important, to explore on Faraday's lines of force. And what he's talking about is, though I will often substitute the vortex, the line of the center of the vortex for the line of force, he was actually talking about the fingers curling around as lines of force instead of the thumb. Okay, and so he describes the vacuum based upon molecular vortices. Both on Faraday's lines of force and on lines of force were very long papers going into great detail. And once again, this is inviscid fluid mechanics, which means it is a non-compressible fluid. And so once again, we have a type of wave that is not familiar to the people of the time. Okay, 1867. Kelvin, so Thomson and Tate published a treatise on natural philosophy. It's a groundbreaking seminal work on fluid mechanics, hydrodynamics, and elasticity. It is still foundational today and relevant today in a number of fields. And also in 1867, Kelvin publishes the vortex theory of the atom, which is a foundational paper for knot theory. Now, it is actually that is where knot theory came from, and it is a model that is also in an inviscid fluid, which is therefore compatible with Maxwell and McCulloch. 1845 to 1886, the Stokes complete ether drag model is dominating for some reason in people's opinions over Fresnel's partial drag because of aesthetic convictions alone. They don't have a real good reason for it. They just don't like the idea of partial drag. And so it just sort of becomes popular within the community. However, partial drag does account for all the optical ether drift experiments sensitive enough to detect first-order effects such as Arago, Fizeau, Hooke, Airy, and Muscard, and is fully compatible with observations of stellar aberration, because that was the main problem at that time, was stellar aberration. We see the movement of starlight depended upon the orbit of the Earth, and that it was thought to be difficult to explain. There's a couple of things that we'll go into in some other presentation, but for now, just simply understand that that was what they were trying to resolve. And partial ether drag, because it is a small component, would actually be compatible with all of those observations. 1887, Michelson conducts the eponymous landmark experiment with expectations of full drag or not. He does not actually think of it or talk about it in terms of partial ether drag, because that was not the current favored ideology. And he reports an east-west wind that was 1/40th of the expectation value. Now, I'm putting emphasis on things here because it's very important to understand how it was that he reported the paper, and I really recommend that people go back and read the original paper and look at the actual data and plot it themselves. So, however, he conducted this experiment with white light and in open air, and these things are both very important. And what it did show was a characteristic dual sine wave of results. It was not random. It was not a random plot. It was a dual sine wave, exactly as would be expected of an ether wind. And that speed would be at its maximum between 8 and 12 kilometers per second at a minimum. That was one calculation, taking the straightforward calculation. However, if you expect that a relativistic ether, which we will be discussing further as we go along, then the only thing that it would be measuring is the ether drag in air, which has to do with the index of refraction of air. And that would be roughly 300 kilometers per second, according to Fresnel's drag. So understand that the Michelson-Morley experiment in the appropriate ether theory does not detect anything other than the ether drag of the air. And so therefore, of course, it will be perfectly null in a vacuum. And we'll continue on from here, however, because I do have to give an overview, because there's a lot of information I need you to get all at once to be able to understand the total picture. And then we'll deep dive at a different point. So The Michelson-Morley experiment has never actually been replicated in history except by Dayton Miller. He did tens of thousands of experiments, and he actually was one of the first people in physical sciences to do a double blinding procedure where the person performing the experiment, the person writing it down, neither one of them had any idea what was going on. Really, really interesting science. He also duplicated exactly the same results of the Michelson-Morley experiment with the variations having to do with the sidereal day and the equinoxes and the solstices, which have to do with the distance of the Earth from the sun. So he got the same results as the Michelson-Morley experiment at 8 to 12 kilometers per second. Now, you have to understand, let me continue to digress just a moment on the Michelson experiment. When Michelson reported the 1/40th, he was talking about only the east-west component. Now, that is not taking into consideration that the wind might not simply be an east-west component. And secondarily, because it is a second-order effect, there is a nonlinear relationship between the speed that it means and the reading that you get. That is why the actual reading that he get, even in a straightforward looking at it, is 8 to 12 kilometers per second, which is 1/3 of the expectation of 30 kilometers per second. So there's something to understand about that experiment that a lot of people have not properly discussed. Let's continue forward. 1889, Fitzgerald publishes the first expression of the relativistic factor of change. Now, a lot of people aren't aware of that. It was something only recently discovered by historians, that he was the first to publish it in its simplest form. So he mathematically was intending to describe an illusion caused by ether's anisotropic effect on the propagation speed of light, which mimics constancy. So in other words, what I'm trying to say here is that Fitzgerald was mathematically modeling what would happen to a Michelson-Morley experiment and how it could end up being null, even though there is definitely an ether wind impacting the motion of light. And so there's, instead of, like, for instance, going across the wind, it would have to travel at a triangle. And of course, when you're going up into the wind and back, it's going to slowly catch up to the leading mirror and then bounce back quickly. That is mathematically expressed in a certain way. That is what exactly the change factor is, a mathematical expression of that particular attempt to model an illusion, a perspective illusion. Very, very important to understand. Okay, then I continued too far forward. In 1889, Kelvin publishes on a gyrostatic adynamic constitution for ether and solves the non-mechanical claims about rotational elasticity, thus giving a fully workable mechanical model of the field concept. So a lot of people in history are aware that that McCulloch and Maxwell are responsible for the field concept, and that it is related to this concept of rotational elasticity. Now, keep in mind, Kelvin is one who gave us our original understanding of elasticity. Then he also continued forward right after the Michelson-Morley experiment and gave us a model of rotational elasticity that is physical in nature. He built models, etc. This is a lost part of history. A lot of people have forgotten. Okay. Now, 1889, 1904, the Maxwellians, great book by Bruce J. Hunt, including Fitzgerald, Heaviside, and Hertz and Lodge, used concepts from McCulloch and Kelvin to reorganize and re-express Maxwell's work. So the papers that Maxwell originally did, the 4 equations of what we call Maxwell's equations, they were actually given to us finally in their final form by Oliver Heaviside, one of the Maxwellians. And So simultaneously, at that same time, Heaviside, working with Kelvin, develops a model of electromagnetic effects that account for physical length contraction of particles in ether. By particles, I mean Kelvin's types of particles, which are these vortex atom model type particles. And Lorentz fully articulates the kinematics of relativity, but his electron model is lacking. So you have to understand Einstein's paper on relativity, on the electrodynamics of moving bodies. His first part, the kinematical part, he is re-expressing what was already done and well established for 15 years before him. It was not in any way questioned that all of the length contraction and time dilation had already been established. Time dilation was given us by Larmor. He was another person who was working closely with Fitzgerald and the rest of that group. So what we have beforehand is the electron model by Lorentz with the kinematic model. So that you have to look at it in two parts. So then in 1905, simultaneously, there's a little publishing error we won't talk about. That's too much of the history. But Poincaré and Albert Einstein both articulate this mathematically equivalent extension of Lorentz's work to replace Lorentz's model. So Lorentz has his own electrodynamic model. It doesn't work. Everybody says, everybody agrees that it's got problems. Poincaré and Einstein both give the secondary part. So that is the electrodynamical part. Einstein was not claiming the kinematical part. He was explaining the kinematical part. Einstein's what he was giving us was the electrodynamical part, the second part of the paper. So in his paper, he eschews the necessity of discussing the ether for the extension of electrodynamics. In other words, he kind of gives us the first version of shut up and calculate, because there are these various debates that have been going on for far too long about the ether. And so he wants to just end the debate and move forward is kind of his view of it. But there's no need for us to look at that because this works just fine this way. We don't have to consider it. Let's just move forward. But the thing is, the Poincaré's exactly equivalent model is mathematically equivalent. This is all historians agree about this. His mathematically equivalent model works with an ether, but it both requires and grants additional components to maintain the mechanics of the illusion initially described by Lorentz, Fitzgerald, Larmor, and all of those who developed the change factor. In other words, the cause of the change factor is the motion of the ether and its effect on light. That is where the change factor comes from. That is what is a description of, and that was still required within Einstein's version. Poincaré's version. Okay, 1907, Hermann Minkowski conjoins space with time and articulates a useful mathematical formalism, which presupposes isotropic constancy and conjoins space with time, thus promoting reality to a true 4D without any empirical basis to add the possibility of infinite additional 3D realities embedded in one single moment. So what I'm talking about here is that 1905, we have these two equivalent theories. One works in ether, and one and they are mathematically equivalent. One just doesn't think about the ether. And in 1907, Minkowski then produces a mathematical model that gives a very specific differentiation point. This is a bifurcation point in the history of physics when Minkowski does this, and this is an addition in relativity. It is not relativity. It is a non-empirical actual addition to relativity, and I will discuss further later on. But it is cannot be falsified according to modern scholars. So what you have to understand is there is a difference between anisotropic constancy and isotropic constancy, and this has to do with the one-way speed of light. So that is there an effect in the Michelson-Morley experiment where light traveling up and back, no matter what speed you're going, it's getting shortened just the right amount to always come out to seem constant? That is the Poincaré relativistic ether version that they were working on for 15 years before before Einstein's paper. Or do we simply believe that light travels the same speed in all frames of reference in all directions and that there is no illusion? That is codified in Minkowski's methodology. You have to understand that it is mathematically codified in that methodology, and it is a claim that does not have empirical basis for that claim. So when you codify that, you have to conjoin space with time. It is a necessity for it to mathematically function, and you have to promote reality, because you have to understand, though they were using the four-dimensional, the fourth dimension in the prior theory, with Lorentz and Poincaré, it was not a true additional dimension as much as it was just simply a way of keeping up with time differences, because those time differences were very real, because it had to do with the difference in how electromagnetism mediates process. However, when Minkowski gets involved in 1907, what he has done is instead promoted the dimensionality of reality in his theory. What I mean by this is one single moment is four-dimensional. And that means that it's just like if you take a two-dimensional sheet, adding a third dimension allows you to have infinite additional two-dimensional sheets, infinite additional ones. So by promoting reality, you have basically allowed the ability to have infinite additional 3D realities in a single moment. So understanding this difference between using a fourth dimension as simply a notation for time differences and clock differences and things that are really a difference in process that are measured by clocks versus altering and promoting the dimensionality of reality, that is only Minkowski's addition. And there is no empirical reason to do so because we already had the empiricism developed for relativity prior to that point. So understanding that it is non-empirical, and not only that, it is claimed that the one-way speed of light can never be measured in modern times, which means you cannot falsify space-time, because that is the differentiating experiment between relativistic ether, which is by all historians is known to be mathematically equivalent with the Minkowski spacetime. So let me take a drink real quick, and I will continue in just one moment. So, 1907 and 1909, Einstein publicly quips about spacetime. Since the mathematicians have invaded the theory of relativity, I do not understand it myself anymore. We don't have an exact date, but it was specifically him talking about spacetime. So he has therefore publicly insulted his former teacher and mentor, Hermann Minkowski. 1909, this enormously influential figure in the very small school of German physics unexpectedly drops dead from appendicitis. David Hilbert writes his obituary. Max Born delivers it at Göttingen. This is, of course, two major figures in physics of the time. I simply pointed that out for those who are aware of these influential figures in physics. So around the 1912 era, numerous polemics between Einstein and other scientists. These are public polemics, in other words, arguments in the public discourse. They pressure him to use Minkowski's formulation, and Max Abraham, in particular, who's supporting a non-relativistic ether theory, publicly and falsely accuses him in Annalen der Physik, that's the major publication of the time, of giving the death blow to relativity by exploring variable light speed or anisotropic constancy. So that is counter to Minkowski's isotropic model. So he's being ridiculed. First, he's pressured, then he's ridiculed. And there's this fundamental misunderstanding because he is continuing. There are multiple times that Einstein says that we have to give up the idea of constancy. And what he means by this is isotropic constancy, not anisotropic constancy. In other words, he is starting to support one model, which is the relativistic ether, over the other, but only partially. So 1915, Hilbert uses Mie's 4D generalization of McCullough's ether to approach general relativity. He works so closely with Einstein during the publications of GR papers that some scientists give primacy to Hilbert for GR for many years afterwards. It's only been very recently that people have found some little particular paper that has kind of answered the question, and for a lot of people to say that no, we still believe that Einstein should be given primacy for GR. But the point is that they were actually corresponding very closely, and Hilbert did sort of independently come to general relativity as well. And they were, at the time that Einstein was publishing, they were working together. So it's kind of a collaborative effort, if anything. And then Hilbert is also a staunch promoter of space-time developed by his best and truest friend. In other words, Minkowski is Hilbert's very best friend. And he also states he was closer than any brother. So understanding the social environment, and the fact of the matter is, once again, when you have two mathematically equivalent theories, it's only a very subtle differentiation point that makes a bifurcation, because they are interworkable, which means Minkowski's formalism will work for most considerations of the ether version. All right. So these are a couple of the quotes by Einstein between 1907 and 1923. It's just a few of them. I've got at least 5, I think maybe 6 or so, and you could probably find more if you kept digging. However, the writer of these lines is of the opinion that the theory of relativity is still in need of generalization, in the sense that the principle of the constancy of the velocity of light is to be abandoned. On the other hand, I'm just going to read some of the excerpts here. It's not to be regarded as independent of the gravitational potential. In other words, it is locked to the gravitational potential. You must understand constancy in the context of the gravitational potential, which you have gone away from the previous theory of special relativity and into the more general theory general relativity. So the constant of light, speed of light no longer holds is another thing he says. This theory of special relativity therefore applies only to a limiting case that is nowhere precisely realized in the real world. That's Albert Einstein, numerous quotes. So I'd like to take a moment here to say that basically still ether is marching forward in the background. 1906, Poincaré writes The End of Matter. It's a very important paper. He articulates the mass energy equivalence. He further articulates mass energy equivalence in terms of ether theory, which he initially explored in 1900, which was cited by Einstein in explaining that electrons are holes in the ether. He basically talks about the fact that they are finding that the mass of a particle is they first had a rest mass and then a inertial mass, and basically he was finding that there was no inertial mass, so there was no mass according to what he was understanding within his theory, and that is why he came to the idea of holes in ether. And like I said, that was the continuation of ether theory. In 1909, the Kossarab brothers write the theory of deformable bodies, thus encapsulating all prior rotational models of McCulloch, Maxwell, and Kelvin's ether into a successful continuum model, which describes superfluid behavior. And what I'm saying is that is the model of ether. It's been rediscovered in the 50s and is used as in material science. It's called micropolar elasticity. It's far better than a lot of other continuum models, but it is also a way of describing superfluid behavior. And I'm saying that it is the superior model of treating ether, and is really the only model of ether that will work to analogize all of our various particles and things of that in modern physics. 1913. Georges Sagnac, I don't know how to pronounce his name. It's driven me crazy for years. He demonstrates the effect bearing his name, revealing an anisotropy in the speed of light that contradicts the fundamental constancy postulate of special relativity, but not the illusion of constancy found in relativistic ether. Now, a lot of the descriptions around the Sagnac effect are very, let's say, I don't know how to put it nicely, but they're just dumb. And it basically, the Sagnac experiment just shows the exact same thing that Einstein was getting to, is that the constancy doesn't actually fully work. It is an idealization. And what we're finding through all of these various experiments is that constancy, anisotropic constancy, two-way constancy, where there's a compensatory illusion, that is functional. So 1916, 1920, Ernest Sommerfeld, German physicist who later makes significant contributions to quantum mechanics, publishes key works exploring the quantum theory of spectral lines, giving us the central guidepost of quantum theory, the fine structure constant. His continued work repeatedly mentions a medium through which electromagnetic interactions occur, explicitly highlighting his underlying belief in the necessity of a medium. So, and then in 1920, Einstein gives a speech at the University of Leiden, which can be summarized with space without ether is unthinkable. And now one of the arguments about that is like, oh, he was just talking about space-time. No, he wasn't just talking about space-time. For in such a space, not only would there be no propagation of light, but also no possibility of existence for standards of space and time. So no propagation of light, meaning it is a light-bearing medium that he is referring to. He says it explicitly right there. So understanding that what he is referring to is relativistic ether, but he is still loyal to Minkowski, and Minkowski's mathematical model is extremely functional within limits. And those limits are for absolutely most, but the overwhelming majority of circumstances, the Minkowski formalism will function. However, it will give you a very bad theory about how reality functions. And there are certain edge cases that you can explore, and that that I've already pointed out some of the issues here. 1922, Erwin Madelung, a German physicist, publishes Mathematics. Oh, I don't know how to pronounce that. A work that introduces mathematical tools for physicists with a focus on using fluid dynamic analogies in physics, further establishing a theoretical framework for understanding the ether. So understanding that there is, at the same time right now, there's a change in what's happening in Germany, and the German science is starting to dominate in a certain way. 1923, remember I mentioned Dayton Miller. He was a respected physicist at the Case School of Applied Science. He announces the detection of an ether drift. based on years of meticulous experiments. His findings, which directly challenge the foundations of relativity, are met with skepticism and resistance. But he wins the 1923 Newcomb Cleveland Prize from the AAAS for the successful detection of ether. And he actually is the reason why Einstein did not receive a Nobel for relativity, because he was proving that there was an ether. Unfortunately, he had the more simplistic, non-relativistic idea of ether in mind, and that is not functional. Only a relativistic version of ether is actually functional. In 1924, Louis de Broglie completes his research on the quantum theory, which it describes the wave nature of matter, wherein pilot waves produced via a difference between relativistic frames guide the motion and nature of a particle in a way only relativistic ether can accommodate. You need to read that paper, and you will recognize there's a difference between the frames that require a preferred frame of reference, which is what Einstein eventually calls the Machian frame, or gravitationally defined frame. There's a wide variety of ways in which he speaks about the ether as a preferred frame, and general relativity is a preferred frame theory. In 1926, Schrödinger publishes Quantization as an Eigenvalue Problem, which he introduces the Schrödinger equation, and in it he prolifically cites, describes de Broglie's paper as his primary source, and he is developing a physical model. In other words, the waves are physically real, and what he's talking about, which is why the Schrödinger equation actually gives us spherical harmonics. They're roughly equivalent. You'll find that whenever you look at spherical harmonics and whenever you look at our actual electron shells, they are basically the same. So he is going from there. So now I'm going to take a moment and we're going to jump forward, because what I've established already has given us kind of a starting point to talk about what exactly is the ether, how does it work, and what evidence do we have, so we can start working backwards from our most recent developments and how that's going to give us some value. I'm trying to fit in a lot of information all at once, so you'll have to excuse me. I'm going to take a second drink. This is requires a little bit. So we have Madelung giving us the hydrodynamic. He casts quantum theory in hydrodynamic form successfully. I didn't mention that yet because I just made these. It's actually a little bit further down in my slides here. And basically through the Wigner-Weil transform, we have a way of understanding quantum theory from a hydrodynamic perspective and transforming between them. That's one of the ways in which we will probably first start to match up our analogies with our current physical models to the fluid model, and how we'll be able to transfer over to a fluid model. So what we're going to do now is start working backwards towards Madelung, Schrödinger, and de Broglie. So these are some slides I pulled from a different place because I was working till like 3 or 4 in the morning on this, so I had to pull it from a different one here. So here's the most recent way of showing that there is a model of quantum physics and the apparent stochastic behavior that we no longer need to accept that reality has this pure randomness at the bottom. We can instead expect that there is something called chaotic determinism. This is something, as we started to understand chaos and feedback loops and the complexity of evolving systems, that we now can have something underlying. In other words, the quantum physics actually is the probabilistic treatments are saying something very real, but probability is a way of treating something that is extremely complex and has a lot of detail in a way that you can kind of grasp the big picture of it. However, if there is something underneath that probabilistic treatment, then there may be additional ways to exploit that additional layer of information. So in other words, what we're talking about here is below the stochastic treatments. And so here what we have is the Yves Coudet comes up with the silicone walking droplet experiments, where a droplet of silicone is taken from the main bath, which is driven at a frequency below the Faraday threshold, and then with that droplet, when released, will bounce indefinitely on the surface. And then one of the ways in which it expresses itself, you'll see in the top right hand image there, it will simply move around the corral in a what looks like a random pattern. However, that random pattern over a period of time is the Faraday wave mode of the cavity, which is exactly what we see whenever we trap an atom in amongst other atoms. We see the same form of waves. And so you can see there are a variety of ways in which the researchers in the silicon Walker experiments have proven the dual slit experiment, quantum tunneling. Every quantum behavior can be shown to be analogized by this. In other words, there is a way in which we can show that there may be a system, and that system, and I'm saying it's ridiculous to not accept that this is the appropriate system, because you're actually accepting that there's randomness below the surface is a magical belief, in my opinion. But this gives us an actual layer of determinism to go back to a more mechanical version of reality. And at this point, if I could ask you to bring up one of my favorite videos, because I did want to show some of the other behaviors live, and there's a great little video that I sent over to you, and it is, let's see, it is in my the best collection of pilot wave walkers videos. It is the third link in the video that I sent you. I mean, the follow-up email that I sent you, Tim. If you could,
yeah. Sorry about that. I'm juggling windows here. Okay, so let me bring this up.
Yeah, somebody just put together a really spectacular collection of videos. It's actually kind of funny because they made it entertaining, but it is
yeah. And can I ask what was the name of it again? You sent me over a bunch.
It's the third one there, and it is the one I labeled the best collection of pilot wave walkers, and it actually is named pilot wave walkers when you go to the video.
Okay, because I have qubit walkers.
Yeah. Oh, yeah. Sorry, that was what it was called. Yeah.
Oh, okay. So let me bring that up. Okay. So sorry about that. Yeah, and we have just about 15 minutes left. So okay. So sorry about that.
So you can see these self-organization behaviors and these various modes, like where it's jumping, etc. In this one image below, there's another one of the behaviors that it does. So there are quite a lot of quantum-like behaviors that we find. And John Bush at MIT has started to put together something he calls pilot wave hydrodynamics, which recovers all those various things.
Okay, there we go. Can you see that? Okay.
Yeah. Mm-hmm.
I'll put that in theater mode. Hopefully.
So here, so you can see there's one of the ways in which the wave that accompanies the droplet goes through the two slits. And eventually, you actually replicate the two slit experiment. Then you have these various formations of various patterns that are they're just reminiscent of a wide variety of behaviors that you see at the quantum level. And I just love some of these demonstrations. Like that one is one of my favorites. And so yeah, it goes through some of these, the locking together in various modes. You see these lattices. There's an instability of a lattice. Some of them rotating around each other. So that's a fun little video. And now there's one other thing that I would like you to bring up, if you could, in the background as well, and that is the first video, the first link I sent you, which is I think it's called I don't know, it's something German, and it's water sound images is the first link there, and it's cymatics, and it's about so it's a cymatics video, and this is actually really funny. I recommend you guys look at this this video because it's pretty funny. It's very entertaining. They did a great job with it. Can you bring up the water sound images one instead? That's the cymatics, science versus music. That's a one that's very entertaining, and really you kind of have to watch with sound, but that's not what I intended to bring up. I was just going to leave that as a video for people to watch. But these are various ways in which people are using Faraday Faraday waves, because cymatics and Faraday waves. Okay, here we go. So in this demonstration of cymatics, which is basically using the Faraday waves, you can see there that it is a toroidal vortex, and by the bubble that is circling along the top, and so this torus it's just a droplet of water that is driven at the correct frequency and amplitude combination. And now you'll see these alternating vortices in this direction, as well as vortices in that direction, and those actually match the d orbital shape that you're familiar with. And so you can see that there's this interplay of spherical harmonics that allow vortices to behave in very particular ways. And now if you were to go forward here, you'll find that there are various shapes that will arise. And you have to keep in mind there is a vortex or multiple vortices within these figures that arise when you hit the appropriate resonant frequency and amplitude of the waves, and the number of waves that are contained within one actually determine the number of vortices that are in them. And you'll find that, for instance, a lot of people I'm sure are aware of the hexagon on the top of Saturn. That is it actually is 6 vortices that are kept together by mechanisms of resonance like this. But a lot of people are not aware that the same thing exists on the top and bottom of Jupiter. There is a octagon of vortices, and on the bottom of it there is a pentagon of vortices. So this wave vortex duality interaction is a very important part of the theory. And so I wanted to start to introduce some of these concepts as what it is that is, how does the mechanics of the ether lead to particle formation, and what is the relevance of knot theory. So what we're seeing here is the formation of knots through resonance because of the way in which waves have to pass through each other. There's a mechanical interaction that leads to rotation, and that is where we get these vortex filaments that that automatically are instantiated by the waves that are going back and forth. So these are some of those solid ones. Let's get back to the presentation, if you don't mind. All right, great. So let me get to the next one here. So you have to understand the idea that Kelvin was talking about was this ring vortex model with vortex filaments, and that the lines of force and vortices were a critical and crucial part of the way in which electromagnetism worked, according to all the developers of electromagnetism. The only person who didn't explore this model of all the developers of electromagnetism, Heaviside, Maxwell, Lorentz, all of those, the only one who didn't explore this aspect of it was Einstein, actually. So what we find is that Kelvin's knot theory of atoms gives us some insights into newer theories such as skyrmions and solitons, topological defects, in understanding that what the ether may be like. And let me also just give you a quote in 1951 to understand that quantum, it did continue forward all the way into quantum theory, and Dirac wrote Is There an Ether in 1951, in which he finalizes it with we now have the velocity at all points of spacetime playing a fundamental part in electrodynamics. It is natural to regard it as the velocity of some real physical thing. Thus, with the new theory of electrodynamics, we are rather forced to have an ether. And so this was kind of an answer to the only one thing that Einstein said that was incorrect in his address, that was space without ether was unthinkable. As he said, the parts don't move against each other at the very end of it. However, we know that frame dragging or the lens throwing effect does occur. And then, of course, Dirac is also pointing out that there is a motion of space against itself. And so therefore, we also show that there is a movement of space that is relevant here. This is just a demonstration of a multidimensionality. That is the reversible laminar flow experiment that is a favorite of David Bohm's, who brought back pilot wave theory in a form that that people did not find aesthetically pleasing. However, John Bush, by using de Broglie's wave equation, which basically shows this feedback loop, which allows it to which causes that semi-random behavior. He actually shows a way in which pilot wave theory now is a functional, workable way we can think of how the pilot wave works. And so this actually gets into my paper on deterministic entropy, which I won't be going to here. So just going back to the superfluid vacuum, one of the things that we look at down here in the bottom left, these are called plasma vortex crystals. Whenever you perturb a plasma, if it is allowed to be in a two-dimensional form, which means that it is very important that it does have those borders, then one of the things that happens is they self-organize into crystalline forms. And understanding that one of the things that we find in superfluids is the automatic arising of vortex filaments. That is just part of, as a wave travels through a superfluid, it ends up creating these vortex filaments that are all throughout it. And so what I'm saying is that there is, struck through the ether, there are these vortex filaments. They are a very important part of the way in which the ether works, and understanding them from Maxwell's and Faraday's perspective. We have a way in which we're connecting all the various ideas of electrons and the formation of particles. But I'll have to get back to the reason why a 2D border is important to organizational principles. Let's see, from this one, we just wanted to see some of the self-organization of bouncing droplets. You see that those are very familiar things there. The one thing I wanted to point out is the idea of a cavitation. So you see not all of the of why that opens up is a gas. That's why it then collapses with the gunshot there in the bottom left-hand corner. It's one of the best examples that I can show you, but understanding that there is a way in which something can be opened up that is more of a vacuum is very important. But what we'll find in exploring this idea of holes in the ether as electrons is actually the combination of a wave on a vortex filament. So you have to understand that when waves go across vortices, they can be spun up by the presence of the wave. So therefore, when a wave combines with a vortex, what you can have is it crossing a threshold that causes the vortex to open up into a cavitation. And so this is one way in which we can model free moving electrons. This is some of the exploration of the holographic model. I'm not sure that this is extremely relevant right here, but just looking at the way in which waves come together. And there are some aspects of the, let's see, the ER equals EPR, the entanglement issues. Actually, you have to start dealing with holography, but I really shouldn't go that way because I'm running out of time. So let me just point out that basically electromagnetism organizes vortex filaments, which is what Maxwell was pointing out. So that is the organization of them. And what you'll see in a moment, I'll show as the last thing for my presentation, I'll show this when you use a Heelshaw plate, which is you trap a ferrofluid between two glass plates and light it from the side. You can actually visualize the lines of force in a different manner that gives you a better idea of the organization of the vortex filaments that I'm talking about. And basically the idea of gravity is that it is a bulk local vorticity. So in other words, it is the, I'm loath to use the word density, but it is the frequency, the amount that you will find these vortex filaments. The vortex filaments, as the speed of the ether is rotated very near the speed of light, that is what's able to cause the cavitations, because the speed of light is merely a measurement of the actual properties of the ether itself. So basically, whenever we go all the way back to Fresnel, and instead of using the density, increased density in an object, we instead have a reduced bulk modulus, or actually it's a reduced rigidity. Then what can happen is that will lead to the exact same equation for all of the same things. And what we have then is a method by which we might actually find at the quantum level there is a nonlinear effect, and which can allow for solitons. And basically our idea of bent space is that there is a slowing of light, and light is responsible for time because it is the mediator of communication of change between objects, or actually there's a slowed waves in the ether, whether that be gravitational waves or any sort of wave, because the waves are in fact ether. So I'm not going to get into the further stuff there, but basically what we end up finding in some of my other things here, and like I said, run straight out of time, but it looks as though as they continue forward, there's further developments of Madelung's theory, and then the Nazis self-sabotage themselves because they conflate relativity with no ether. Whereas what we've been talking about this entire time is that relativity and ether are fully compatible, and that there was a completely mathematically equivalent version of relativistic ether that Einstein was eventually supporting. And because of being jackasses, they conflated these things, and that led to them not advancing their science in very particular ways. And some of the interesting things we find is that these various meetings between Werner Heisenberg and Bohr, and the possibility that they were actually actively sabotaging the Nazis, and that's why there was a secret meeting between Bohr and Heisenberg before he defects, and Heisenberg stays. Very important thing to note that Heisenberg did stay in Nazi Germany as part of their nuclear program. And so what I believe happened is he was actually actively sabotaging their program, and one of the ways in which he was doing that was by focusing on a stochastic treatment instead of a deterministic ether-based treatment. That will be it for this presentation, but we will just deep dive on various experimental history, the linchpin experiments, the one-way speed of light that we mentioned, and then also we can get into holographic theory, rewriting string theory, and deterministic entropy and more. So thank you very much.
Well, and Shiva, thank you, sir. I genuinely, you were one of my favorite people. Like there is smart, and then there is your level of smart. And when you dig into this, it's the conceptual models and the history and just the wealth of knowledge and putting these puzzle pieces together. It just consistently blows me away. So thank you so much. And you know what? I'm going to bring everybody else in. We're pushing on time today, but I'll tell you, man, here. So let's and you know what? Let me take that out. Let's do this the right way. Everybody give a big applause to Shiva Meucci. And so just for the guys to know, I've asked you to present on more of these, and if you're open to it, man, I would love to have you back and just run through these, you know, over the next few months. Again, the depth of what you've gone into is just mind-blowing. So thank you, man. Thank you. Okay. Well, I'm going to take everybody out now. And so our next speaker is none other than our very own Dr. David Chester. And Dr. David Chester is no slouch himself. You are also one of my very favorite people, and also incredibly super duper brilliant. So you were going to be talking about longitudinal waves. And then you also, I think you have a presentation to upload, right?
Yeah, I was going to share my screen. Hopefully I can just do it that way.
Yeah.
I can send you the slides later. I just finished them.
There we go. Okay. Add to stage. Perfect. And so I'll be here in the background. Just let me know if you need any help. And thank you as well, because again, you are incredibly brilliant, and I love it that you're digging into this. So.
Well, thank you to Tim for giving me the invite, and also thanks to Shiva for that talk, for going through a lot of the history, because we'll be diving into some of the mathematics of history as well. So it was a good transition here. So we're interested in alternative propulsion. Our goal at this conference is to understand alternative approaches. And this means that we shouldn't use rockets or oil, which motivates electromagnetic sources of energy. Ideally, it would be nice if we could use this electromagnetic energy to warp space-time and usher in a new era of metric engineering. So if we can understand a deeper level of electromagnetism and gravity, then maybe we can find some new insights for propulsion applications. So I'll be discussing some notions of unification, but it's not about a theory of everything. So no dark energy, no dark matter, no standard model. Just we're just restricting our study to electrodynamics and gravity. And so to grossly oversimplify the history, essentially what occurred is Maxwell's theory predicted that light were these transverse electromagnetic waves in an ether originally, and then soon after, Hertz experimentally detected these transverse waves. He was somewhat agnostic about whether the ether existed or not, but more was just trying to state that some version of Maxwell's equations was correct. And so Tesla immediately contested to this because he thought that electromagnetism was described by longitudinal waves. He also thought that might be related to gravity, and he talked about radiant energy. And I'll just briefly mention, it's also curious how Sir William Crookes, who was the discoverer of plasma, he actually coined this term radiant matter, and he was a mentor to Tesla as well. So it's curious because some of these longitudinal modes turn out to be related to plasma in some sense, mathematically, at least you can look at it in that way. So there's kind of this debate. Some people look at Einstein and Tesla as rivals. While Tesla believed in this ether, Einstein's special relativity found that the Lorentz ether model was unnecessary to describe the Michelson-Morley experiment. And this eventually led to Einstein's general relativity, which predicted transverse gravitational waves, while Tesla believed that the ether contained longitudinal modes, which related to Earth's gravity. As we dive into the true nature of gravity, we can ask the question of whether Tesla was onto something at all, or if maybe we should just stick to Einstein's general relativity as the primary theory. So what if it's actually possible that both Einstein and Tesla were in some sense correct? Einstein spent the rest of his life pursuing unification of electrodynamics and gravity, but he never reached his goal. He always regretted the removal of the ether later in life. And in this talk, I'm going to describe a new approach to Einstein's earlier attempts on unification of electromagnetism and gravity. And to my surprise, the theory suggests that Tesla might have actually been partially correct about the nature of electromagnetism and gravity. So by the end of the talk, we'll understand what that means. So my approach initially was to just start writing a textbook where I would revisit Maxwell's treatise and dive into 4 obscure concepts in electrodynamics. So these 4 concepts are: 1, the vacuum as a medium, or at least give an exhaustive study to macroscopic media because the equations are the same. Number 2, the study of longitudinal electromagnetic modes. Number 3, the possibility of magnetic monopoles. And finally, number 4, the hypothesis that Whittaker or Hertz potentials might actually contain physical information. And so while all the mathematics for these has been discussed in isolation, as I've been doing more research, I've realized that I haven't found any sources that certainly not that combine all 4. Maybe there's ones that will look at 2 at a time, but I figured rather than trying to really explore new theories of electrodynamics, if I can find basically a more comprehensive view of all these phenomena that are discussed, maybe that will provide a bigger perspective for us to tackle this problem. So now my current intuition is essentially that these Hertz potentials are analogous to the strain of the ether, but not literally strain in the normal sense. And this then motivated this idea of unifying general relativity with these Hertz potentials. So that's going to be a big thing that I'll talk about at the end of my talk. And I want to mention that one of the main reasons I'm presenting here today is because I'm looking for suggestions on experiments. While I'm primarily a theorist, I am starting to do experiments. So you guys as engineers and experimentalists out there have a lot more knowledge about some of these obscure phenomena that so that there might be some dialogue that we can have here. And so I can't really focus on everything today. So I'm going to mostly focus on revisiting Maxwell's treatise, focus on the longitudinal modes, and I'll give a review of Hertz and Whittaker potentials, and then finally get into my view on just a slight tweak to Einstein's unification by using Hertz potentials. And then I'll conclude with some concrete yet speculative ideas for propulsion based on that theory. And so you can find a lot of bold claims on the internet. And a lot of these ideas were inspired by Nikola Tesla, such as longitudinal modes, resonance with the ether, and free energy. And some even speculate that these have propulsion applications. So in 2017, Bahman Zohuri wrote a textbook on scalar waves, which claims that the Navy sent this type of signal that could propagate through water to transmit information at the speed of light without using something like radio waves. And Stephen Greer claims that these are the secret to unlocking free energy and UFO technology. Well, so such extraordinary claims clearly require extraordinary cartoons generated by ChatGPT. You can see that barely even knew what a naval ship is, but hey, it's within line with what we read on the internet. It's about as accurate as some of the information out there. So another person who inspired me to look into Maxwell's treatise was Tom Bearden. And he made a lot of different bold claims about the history of electrodynamics. And while he got a lot of details wrong, I was able to find a story that closely matches some of what Bearden was saying in terms of quaternions and Whittaker potentials. I will not focus on any of the theories that Tom Bearden or his collaborators worked on, but just keeping his story in mind in the back of my head was somewhat inspirational for me to actually review a lot of this material. So Tom Bearden claimed that there were 20 equations in Maxwell's treatise, which led to the loss of important physics. He also claimed that this was due to the quaternionic formulation of Maxwell's equations. Well, Maxwell did have more equations, and he did use the quaternions. The details of what Bearden is saying is completely wrong. First of all, the use of quaternions is not really relevant because you can use vector equations or quaternionic equations. I'll show this more explicitly in a bit. So the use of quaternions in the way that Maxwell used them was not really giving any new physics. And also the 20 equations appeared before Maxwell's treatise and were used without quaternions. So this idea of the 20 equations having new physics is not, or overlooked physics isn't really accurate. But it is true that Maxwell's treatise did have some equations that have not really been considered as much, but they're not really what Tom Bearden said they were either. So we'll try to decompose that a little bit. So what was Maxwell after? Well, really, his main achievement was to provide the mathematical framework for Faraday's conception of the electric and magnetic fields. These fields were first envisioned as fictitious force fields that cause charges to accelerate. And Maxwell actually looked at this as being an ether, and his conception didn't really catch on at the end of the day. But he was successful at really getting Faraday's conception into the mathematical framework that is now in modern textbooks to a large degree. And so now we have this Lorentz force law, which describes how charged objects feel a force from electric fields and currents from the magnetic field. So as we'll show, Maxwell actually looked at this Lorentz force law a little bit differently. But before we get there, we'll just review some of the mathematics. So we can have 3 vectors, which was really inspired by this idea of position having x, y, and z coordinates in some Cartesian reference frame. And so we can have different operations. We can add vectors. We can multiply scalars by vectors. Scalars would just be real number quantities. And so you can also introduce this dot product, which maps 2 vectors into a scalar and is given by the formula right here. And there's also this cross product, which inputs 2 vectors and outputs a vector. And so here you can see what a dot product is actually doing is essentially characterizing how in line 2 vectors are. So you can think of taking a shadow from one vector onto the other, and the dot product will be the magnitude of that shadow. So if the 2 vectors are very parallel, then you'll get a large dot product. With the cross product, on the other hand, they're characterizing how perpendicular different vectors are. So if you have this Cartesian frame, you could take the cross product of x and y and get the z-axis. So you can also go into vector calculus, which takes some of these mathematical operations and then introduces this nabla operator, which is a gradient or partial derivative in terms of 3 components right here, partial x, partial y, and ddz, if you will. And so you can use these to act on a scalar or vector in various different ways. So the gradient acts on a scalar and returns a vector quantity. And the divergence acts on a vector and returns a scalar right here. And finally, the curl can act on a vector and return a vector. So here's the modern formulation of Maxwell's equations. We have the divergence of E equaling the charge density rho over epsilon naught. And there's various other equations. So basically, we have Gauss's law right here. This is called Ampere's law. This is now called Faraday's law, and Gauss's magnetic law, which states that there's no magnetic monopoles right here. So these 4 equations are 8 real equations because we have 2 scalar equations. There's a scalar equation here, and 2 vector equations. So this is kind of also called the microscopic formulation. And it's also worth pointing out that there's other equations that get used as well. So the Lorentz force law, as I mentioned, there's the continuity equation. And you can introduce this magnetic vector potential and this electric scalar potential and find the magnetic and electric field in terms of those potentials. So just to review some of the fundamentals of what's going on here in terms of the vector calculus. So if you think of a parallel plate capacitor, you charge up 2 plates to a constant charge, and you're going to get a gradient in phi, or you're going to get a difference in voltage, which creates a gradient in the scalar potential, and then you'll get a constant electric field, roughly speaking, between the 2 plates. For the divergence, if you just had a point charge with charge q at some point, you're going to get vector fields emanating from that with radial symmetry. And so you can think of the divergence as characterizing those charges. So you would find if the electric field lines are all pointing radially outward, you would get a divergence right at that point, which corresponds to where the charge density is non-zero. Similarly, and then moving on, you can consider currents that will lead to curling magnetic fields. So if you have a current going down a wire, the magnetic field will curl around that. So then we can go into the macroscopic formulation, which is closer to what Maxwell was talking about in his treatise, but there is a slight difference as well. There's no velocity in these equations like Maxwell's had, and I'll show you what Maxwell studied, but this is kind of more familiar. So you introduce this notion of this dielectricity, which then is equal to epsilon times the electric field, and then you get B equals mu H, and then you can express half of Maxwell's equations in terms of E and B, the ones with no sources. But then you now have this notion of a free charge density and a free current density that source D and H. And you can also separate D into this E plus P, where that's the polarization that relates to bound charges, and this magnetization relates to bound currents. So you have this notion of total charge equaling free charge plus bound charge, where the bound charge is typically bound to media. But it's also worth pointing out, I mean, historically, we used to think that the ether was a medium. So as we transition into the modern era, after the 1900s or so, that's when now we only considered macroscopic media, which is now called the macroscopic formulation of Maxwell's equations. So to revisit some of Maxwell's work, it really started in 1855 with this on Faraday's lines of force. And he had this notion of an incompressible fluid to model the magnetic lines of force from Faraday. And then he really, by 1861, he put out 4 papers that really brought in the full scope of Maxwell's equations. So it actually contained a lot of equations in there, but it certainly had a lot of the equations that we now pretty much call Maxwell's equations. And so it's worth pointing out by 1865, there was also this summary of the previous work, and this included 20 equations. No quaternions were used. So that's where Bearden is kind of imprecise in this way, because they came in earlier. So these are some of the equations that were included in 1861. So there was this notion of a current, and he thought of it as a convective current, but then there's this displacement current, and that was really Maxwell's new contribution to understand how that fits into Faraday's law. So this he called this you could think of it as a total current, which then entered Maxwell's equations right here and allowed for a source of the curling magnetic field H. So he did have this notion of a vector potential, which he called the magnetic momentum, which is curious. And the real curious thing is that, well, I'll explain this in a bit. And so it's kind of curious. Maybe it was in the 1865 paper, but when he summarized the equations, at least this equation, which is also studied in the modern theory, is also included here. So he had that back then. And so the one curious thing that's different about the way that Maxwell looked at it is usually now we define this electric field as being minus the gradient of phi minus d a dt. But this notion of the magnetic field with the curl operator and the velocity was included. And so now this more looks like the Lorentz force law, where we think of F equals Q times E plus basically V cross B. And so for whatever reason, Maxwell included this term here in with the electric field, and he still defined the electric field in the same way that we do now. So that's the one main difference about Maxwell's theory that got changed. Another way you can think about it is you could set this velocity equal to 0, and then it would kind of drop, that term would drop out of the definition of electric field. So that's one of the main things that was lost over time. And so Maxwell had 3 volumes of his treatise. The first one basically took those equations and then also added magnetic monopoles, which he called magnetic mass, and this magnetic scalar potential. And so in the second volume, he included the quaternions. And the third volume actually came out after his death, and it was organized by J.J. Thomson. So some of the equations that were found in Maxwell's treatise included, as I was saying, this magnetic scalar potential. He called it capital omega. I'll call it chi in this talk. And let's see, another curious equation is, so he has this electric field, which kind of looks like the Lorentz force law, but then he had another equation for a Lorentz force, which then also included this magnetic force. So it's curious just to see how there's these slight differences back then. And pretty much all the other equations are the same. He was using Gaussian units here. So now we might as well dive into the quaternions a little bit. So it's this algebra that is 4-dimensional. It's spanned by the real numbers, but then there's 3 imaginary numbers. So you have I, J, and K that all square to -1. And you have to add one more property, which is ijk is equal to -1. Or you can also just stipulate the algebra's definition by pointing out that ij equals k and also have that it's non-commutative. So ij is actually minus ji, which is kind of funny. So it's a non-commutative algebra because of this equation right here. And so a general quaternion, we use the capital letter H to really give respect to Hamilton, and also Q is typically used for rational numbers. So we had to use something. And so you have 4 real components, Z0, Z1, Z2, Z3. And so you have this real component here and then 3 imaginary components that would build up a general quaternion. And then you can introduce this quaternionic conjugate that would flip all of the minus signs. So I would get sent to minus I, just like the complex conjugation. But now we can also change the sign for J and K. And one curious thing you can do is if you take Z times Z star, the quaternionic conjugate, you'll get this real quantity that is the magnitude squared of the quaternionic value, which really is actually giving a 4 vector, but not for space and time. It's actually, it's really for 4 dimensions of Euclidean space. And so this is just a simple example where you're multiplying 2 quaternions. So you had 2i times 2 just gives 4i, and then 2i times minus j turns out to be minus 2k. So just a simple example of multiplying with quaternions. Another fun fact is the quaternions are isomorphic to the Clifford algebra CL, 02, which is also the even part of CL3. And so one point I want to make is that these same equations can be found with 3 vectors or quaternions. So if you have a quaternion here, you can think of it as just adding some real scalar with a dot product of a 3 vector. And so you can implement quaternionic multiplication in this way and write it in this formula, in this notation. So the real part would have basically the combination of the 2 real values of a and b, but then there's also minus the dot product of a and b because I squared is -1. So that's where that minus sign is coming from. And so you can also get basically the scalar times the vector of b. So, and then here you're getting the scalar of b times the vector of a. And then you also get the cross product coming out as well. So if you take the real part of a times b, you get the scalar quantity. And if you take the imaginary part, you're going to get this vector quantity. And you could even consider this, this anti-commutator to isolate the curl. So at the end of the day, once you take the real and imaginary parts, there's different ways where you can isolate the 3 vector quantities from the quaternions. So in that sense, basically you can just write most equations in terms of quaternions or 3 vectors, and it doesn't make too much of a difference. Although it's worth mentioning that the quaternions can give a little more natural, it sometimes makes the equations easier to write down, which I'll show later. So basically another thing I wanted to point out is that Heaviside generalized Maxwell's treatise. So a lot of times people on the internet, they're kind of poo-pooing Heaviside because they're saying, oh, he reduced Maxwell's equations to those Hertz-Heaviside equations. So, you know, he got rid of the quaternions, he hated the quaternions, and he made everything simpler. But something that most people are overlook is that Heaviside also generalized Maxwell's treatise, and it was really considered it was Heaviside's last work, I believe, and his most difficult work. So it's not clear if anyone that was, and also Heaviside wasn't really fully respected until after he died. So he had a little bit of a rough life. And so not really anyone studied his work in much detail while he was alive. And so this work largely got overlooked. So I just figured I'd mention that because there's some hidden gems there. So diving into longitudinal modes, Tesla believed that the ether had these longitudinal modes, and if it's kind of stated at a pop physics level that these longitudinal modes don't exist, but it's actually not exactly true. They have been studied very carefully by some of the greatest physicists. So Dirac talked about an ether, at least an ether. Aharonov and Bohm talked about this theory that has these longitudinal modes. Feynman talked about them as well, in terms of basically there's this Feynman gauge of QED that leads to this. And so if you study the quantization of QED in the Lorentz gauge, you'll find that you get these virtual or off-shell modes, and you get these longitudinal modes and these scalar modes. So there are actually two different types of modes. And there's other authors who discuss there as well, Wasser and Van Vlanderen, and Van Durk, who's presented at APEC as well. And I'm curious if some of the stuff Greener has mentioned also might relate to this. And so we can ask the question, we hear this term scalar waves, longitudinal modes, it kind of gets thrown around and is used on the internet in a lot of different ways. And so we want to kind of clarify that. So if we discuss the polarization of an electric field, that refers to the direction of the electric field, or also the direction of the potential A. So if you have a transverse electromagnetic wave, it could be linearly polarized in the X or the Y direction, assuming the wave is traversing in the Z direction. So the polarization vector, if it's in the X, you have X, Y, Z. Oh, this is actually, sorry, that should be 0, 1, a little typo here. So this polarization vector would point in the X direction. This polarization vector would point in the Y direction. That should be in the third component here. And then if you had a longitudinal polarization vector, it would point in the Z direction. And finally, if you had a scalar mode, it would be in that time-like component here. So you could have a transverse wave that is traveling in the Z direction, but the electric field itself points in the X direction. Or you could have a longitudinal mode that's traveling in the Z and goes in the Z direction. And so this is just depicting a transverse electromagnetic wave. You have the wave traveling in the Z direction. The electric field could point in the X direction, and the magnetic field could point in the Y direction. You could also have circularly polarized waves. So the electric field would kind of rotate around like a helix in that way. Or you could have longitudinal modes. So you can imagine the electric field lines pointing outward in this direction, and you could have this longitudinal disturbance propagating that way. So we'll dive into those solutions a little more. But so now we can go into 4 vectors, which allows for a manifestly relativistic formulation. So we can take the scalar potential and the vector potential and throw it in this quantity A mu, which this index runs from 0, 1, 2, and 3. And then similar with the charge density in the current 3 vector, we can put it in a current 4 vector. And this really allows for an elegant representation of Maxwell's theory, because we can write down this action in terms of F mu nu, which is the field strength, which takes this antisymmetric derivative of A mu, where now you have this partial mu that contains the time derivative as well as that gradient 3 vector that I described before. And so if you notice this 2 tensor, it has 2 indices, so it's a 2 tensor. It's antisymmetric because if you look here, we have EX, but then you have minus EX. And then if it's antisymmetric, the diagonal has to be 0. And so you see here, you have minus BZ, but on the other side, it's plus BZ. So it's antisymmetric once again. And you can also add in this term. And so you can derive Maxwell's equations from the Euler-Lagrange equations, which is conveniently expressed in this way. And you can also represent it in terms of the potential. We'll get this D'Alembert operator here. But you get this extra term. And so the full set of Maxwell's equation also includes this Bianchi identity. So this is actually mathematically true. You can if you just plug in the value for the derivatives in terms of A mu, you can actually calculate that it is identically 0. So that's Maxwell's theory rewritten in terms of 4 vectors. And so it's also worth pointing out that there's this notion of a gauge transformation. So the idea is you can shift A mu. And originally, it's worth pointing out, historically, people thought that E and B, or that F mu nu, was where all the physics is. But then once quantum electrodynamics came around, they realized that A mu was the physical quantity. But they still believed that the physics of E and B traced back to A mu was most important. So they said that up to gauge transformations, you're not changing any of the physics, but still A mu is the physical quantity, which is subtle and confusing. So the idea is you can shift a mu to some other a mu. This partial mu epsilon is just the delta a mu term. Sorry. So it should be a mu plus partial mu epsilon. And so that's the gauge transformation. And so you could be in the Coulomb gauge, which has this constraint, or you could be in the Lorentz gauge, which has a different constraint. And so the Lorentz gauge is thought to be where energy and momentum is localized. But there's this other thing you can do in the Feynman gauge where it's called gauge fixing. So you can basically add terms to your Lagrangian and gauge fix them in a certain way. And when you do this gauge fixing, you can basically simplify the equations of motion. So in the Lorentz gauge, this term is already 0. So if you remember the equations of motion, there was this additional term. I can just show you real quick. So there's this box a nu, but then there was this d nu of partial mu a nu. But if partial mu a mu is 0 in the Lorentz gauge, that term drops out. So you get this equation. So Feynman was really careful about how he worded this, but he was pointing out, well, it's kind of nice to gauge fix such that you always get this a wave equation, even if this is not 0. So in the Feynman gauge, this was only 0 on average. And so that it leads to some subtle interpretations there. And really, most people just kind of refer to the math, and it's not really the precise interpretation isn't really like clearly stated a lot of times. So it's worth pointing out that you can get those equations of motion and then put them back in the 3-vector formulation. And when you do that, you can get this Lorentz scalar is what I call it. And so a bunch of people have studied this equation and called it like generalized Maxwell's equations, but it's also worth clarifying that, Feynman discussed this. So it's not like there are these obscure, unpopular authors who have discussed this. This is some serious stuff here. And so you get these 2 additional terms that get added, where one involves a time derivative of this scalar, electric scalar, and another involves a gradient of that electric scalar. And so there's a few people who've discussed this. Another one includes this Peter Michael Jack, who discussed it. And basically, he showed how that electroscalar can be used to give a notion of thermal electricity, provided that you assume that that electric scalar depends on the temperature. And so that was something that I was studying about 10 years ago. And so typically in thermoelectricity, you just write down Maxwell's equations, and then people discovered these different thermoelectric effects, and then they just develop equations for that, and they just kind of add it in. So this formulation allows you to it doesn't give you any new physics. We've understood the theory for thermoelectricity, but this sort of provides a fundamental framework to get the equations of motion from an action principle. And so this is the reference for it. And he never published it, so it was overlooked by a lot of people. And then someone else plagiarized it, which is kind of annoying when I showed the reference to someone. So I kind of left it aside back then because I didn't really feel like dealing with that controversy. And so at that time, I was trying to argue that it's kind of within the scope of Heaviside's generalization, because Heaviside actually had a comment where he said the ether can include thermoelectric effects. So at that time, I was basically trying to say, well, what if the ether exists only in non-equilibrium thermodynamics? Then maybe we can sort of get access to those longitudinal modes, just to kind of not say something too radical. And so Aharonov and Bohm also discussed that theory, and they said that they didn't really take the Feynman gauge. So they ended up saying some strange things like, well, it would violate charge conservation because it's breaking the gauge symmetry. And they kind of argued that it wouldn't be a problem if space-time was granular or discrete. So as if it could be charge could be violated on a small scale, which also probably is somewhat self-consistent with the Feynman gauge, but they didn't really look at it in exactly the same way. So in 2003, Wasser and Van Vlanderen wrote down this solution that involves this electric scalar and this vector. There's a small chance I'm off by a minus sign or something here, but I just put these together very recently. So it's in this this paper. Oh, maybe they had a couple papers. They talked about 2001 and 2003. I believe they followed up again. So this is a solution of those off-shell equations, and it propagates into the far zone. So typically we'll hear in academia that you can have longitudinal modes, but only in the near zone. So it's curious to understand, well, do these longitudinal modes exist? Yes or no? There's at least some mathematical theory that you can discuss that allows these to propagate to infinity, but that math doesn't really mean that they're there. We have to go to experiment to decide. Also, just briefly mention that Richard Bendirk has also discussed these equations. I haven't had the time to really, I've skimmed his papers, but I haven't really given an exhaustive review. So If any of you guys have more information about what he did, please reach out to me, because I'm curious to learn more about what he was doing and how he's looking at it. So there are claims in the literature of experimental evidence. There's this paper from Monstein and Wesley who claim to observe these modes. And also, as I was mentioning, there's this textbook from Zohuri. He claimed that the Navy sent these signals. And I just looked, apparently it was retracted by the publisher. Not too surprising. Honestly, the textbook, it had a lot of good mathematics, but it kind of was, it was giving too much credit. It was really just citing all these obscure works on the internet, like Tom Bearden and different people, and just kind of assuming that everyone on the internet was talking about it was correct. And so there's some kind of contradictions in his textbook where he actually presented two different theories, and he wasn't really clear on what how to actually describe them. Another experiment that I noticed was this they measured 3 qubits per photon. So typically they thought that since the electromagnetic field is thought to only have, the photon is only have 2 physical degrees of freedom, they only thought they could get 2 qubits per photon, but they were able to find a way that used the third, that got a 3rd degree of freedom, which kind of surprised them. And when you look into it, the 3rd degree of freedom had something to do with looking along the direction of propagation. So it's a little cryptic to really figure out the mathematics and how to connect it to Maxwell's equation from what they observed, but it's possible that it could relate to this longitudinal mode. So maybe there is actually some physical information that has been overlooked and has been experimentally found. I also mentioned that Giovanni Modenese has also discussed this notion of charge conservation violation. I personally am trying to find a way where we don't think of it as being charge conservation being violated. One idea is that maybe there is this ether that allows for bound charge in the ether itself, and then you could add that bound charge. Basically, that electroscalar, you could subtract it to the other side of the equations and interpret it as a bound charge, and maybe that'll help figure out the conservation laws. So what do we make of all these claims from Tom Bearden? Because I admit that I took inspiration from him, but I kind of ignored all his math and wanted to verify these claims by going to the experts and looking at the history. So basically, Bearden got a lot of the details of Maxwell's contributions wrong, and this idea of quaternions and the value of them is wrong. But it's curious because the quaternions can be used to very naturally get that off-shell equations of motion that add that scalar term. So there's a chance that Bearden was kind of briefly looking through the internet, finding all these sources, and kind of assumed that the newer equations were actually studied in Maxwell's treatise, even though they weren't. So it's kind of curious. But the other thing is Bearden also got me to look into these Whittaker potentials, and then I realized they're contain the same information in these Hertz potentials, which is curious. So let's dive into that a little bit. So what are these things? Well, they're kind of pre-potentials or potentials of the potentials, because the electromagnetic potential, you take a derivative of that to get the electric and magnetic field. Well, with these pre-potentials, you take a derivative of those and they give you the electromagnetic potential. And what Whittaker pointed out is that the solutions of them are determined by the positions of the charges alone, not the velocities or the acceleration. So if you're thinking of this medium with these material-like properties, you should be able to refer to the position of some particle and have it move around. And if there is some electrodynamic variables that are in terms of the positions of the charges alone, then maybe that's talking about some of the material properties of this medium. So I'm playing with the idea that these are in some sense types of ether potentials. And so there are these Hertz potentials as well. They were partially introduced by Hertz in 1889. And it's really funny because he just thought they were mathematical. He didn't think there were these physical things, but we know his interpretation was wrong because he also thought that E and B was physical. And so once again, derivatives lead to the potential. And so he used them to discuss dipoles, and basically the Aharonov and Bohm really ushered in this idea that the electromagnetic potential is what's physical, not E and B. So it's also curious, maybe they'll be useful for studying complex media because there's issues with trying to understand how to synchronize things at times. And so if we have electromagnetic variables that are in terms of the positions, then maybe that'll help with synchronization, because if we take a derivative, you'll lose track of the position to some degree, and maybe that makes it harder to calibrate things. So Keith Wanser mentioned that it might be helpful for that. And so here's the mathematics for it in terms of the 3-vector formulation from Stratton's 1941 textbook. And so we have these 2 3 vectors, pi e and pi m. So you can kind of think of them as sort of being similar, mathematically similar to the electric and magnetic field, where you have a 3 vector and a 3 vector. And except now we have a time derivative of this electric Hertz potential and then a curl of the magnetic. And then you can also add this other scalar field. This turns out to be related to the third Whittaker scalar potential there. And it's also related to the gauge transformations. So if that gauge transformation actually contains some physical information, I don't know. But if it does, then maybe you could attribute some physics to this. So a lot of times these psi terms are dropped out because they're thought to be unphysical. And so then another thing you can do is similar to F mu nu absorbing the electric 3 vector and the magnetic 3 vector. You can take the 2 Hertz vectors and then embed them in this antisymmetric 2 tensor, which I'll call pi mu nu. And then if you take a derivative of that, you get a mu. So then if you look at F mu nu, you can solve for what it is in terms of pi. And then we can also claim that there are these stream potentials such that when you take a derivative of that, it leads to j mu. And if you do that, you get this wave equation here where the stream potentials are sources for the Hertz potentials. So that's kind of a curious thing that is often lost in history. Those stream potentials there's not that many people discussing them, but they've been around, I believe, since 1923 they're introduced. And so there's also this higher gauge symmetry of the Hertz potentials, which is very rich mathematics. I'm not going to go into the details, but here's the reference. I guess it was, maybe he wrote it in 1954 and published it by 1955. And what's really curious is the string theorists rediscovered this mathematics, but they have no idea that it was already done in the 50s. So they end up using it for gravity and they call it 2-form electrodynamics, but then don't claim it's related to electrodynamics and believe it's a part of their gravitational sector. So it's pretty funny that essentially what I'm claiming is that the string theorists kind of rediscovered these ether potentials, if you will. And so here are the solutions of the Whittaker potentials. There's 3 scalar quantities. They're not Lorentz scalars. They're just real numbers. So that's another confusing point. And he called them F and G. I just gave him the subscripts psi d and psi h. And so they're in terms of solutions of the charges. So if you have a bunch of electrons or point charges, you can sum over all those charges. And then basically you end up using the bar is basically a time retarded time. So that charge would be at some position, xi, let's say. And then if you're at some other location at x, you could wait for the signal to reach you and take the speed of light. So you'd have to take the time retarded position or look at the position. If it was a light year away, you'd look basically where it was a year ago and then propagate that forward to take that position. And then so all of the solutions are in terms of those positions. And so this one was referred to be gauge redundant, but it turns out if you have these longitudinal modes, then this one relates to those longitudinal modes. And so you can basically figure out what phi and A are in terms of these Whittaker potentials. And Whittaker also used D and H rather than E and B. So if you were taking his work, once again, Whittaker was interested in the ether. He wrote another book called The History of Ether Theory. So when we transitioned from Maxwell's theory in terms of this ether to the modern era, what used to be called the free charge is now the total charge. Because if you just didn't have macroscopic media, you would say there's free charges in space and maybe there could be some bound charge in the ether because that's a medium. But now we say, well, no, there is no ether, so there's no bound charge in the ether. So now what Whittaker was calling the free charge is now the total charge. So that's another one of those subtle things with the interpretation that we can go back in the history and see, is there a way to retain that interpretation and bring it forward? And so now if you look at the Hertz potentials versus the Whittaker potentials, they're essentially the same thing. You can basically put the Whittaker scalar in this 3 vector and then realize that this 3 vector is the same thing as the electric Hertz vector. And then if you do the same thing with this psi h, you get this 3 vector, which is proportional to pi m. And so I think Bearden and them got obsessed with this notion of O3 electrodynamics because they saw this 3-dimensional rotational symmetry of the Whittaker potentials. But once again, if you look at the work of Nisbet, it's actually understand that there's this higher gauge symmetry, which is a Lorentzian symmetry. It's a special relativistic type of thing, with SO3-1, not SO3 or O3. So, I mean, really the key is that, yes, there's a 3 vector here, but there's 2 3 vectors. And just like you have the electric vector and the magnetic vector field, those can be combined into a field strength that is, that's the Lorentz covariant formulation in terms of 4 vectors. So I think Bearden was confused on that point, and his collaborators as well, in my opinion. And so there was that experiment with 3 qubits for photon I was talking about. That's curious. And so that if you were working in terms of Whittaker's notations, instead of an E naught as a scalar field strength, you'd get this D naught as a scalar field strength. And that would relate to that third Whittaker potential, which is, yeah, I guess there is this CIA document that was released that mentioned this point. Actually, I thought I figured that out. But yeah, fair enough. So people have discussed it. And then, so you can actually use the biquaternions to formulate all of the Hertz and Whittaker potentials, and then use these different operators that I probably didn't really explain in enough detail. But you can use the biquaternions. Oh, that's the complex quaternions. I kind of left out some slides going through that, but you can use the complex quaternions to get Maxwell's equations with that scalar field equation in a very natural way. So you can, it's very natural actually to get representations of the Lorentz group with the biquaternions or complex quaternions. So I'll just briefly mention that you can add magnetic monopoles, which is something that Maxwell did in his treatise, but he didn't really add this magnetic current. So that's why Maxwell's treatise added these, but he didn't really study the full theory. And so Stratton pointed out that he didn't consider magnetic monopoles, but he showed that there's this other solution in terms of another scalar potential and another vector potential that you can add in, and these are valid solutions. And so typically we send these to 0, but by the 1960s, it was also realized that this theory was kind of rediscovered when studying magnetic monopoles. And I noticed that Konstantin Meil, who's done a lot of experiments claiming there's scalar waves, he says there's 2 scalar waves. There's this electric scalar wave and this magnetic one. So, but then he does this strange thing where I basically in my opinion, all of his mathematics is wrong. I mean, maybe some of it's okay, but a lot of what he does is incorrect. And so he says, oh, well, since we have these magnetic monopoles, we have to reject the vector fields and focus on, I don't know, some scalars with vortices, and it goes off. But he really overlooked the history and the mathematical details. No, what it means is there's 2 vector fields, not 0. So you can have 2 vector fields, and this is described back in 1941, but it's often overlooked. And so another thing I noticed, well, if we wanted that magnetic scalar wave, then you can go into the complex quaternions and consider an 8-dimensional Hertz-Whittaker potential, and you can get basically that third Whittaker potential. If you make it complex, the imaginary part would be some psi1, and that would correspond to some, you could think of it as a 4 divergence of that 4 vector field. So you have A mu, and now there's this Z mu that has that, the chi and this Z vector here. We put that into a 4 vector, and now we get this new magnetic scalar field strength that I haven't really seen anyone discuss. Maybe there's, Michael Perron might have found a textbook, but certainly not described in terms of that Whittaker potential right there. So it's not really the main point of my talk here, but I just want to kind of briefly summarize this this electrodynamic framework where we could think about the vacuum being a medium. So maybe that would imply that those macroscopic formulation might actually apply to the microscopic. That's one idea. And so that's either true or false, right? We could ask the question, do longitudinal modes propagate to infinity? Yes or no? That's a Boolean. And we can ask, are these magnetic monopoles real? Well, there is actually topological insulators effectively have magnetic monopoles as mirror charges of electric monopoles. So depending on how you interpret that, are they real? Are they physical or not? Well, certainly the mathematics is useful for topological insulators, it seems. So that's another yes or no question. And then finally, we can ask the question, are these Hertz or Whittaker potentials, are they physical? Is there some experiment that we can do that similar to what Aharonov and Bohm did? Is there some deeper way we can look at electromagnetism and measure something even more subtle than what Aharonov and Bohm were suggesting, and find that maybe when A mu is 0, maybe the Hertz potentials are non-zero, and does that actually matter for physics? So that's another yes or no possibility. So I'm basically trying to look at this framework of 16 different theories of electrodynamics and then start to go into the experiment, because at the end of the day, you know, I can't really just study theory to determine which one of these theories is correct. They all look beautiful to me. It's just that at the end of the day, experiment decides what is real. So let's see, do I have time, or do I have the space to talk about gravity? Well, I'll dive into it. So basically, Einstein introduced general relativity in 1915. This included this metric tensor, which then led to the Levi-Civita connection that can be derived from the metric. And then there's this Riemann curvature tensor that is used with the Ricci tensor and Ricci scalar in Einstein's field equation. So the metric helps define infinitesimal lengths and time intervals in this way. So dx mu is an infinitesimal length. It's typically a symmetric tensor because if it was non-symmetric in this equation, it wouldn't really matter because this part's symmetric, so the anti-symmetric part would drop out. Just keep that in mind as we go into unification later. So the metric varies over space-time, so it's a function of space-time. And the action principle varies the action with respect to the metric. For instance, this is how you define the stress energy momentum tensor that sources gravitational waves or gravitation. And so you can introduce this connection that allows for well-defined covariant derivatives such that you can get, well, I should say well-defined tensors that involve, that generalize the partial derivative. So depending on the number of indices you have on your tensor, you'll have that many extra terms in terms of the covariant derivative. This vector is a one tensor, so there's one additional term with the Levi-Civita connection, or sometimes called Christoffel symbol. And so you can derive it in terms of the metric tensor in this way, just by taking a derivative. So yeah, that's curious. And then if you take the acceleration, you can get this geodesic equation. So this equation mathematically, it tells us how to parallel transport vectors around a manifold, but then the physical interpretation is you can say that the geometry of space-time in this connection is encoding how gravity is a fictitious force, because we usually say F equals ma from Newton's laws. And so if you just multiply this equation by the mass and you subtract this to the other side of the equation, it appears as if it's a gravitational force, but it's really encoded in the geometry itself, so it's fictitious. And so we can define the curvature tensor for arbitrary connections. You always define the curvature tensor in this way. And here's like an intuitive way to interpret what that means. So if you started with some vector here, you could basically parallel transport it around some infinitesimal loop. So you go from P to Q, where there's some infinitesimal distance there. You go from Q to R. And then you compare that. If you go to P to S and S to R, you'd expect typically if everything was flat, the two vectors would land on the same spot. So you could have this, let's think of it as a partial rho going this way, and then a partial rho prime from going that way. And the difference in those two vectors is used to characterize the curvature. So it is a 4 tensor specifically because we have the area that we're going around, which counts for 2 of the indices, this partial mu, partial nu. And then there's the initial vector that you have. That's another index. And then there's the final rotation that you get from those 2 vectors. That's another index. So that kind of geometrically, intuitively describes why the curvature tensor is a 4 tensor. And so you can then find this Ricci 2 tensor that contracts indices from the Riemann 4 tensor. And that's what it is mathematically. And then you can use the inverse metric to get the Ricci scalar, which is this quantity right here. And that goes in the Einstein-Hilbert action. And you can derive Einstein's field equations right here. And so you can also study linearized gravity, which has the idea is you have the Minkowski metric as a background, and then you perturb around that background metric. You can actually use any metric, but it's often convenient to use the Minkowski metric because you naturally think of if gravity is weak in the limit of 0 gravity, you get back to Minkowski spacetime. Or you could also study being around black holes, take a black hole solution, and then study perturbations around that. And so you have this gravitational field h mu nu with some coupling constant kappa that relates to Newton's gravitational constant, has the speed of light in there as well. And it turns out that the trace reversed metric, this quantity right here, is useful for the equations of motion. And there's this thing called the de Donder gauge that's basically the gravitational analog of the Lorentz gauge that leads to this nice simple equation of motion where the stress energy momentum tensor is the source for the trace reversed metric. And this de Donder gauge is a derivative of that trace reverse metric equaling to 0. Whereas if you remember the Lorentz gauge, that was a partial mu, a mu was equaling 0. I mean, now we have an additional index, but still it's the same idea. So we can gauge fix linearized gravity just like QED. And that was originally also discussed by Feynman and other people because people are interested in studying perturbative quantum gravity. So this was one way to look at it. But it's really worth pointing out that this perturbation theory, this expansion I'm talking about, you can go into the quantum theory, but also you can just study the classical theory. And so the desire to study quantum theory kind of obscured a lot of the facts about classical gravity itself because they were so interested in obtaining quantum gravity. And so just really to drive this point home, so there's this post-Minkowskian expansion, which goes to arbitrary higher orders rather than that linear order for linearized gravity. So in the post-Minkowskian expansion, linearized gravity is basically the lowest order. And then you can go to higher order, and basically that will eventually converge on the full theory of general relativity, which is a classical theory. And so this is very subtle. It's very hard to find this in any papers really mentioned. I heard a graduate student tell it to me once, and I even tried to find it in textbooks, and I couldn't find it. But through the research that I personally did, it just became very obvious that this is true. Basically, classical general relativity contains virtual particles. So these virtual particles are not necessarily quantum information. This is often stated that, oh, the virtual particles, it's all this quantum weirdness. And, so people that hate quantum field theory, they hate these virtual particles. And it's just really worth pointing out that this, you get perturbation theory, which is basically like a Taylor expansion in this post-Minkowskian approximation, and it includes these virtual modes. So you can get loop diagrams, you can get Feynman diagrams with loop terms, and in QED, those loops would be associated with quantum corrections. But since gravity, general relativity is a nonlinear theory, and linearized gravity is linear, those higher order terms introduce successive nonlinearities, and those nonlinearities relate to these loop diagrams, but it's just a classical theory. So once again, these virtual particles in general relativity are there as classical objects, and you can have gravitational waves that are longitudinal in principle, just like we discussed with the gauge fixing, except it's still maybe classical in some sense, but virtual. And so what if you used a different gauge, right? Just as Feynman discussed, you could gauge fix in a different way. You don't have to go to the Lorentz gauge here. You don't have to go to the de Donder gauge. So you could gauge fix linearized gravity or the post-Minkowskian expansion. And there's a bunch of different ways you can gauge fix general relativity. It's a very interesting topic. And this notion of technically you can have transverse waves, transverse longitudinal, and longitudinal waves. This was even pointed out by Eddington back in 1922. And so there is the mathematics is there to study longitudinal gravitational waves. And so now we discussed longitudinal electromagnetic, longitudinal gravitational waves. Now I want to dive into unification with hopefully I'll probably go over I probably have another 15, 20 minutes left. Sorry for going over. And so general relativity has this metric, a connection, and a curvature. And after reflecting upon unification for a few years, I've realized at a geometric level, there's three ways you could think about unifying electromagnetism and gravity at the mathematical level. Because Einstein, he actually tried to take the electric and magnetic fields and combine them with the potential. And then there was Kaluza and Klein, actually slightly before Einstein. They looked at considering the electromagnetic potential, A mu, and unifying that with the metric by going to an extra dimension, going to the fifth dimension. And that's a different geometric alignment because the electric and magnetic fields are a derivative of the potential. But what's kind of the most obscure option is to think of these Hertz potentials and unifying that with the metric. It's geometrically aligned with what Weil did in 1919, but I don't think Weil looked at the Hertz potentials. He mainly looked at the potential, the electromagnetic potential, as being a connection. And also there's this Wu-Yang dictionary once Yang-Mills theory came along. It's understood how the connection is like a gauge field and the curvature is like a field strength. So then what's like the metric? Well, naturally it would be the Hertz potentials, but this is largely overlooked. No one's ever even discussed non-abelian Hertz potentials for Yang-Mills theory for the standard model. So there's just a lot of mathematics that needs to be developed. Well, I have some handwritten notes on it, but nothing's been published yet. So the string theorists study some of this math of the Hertz potentials, but they don't look at it as actually being electrodynamics, which is hilarious. So now I'm going to dive into just a lightning review of some of Einstein's attempts at unification. And as I was saying, he considered this non-symmetric metric. So this the parentheses here mean take the symmetric part. So now this G mu nu is different than the typical G mu nu because it adds this field strength, this anti-symmetric tensor that I kept harping was anti-symmetric. That gets added to the symmetric part to make this non-symmetric metric tensor. And then he used the non-symmetric metric tensor in here, and he basically claimed that he could get Maxwell's equations, or at least half of Maxwell's equations. He got the one where it's sourced by J mu, and you get the partial derivative of F mu nu, but he missed the Bianchi identity. And so he wrote about it in German in 1925, and I believe Unzicker and Case has a paper that translated it to English. It's in here. They translated a few papers. And so along the way, Einstein started to expand his theory or look at it in different ways. He had a bunch of different slight modifications. A pivotal point was when the frame field or tetrad or Vierbein was introduced, because the Dirac spinner came out in 1928. So Einstein wanted to study the Dirac spinner in curved spacetime and realized he needed this frame field, and that's translated to English in this paper by Yepes right here. And so that's curious. And then so through the 1929 to 1930s, he started exploring other theories that are very similar but use that frame field, and thought of that as being the 16 component object rather than the metric as being non-symmetric. Maybe you had the metric still non-symmetric, but it provides deeper mathematics to look at the metric tensor. And so he still didn't have a Bianchi identity. And finally, by 1929, Lankos wrote a letter to Einstein saying at least one of these theories at this point was merely a theory of gravity. And that's reported in this historical paper here. And so now that theory that Einstein was looking at is called the metric teleparallel equivalent theory to general relativity. It doesn't have electrodynamics. It's just a theory that has torsion. And so that was another thing. Einstein sort of rediscovered torsion through the non-symmetric tensor. And part of the clarification was Cartan was saying, hey, look, I already invented this geometry that you want, that's torsion. And now we also understand how the frame field is kind of like the gauge field for torsion. So really, it's great that both Cartan and Einstein did those works, because now we have a more complete picture of what's going on there. And so eventually Einstein abandoned those earlier attempts. Through the 1930s, he tried a bunch of other wild modifications for unification that were pretty complicated and messy. Finally, by 1945, he returned to this idea of a non-symmetric tensor. He was also playing with the idea of making the anti-symmetric part imaginary. And then he published another paper with Strauss. Eventually, that theory was abandoned because they couldn't find any spherically symmetric charged particle solutions. And by 1954, it was proven that those solutions are not in that theory. And then there's claims of that attempt being fixed as well. So there's this paper from Kirsanoglu and Bonner who discussed this slight modification, and they claimed it had all these great successes for making Einstein's field theory, that dream, being valid. But this kind of largely got overlooked because by this time, Yang-Mills theory was starting to come into play, and we're starting to understand there's other forces of nature. So that even this idea of unifying gravity and electrodynamics we started to realize that's not the full picture anyways. Also, the variational principle, it's not really, they used a non-symmetric metric, but if you combine the field strength, that F mu nu, with the metric, then you're not really doing true variational calculus with respect to that full non-symmetric metric. So in my sense, it's not really a truly fully unified theory in a sense, because it's kind of just a hack to get Maxwell's equations to come out in a convenient way. And so then eventually other people started discussing this theory. I don't know why exactly, but I guess they started saying, well, what if this mathematics is correct, but it has nothing to do with electrodynamics, since Einstein couldn't figure it out? Maybe there's just some additional gravity that is modeled with this non-symmetric metric. So Moffat looked at it around 1975, and also the Kalb-Ramon axion introduced that concept. And also string theory, it's in string theory in the closed string. So these three paths to unification that I'm talking about, there's the attempts from Einstein by looking at F mu nu. Then there's the electromagnetic potential. I'm not going to review Kaluza-Klein theory. And then finally, this new path is using the Hertz potentials, which is more geometrically aligned, because we can have a curvature as a two form in terms of differential geometry. Sorry for this elegant presentation of the geometry. It's a little confusing, but basically that curvature is now understood to be a Yang-Mills field strength, which is kind of like a generalization of the electric and the magnetic field. And the connection as this one form is basically the same thing as a gauge field, which is a generalization of the electromagnetic potential now given this non-abelian index
for the other forces. But where's the metric? No one's really ever pointed out anything like the metric. And so let's just let's dive in. Let's compare linearized gravity with the Hertz potentials. Right away, the equations of motion, they look identical. This tensor right here is symmetric. This tensor right here is anti-symmetric. So this one's symmetric, that one's anti-symmetric. So right away, we can just add these two equations of motion together to get some non-symmetric metric tensor. And great, we could get this, this theory. So you can imagine this metric now having some perturbation around a background because we're still in linearized gravity. And it would have some symmetric part here and some anti-symmetric part. And then we could just throw the stream potentials into the the anti-symmetric part of some stress tensor. So here's some non-symmetric stress tensor here. And this theory would work just fine. But it's really just a cute little theory because it's just getting linearized gravity. There's a lot of known effects that require the nonlinear theory. So it's pretty straightforward to see how this will work. It's a lot more difficult to get it to work with the nonlinear theory. This took me a while to really figure out, and it ended up working out way more simpler than I was expecting as well. So now we're going to consider a non-symmetric metric with Hertz potentials as the anti-symmetric component. I'm going to put this little circle over the top to represent the symmetric part. And the thing that I realized is, there's the connection of the first kind or the second kind. The first kind has all of the indices lower, so you do not need an inverse metric. You can define it just in terms of the metric. The inverse metric has the indices upstairs, whereas the metric has the indices downstairs. So the connection of the first kind is written in this way, and I'm going to use the full non-symmetric tensor here in this connection of the first kind, which is then going to lead to non-Riemannian geometry. But I'm going to use the symmetric part alone to raise and lower indices. And this was something that Einstein didn't try to do. Einstein tried to use the full non-symmetric metric to raise and lower indices. So this is another subtle difference that I'm going to do from Einstein using the Hertz potentials. And then the connection of the second kind with this first index raised, I'm then going to use the symmetric metric. And then you get, this is the Levi-Civita connection, which I have the little circle over. The circle, when it's over that, that's always reducing back to the general relativity theory. And then you get this additional term, which is called the contortion, which stems from torsion. So the contortion tensor is basically what you add or subtract depending on your conventions. You'll find it in the literature either way. There might be a plus or minus sign here. So if you add or subtract that from the Levi-Civita connection, you can get a more general connection. And it's always difficult to remember how to formulate the contortion tensor. So if everyone wants to shout and bracket, not all at once now, but that's the way I remember it. So there's this shout and bracket that allows you to determine, basically you just follow what is done with the Levi-Civita connection with the indices there. And if you do the same trick with the indices with the torsion tensor, that will give you the contortion tensor. And it turns out that if you look at this connection of the first kind and you plug it in, you reduce into the symmetric part of the metric, which would go in here, and then the anti-symmetric part, it would go over here. And then since these Hertz potentials are anti-symmetric, we can kind of split it into two terms where you take minus sign and you switch it that way. And then you get this explosion of terms here. And it turns out that this quantity right here, you can think of as being the completely anti-symmetric combination of all these indices with a derivative acting on this. And then you'll find that this H tensor is proportional to the contortion. And then what you can do is look at this non-Riemannian Ricci tensor that contracts the indices of this non-Riemannian curvature tensor. And then from there, you get the Riemannian curvature tensor here with these additional terms that involve the contortion. And then we could use the symmetric metric to contract right here. And we're going to get the Ricci scalar. But then we get this additional term here. And it turns out that this is actually this two-form electrodynamics theory. So if we put this in a Lagrangian, if we consider this as our Lagrangian, we're going to get Einstein's field equations plus two-form electrodynamics. And that ends up giving the field equations for the Hertz potentials. And then if you take that Hertz potential field equation, we can then derive Maxwell's equations from there. So it was really clever to see how that was able to come out. And so there's another trick that you can do where you could use the non-symmetric tensor here, I'm not going to show the full details here. I'm still trying to work it out, but there's a chance that we might actually be able to get the sources as well from adding in the Hertz potentials there, but we'll see how that works out. And so basically the point is you can get the equations of motion for general relativity and the Hertz potentials from that framework, which is just a couple small tweaks to what Einstein was attempting. And so now we can ask, what about these longitudinal modes in the unified field theory? We could add the third Whittaker potential to the Hertz potentials, and it turns out that that would go to the trace, because the Hertz potentials had 6 components in the anti-symmetric component. So if we add another degree of freedom for that third Whittaker potential, it turns out it's going to go to the trace, which is part of the symmetric piece. But the symmetric piece was part of gravity, right? So this is where the interpretation starts to get kind of curious and interesting. So another more sophisticated way, if you take an arbitrary 2 tensor, you can actually break it down into 3 pieces. Well, first you could break it into the symmetric and the anti-symmetric part. But the symmetric part, you can think of it as a symmetric traceless plus a trace term. And so the longitudinal electromagnetic, or that electric longitudinal mode, would go to the trace term here. And by string theorists, they'll call the symmetric traceless, they'll call that the graviton, they'll call the trace the dilaton, and they'll call the anti-symmetric piece the axion, or Kalber-Moen axion. And they understand how this is related to torsion. Actually, experts will know that that's related to non-metricity as well in a way, or at least in string theory that was derived, that the dilaton induces non-metricity. So it appears as if this longitudinal electroscalar mode appears as a dilaton, which is curious. And if you study gravitational waves, the theory that gets used for LIGO, they'll always talk about this transverse traceless gauge. So it's already common to take these gauges to remove the longitudinal gravitational modes, just like you do in electrodynamics. But as I was describing, you could do some gauge fixing and include longitudinal gravitational modes. But now the interpretation is a little subtle, because we can add these longitudinal modes. And if we're claiming that the anti-symmetric part is of the metric is electromagnetism and the symmetric part is gravity, well, then that longitudinal electromagnetic mode now appears mathematically equivalent to a longitudinal gravitational mode. So what's coming out of this theory is it's suggesting that maybe we can associate longitudinal electromagnetic modes as being somewhat indistinguishable from longitudinal gravitational modes. And at the same time, what's good about this theory is that it's not predicting that the transverse electromagnetic modes are the same thing as the transverse gravitational modes, because clearly we can send radio waves, and that's different than what LIGO is detecting. LIGO is claiming to measure transverse gravitational waves, which is completely different than radio waves. So in this sense, it's very much in line with what Einstein was promoting, but it slightly sounds like Tesla, because what's going on? There's this notion of these longitudinal modes being gravitational, but secretly coming from electrodynamics, which was what Tesla was talking about. And then we can think harder about, well, what is Earth's gravity and what is electrostatics? And some might even say, I think if you ask ChatGPT or Claude, the AI, they'll say, oh, this is an alternative interpretation where if you think of Coulomb's law, it uses electrostatics, and basically you can think of that as being a longitudinal component. I mean, if you have a charged particle, it's going to emanate electric field lines radially outward, and it doesn't really carry momentum. But if you were to think of this, let's just say it carried an infinitesimal amount of momentum. The momentum would have to go radially outward. It's not going to, if it's spherically symmetric, that's the only direction momentum could go out. But that's also the same direction that the electric field lines are pointing, which is the direction of the polarization. So in some sense, you can think of Coulomb's law being a longitudinal mode. And similar with gravity, you can think of Newton's law, it's statics, it's gravitostatics. And you can think of that as almost being like an infinite wavelength. So you're in the near zone, and you can think of there being longitudinal modes in there. And so really you can think of Earth's gravitational field as being longitudinal gravity. And this is different than the gravitational waves predicted by LIGO and measured by LIGO, or predicted by Einstein's theory and measured by LIGO. So in this sense, it's obviously it's still very much in line of Einstein's general relativity and a slight tweak of his unification attempt. But maybe Tesla had a point after all, because he was talking about Earth's gravitational field. not gravitational waves. And he believed that there was something going on with the electrodynamics of longitudinal modes there. I mean, he refuted the idea that Hertzian waves were transverse. So I don't think he was completely correct there, but maybe Tesla had some partial truth in what he was saying, assuming this theory has some merit. So I then started talking with some other people in our community, and I got this kind of dream of what propulsion might relate, how we might be able to get after propulsion when I was talking to Jeremiah Popp. So he was describing this Keadian physics device, and we were just talking about how we have basically plasma in air, and then we're using ultrasound to oscillate the air, which is going to cause these longitudinal oscillations of the ions. And it's also known that plasma can have ions and can lead to longitudinal modes due to the nature of the ions being like a fluid. And so it's also worth noting that that sounds very similar to some of the ether models that were considered, but now we're looking in physical macroscopic media where you have air. And so the strong magnetic fields are causing these ions, the positive ions will go radially outward or inward, and then the negatively charged ions will go in the other direction. So you get this cylindrical capacitor as well as this longitudinal motion. And then maybe you're getting some longitudinal electromagnetic modes that were actually somehow indistinguishable from gravity. I mean, it's just kind of a dream right now, a little bit of a speculation, too early to say for sure, but who knows if it turns out that some of these experiments that we're playing with lead to something that we can reproduce in the lab in a reliable way. We're going to need some explanation. So this is at least something we could throw on the table as a possibility. Certainly too early to say. And so there's also been this notion of the graviflyer studied by Charles Crawford III and Jared Yates have been reproducing a lot of their effects as well. Also kind of seems vaguely similar to the Hutchinson effect in a few ways. And so assuming it's not a hoax, we don't really know exactly if we can reproduce this lift. But if we did, I mean, it still could just be due to electrostatics. I should point that out. Maybe it has nothing to do with gravity whatsoever. But once again, what we're trying to point out is that in this unified field theory, it might turn out that electrostatics inherently has this longitudinal component that might be interpretable as being effectively gravity in some sense. So who knows? Another thing I want to point out, Todd Desiato had this interesting idea. I was already thinking of the ions flowing in between there and going oscillating longitudinally, but then he really drove home this point where what if they're flowing in a torus as well when you zoom out a little bit, and that would be the only way to conserve momentum where you could get the thing to lift. So I just thought that was a really curious observation. And Alexei also pointed out there was some notion of a torus there as well. And I'll also just briefly mention that Mar Sokol has been hard at work looking at the Alzaphon experiment with DNO. And it's plausible that we don't truly understand the origin of mass. There's been some work by David Hestenes, who's looked at Zitterbewegung, and he's looked at this helical model of the electron, where when it moves along the helix, it's actually traveling at the speed of light, the electron. And so it's massless. But then when you zoom out, if you can't see the helix, you just see it going in a straight line. And that straight line is now, it appears as if it's moving less than the speed of light. So basically the radius of that helix ends up being related to the mass. And another thing that's curious is it turns out that Hestenes and his final student, they tried to figure out if they could get the mass of the electron. It almost worked, but not quite yet. But another curious thing is I want to point out is that I found this obscure paper. I mean, I looked at it, instantly knew that torsion would be related to their construction because basically the spin density source is torsion, but now we're finding electrodynamics to also be torsion in this unified field theory. So who knows? It's understood that you can get mass renormalization in QED, and we know that in QED, the polarization of the vacuum can occur, which is essentially the ether according to Dirac. So as we go into this unified field theory, we might be able to understand at a deeper level some aspects of the renormalization of mass. And there's also this notion of a Cartan radius that's been studied, which relates to the mass. So that might even relate to that helical motion. So if it turns out that we're in this Alzaphon experiment, if it is leading to some gravitational effects, I mean, I think it's really important that we first rule out magnetic forces, because it's entirely possible that that could be what's happening there. But Mark was able to collect some data that did see a shift on the scale. So if it can be reproduced and we can rule out magnetic forces, then there has to be some explanation. And maybe it turns out there is some way to go into this and see how maybe there's something subtle with the spin and the electrodynamics of all of it that's leading to some effects on mass. And so finally, I also wanted to go into this notion of macroscopic media. So there's this elegant way to talk about macroscopic media. You can have this electromagnetic permittivity 4 tensor that also contains the magnetic permeability, but the inverse of it in a sense. And so if you have that F mu nu, you can get this G mu nu tensor, and this G is what contains D and H, which is sourced by the free charges. And you can also get the bound charges by this other susceptibility tensor. This would contain P and M. And this chi 4 tensor here would be the electromagnetic susceptibility 4 tensor. And Jack Sarfati has been interested in this. And if he's out there, I wanted to point out that we should study the Cartan-Weil formulation, not what's in Medina and Stephanie's paper, because we basically need the square root of G. I mean, he probably knows this, but in that paper, they don't really discuss the formulation that is nice for in curved spacetime. So if you use this tensor here, you end up getting that effect right there. And then you can formulate macroscopic Maxwell's equations in this way, which is quite elegant. And so last year, I was looking at the Sarfati-Windsor scalar, and because Jack kept trying to say that the electrodynamics was affecting the scalar that he was adding into Maxwell's equations. And so I was trying to tell him, well, I think you can generalize general relativity to study macroscopic media. And now Jack is now saying that he had these equations. I don't know. I don't want to get in a debate about it, but I mean, it was certainly what I was doing was well inspired by exactly what Jack was saying. He was saying we need to understand a theory of gravity inside of macroscopic media, not in vacuum. So let's just play the same game. We can introduce this 4 tensor and convert the Riemann 4 tensor into what I'm calling a digravitational tensor. It's still a 4 tensor, but we're going to use, we're just going to convert 2 of the indices. And there's a good motivation for why we want to do that. And so then we could contract again and get these Ricci digravitation tensors and scalars. And then we could introduce this notion of a free stress energy momentum tensor, where we could also have total stress energy momentum equal to the free plus bound stress. And so then we could have this new type of macroscopic theory for general relativity that Jack will probably talk about in one of his papers soon. We'll see how he formulates it. And you could have this free stress tensor as the source. So that's kind of curious. And then I also, speaking of dissipative media, because we can discuss these different types of media, Todd Desiato was looking at this polarizable vacuum for quite some time. And then he had this unique contribution, which was to consider gravity as damping. And so what would that mean? Well, you could have this electromagnetic medium, and there could be damping in the media. And this might not always be studied, because if there's damping going on, you'd have this dissipation of energy. And where would that energy go? You have to have energy conservation. So what I'm proposing is, if we look in this unified field theory, we could, and then you generalize it to macroscopic media, you could have basically the material effects from the gravity side that were just introduced, and the material effects of the electromagnetic media, and they could allow for energy to dissipate between the two media. So the gravitational medium isn't the same as the electrodynamic media, but they could crosstalk in some way. So that's another thing that I'm looking into. So not this type of media, but just physical media. So I also wanted to give a shout out to Michael Perrone, because he's been really encouraging me to pursue this theory further, or these theories, I should say. And in terms of the longitudinal modes, he's also been interested in the effective magnetic monopoles. We might be able to actually cook up some ionic wires in the laboratory, which means there's electric and magnetic monopoles. He's great at fabricating different materials. And another thing he keeps suggesting is that there could be this topological Tesla coil, which would be basically take a Tesla coil and basically put the coil in between 2 concentric spheres. And he's thinking that, and other people as well have suggested that this might lead to longitudinal modes going into the far zone. So if that's true, then we would need some theory to match that to experiment. And there's also, a couple experimental papers in literature claiming to measure these types of things, but it's pretty obscure and not generally accepted in academia. So that would be nice if we could figure that out. And then another thing, I just want to give a shout out to Jeremy Reese for mentioning the possibility that quasi-crystals, which you could look at in some cases as being an exotic type of metamaterial. It's known that it was claimed that Edgar Fouché talked about quasi-crystals being used in UFO craft. And then around the same time that he was allegedly looking into this, then quasicrystals were discovered in the lab. And these, it's kind of curious as well. Jared was pointing out, he keeps finding all these crop circles with five-fold symmetry. And in the background, I have a little quasicrystal there. They can exhibit five-fold symmetry. And they're projections of crystals from higher dimensions, which is pretty cool. And so it's plausible that these could be used to exhibit a lot of anomalous behavior. It's in the literature, it's pointed out that they have a lot of bizarre thermodynamic anomalies, also a lot of bizarre tunneling properties. And it's possible that there's even some curious ways to get entanglement in these quasicrystals in certain phases when you bring them down to cold temperatures. So a lot of exotic physics that isn't well understood with quasicrystals and metamaterials in general, but hopefully if we explore this mathematics in fuller detail, we can start to describe what might be going on there. And, I presented all this theory today, but at the end of the day, experiment is king. So I'm starting to look into experiments because at the end of the day, I can't figure this out by just theorizing all day. And so once again, I'm interested in electrodynamic experiments that might prove or disprove the existence of longitudinal modes that could propagate to the far zone. Maybe we could actually test, are there material-like properties of the ether? Now that I'm starting to read Tesla, another point he's really pointing out is that the ether in matter, around matter, like still takes on a different form. So maybe in vacuum, and this Shiva was mentioning this as well, the way that ether is acting in vacuum, maybe it's more subtle than people are pointing out because we keep going to the vacuum and saying, well, it doesn't seem like the ether is there. But we do know in QED that the vacuum gets polarized, which effectively can be described as material-like properties. So maybe if we study this further, if it turns out that those longitudinal modes are real, it might turn out that that leads to this notion of bound charge of this medium. And maybe that relates to claiming that this ether is in some sense more real or physical than previously thought, because they usually say the virtual modes are unphysical, even though they're needed to get all the math right, which is another can of worms because, they're definitely useful. They're definitely doing something good. You have to include them in the theory. So that just gets into philosophical debates on what it even means to be real or physical. And so another experiment I'm interested, or class of experiments, is to see if magnetic monopoles exist. I know Lead Scanlon claimed that at strong magnetic fields, magnetic monopoles were needed. He claimed that the interaction of copper around strong magnets suggested it. I don't know if that's actually true or not, but certainly it seems that effectively there's magnetic monopoles in these topological insulators. So it might help to understand the theory for that. And then finally, what if these Hertz or Whittaker potentials are physical? Tom Bearden claimed that there are these scalar interferometers that could be developed that would lead to these scalar wave of these Hertz Whittaker potentials, or we call them Whittaker potentials. And it's curious how we use interferometers to detect gravitational waves. And that was another hint for me because, once again, I'm claiming that the Hertz potentials or the Whittaker potentials are combined with the metric. We're detecting fluctuations of the metric by interferometers. So maybe there's some experiments with interferometers that could isolate some of the Hertz or Whittaker potentials. So if any of these things, if you have any information about these things, please let me know. And so just to conclude here, basically, I revisited Maxwell's treatise, and it turns out we can really expand his legacy. We can look back to the work of Heaviside and try to bring it further. And also, even conventional QED allows for an interpretation of the ether. And I think it's really important to highlight this because we don't have to go to all these obscure theories of these bold claims on the internet. If we just study the conventional theory out there, we can actually get a lot further than one might think. We can revisit Einstein's unified field theory attempts and then consider Hertz potentials. And that seems to be more geometrically aligned. And so it's curious how that theory then suggests that you get these longitudinal electromagnetic modes that appear to be in some sense gravitational. And here's the subtle thing. If those virtual modes in gravity, in general relativity, are classical, maybe the reason why if we just study QED, maybe we say they're unphysical because we're not studying gravity. So we'll have to look more into the interpretation of this theory, but maybe they're effectively gravity. And that's why when we just restrict our study of electrodynamics, it's kind of been subtle throughout the history. And, we've also mentioned aspects of macroscopic media, and that might allow us to provide alternative ways to get after propulsion. And there's still a lot of more questions to be asked, and there's still a lot of answers to be found, but hopefully we can make further progress. So thank you. That's the end of my talk.
Wow, that absolutely amazing. I am at a loss for words. David, absolutely amazing. Let me bring some of the guys in here, and let me see. I'm going to take down presentation to it. Oop, I'm getting some background noise. And there we go.
Yeah, that really rocks, man.
Giant applause. Dr. David Chester. David, you have outdone yourself. Absolutely amazing. Absolutely amazing. Thank you so much. I have never felt so good to be the dumbest guy in the room. So,
Thanks a lot, Tim.
Thank you. And actually we're at 3:28 now. We're running really, really fast today. We're on it went over, but that's still absolutely amazing. So Daniel Davis has a paper transversing the Everett, transversing the Everettian relative state. So I want to put this up, jump right into this. This is about 49 minutes actually. So
can I give a quick caveat?
Oh yeah, go for it, man.
Yeah, so if the talk does seem a little chopped up, I did cut like 20 minutes out of it on the Wheeler-DeWitt equation and Page-Wooter's formalism, just because I thought, when I was going back and rewatching it, I thought it made it run over and it kind of confused a couple parts. So if it seems chopped up in a couple places, that's why. And like my last two talks on warp drives and quantum mechanics independently, this is more of a qualitative talk meant to bridge the gap between the physicist and the layman. It's not a quantitative talk.
Oh, okay. Awesome. Well, thank you. Thank you again. I mean, today, God, we are just nailing it in terms of theory. I mean, Shiva's work, I am like your #1 fan. And then David blows me away. And Daniel, you were doing absolutely remarkable work as well. So in terms of theory, it's just like bam, 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 one after the other after the other. I genuinely cannot. I cannot thank you guys enough. I mean, amazing. Okay, well, let me do this then. And I can leave. Why don't I leave Daniel up, and I'll take everybody else out of the room, and I will start this. Hopefully, I won't goof up the. Okay, and okay, there we go. Oops, and there's Curtis. Curtis is hiding. There we go. Okay. So let me share my screen really quick. Slides. I still. Oops, cancel. Sorry, I still get a little bit messed up sometimes with StreamYard. Still getting used to it. Oh, there we go. Share screen. Okay. And I think we should be able to hear the sound.
About quantum mechanics, usually we're talking about the Schrodinger equation, right? So
okay, perfect.
H of psi equals I H bar equals the derivative by the time derivative times.
And Dan,
psi.
you can hear that okay, right?
Basic Schrodinger equation.
Okay.
Now we could get into Dirac and why, you need a relativistic version of the equation, or which is, that will lead into the Wheeler-DeWitt equation, which I just had written up here. Well, essentially all this is saying is that you have your Hamiltonian operator, your wave function is equal to the energy of your wave function. And this is kind of all we need to know for the time being. So what does this mean? This is Greek to us, right? So we'll get rid of it, and we'll just go through a basic overview of textbook quantum mechanics. I'm not going to go too super in depth with it. So we're going to say we have we'll draw a quantum harmonic oscillator over here. We're going to have our states, A plus B, and A and B. So you have your wave that is evolving according to the Schrodinger equation with time, or with respect to time. So down here in psi of 0, we're going to start and say that our psi of 0 for this state is going to be wrong. This is technically a wrong notation. PhDs, we can get into it in the questions afterwards on why I'm choosing to do this. This is a qualitative talk that's just kind of, again, meant to bridge the gap between the PhDs and the layman. Try to make these ideas accessible to everyone. So PhDs know this is a Straussian communication, that there are some things that I know are wrong, but you can probably you'll see. You should be able to see what I mean. Now, for the people who aren't PhDs in the audience that don't quite know where this is still pretty much gibberish to you, just keep following along. This is as in depth as you're going to need to get into. So we're going to have this down here. So this is our first entangled state. We're just going to say that it is A plus B. Okay, and so then as we evolve it to psi1, psi1, so technically we would want to, we're squaring our wave here to get a probability instead of a wave. So then this would become squared. And so then over here, our new entangled state is going to be 1 divided by the square root of 2a plus 1 divided by the square root of 2b plus. And so this is how our state evolves. We then flip a coin. So we have a 50-50 state here. We're going to say that tails is B, heads is A, and the coin is tails, so we know that our state evolved into B. So we can now erase this and erase this because we know that the wave function collapsed onto the state that we had associated with B. Now there's not getting too deep into why this is inherently wrong. General relativity doesn't work with this renormalization process. What general relativity does work with is a wave function evolving according to an appropriate version of the Schrodinger equation with no collapse. So it's not that GR and quantum mechanics are incompatible. It is that GR and the collapse postulate of certain interpretations is what doesn't work with quantum mechanics. So we can say that we can find our reality as a vector in Hilbert space, right? Because in Copenhagen, you know, the textbook version of quantum mechanics, we just said, you know, get rid of the other state, it goes away. We renormalize the process. That's what we do with the energy. When it's just some wishy-washy process, and almost everybody admits that it is incomplete. Taking the Everettian point of view, or the world's point of view, as I said, that reality is a vector in Hilbert space, right? So how can we think of this? Well, we can think of a Bloch sphere, right? So we have our qubit over here. We're going to have some point over here at some elevation angle theta, and it has a mutual angle phi. This is going to be r. So we have a coordinate of r, theta, phi. Now, how does this relate to this? Well, any point of r can be associated with one of our states. So in this two-system state, if the coordinate's up here, we can say it's A, and if the coordinate's down here, we can say it's B. So A and B, and this is starting to get into, you know, what spinors are. We don't really need to worry about spinors today for this talk. Okay. So we have this picture. What's a different way we can look at this? So let's look at a qubit state here. So there's always going to be some area here associated with this sphere. So you're going to have the area of your sphere, and there's going to be some entropy associated with this quantum system. And so what is so the dimensionality? So your DIH, your Hilbert space, the order of E to the S. Well, what is S? S is our entropy, and we're going to say that here today that we can define entropy as our IR unit divided by our U V. Now, technically, we could count infinitely large wavelengths and infinitely small wavelengths in our quantum system, right? But what's a reason that we might not want to do that? Well, if we count more than a certain amount of, if we count down on the smaller wavelengths down below a certain amount for any given area, or for any given system, that's the IRs, the large parts of the longest, like the longest wavelength that you could fit your system versus the smallest. Getting slightly ahead of myself here. If you count more than a certain amount of these per this, the system is going to collapse to a black hole. And we know from Bekenstein and Hawking the black holes have a finite entropy, right? So say again, the entropy here is our area divided by our Planck area. So area divided by Planck area. So we just count the area of our system here in Planck areas, and that is its entropy. And so then that entropy number becomes the exponent for here. Now, why is that? Remember, we have to think of this blow sphere as a shell. So if we scraped off one radius coordinate with freedom on the outside, that was going to change your entropy. It's going to change your area of the system, which then changes the entropy. And so you get this this system where one is dependent on the other. So you have, so we can write down that A is proportional to S, where the area is proportional to entropy. Okay. So where is this going to start coming in handy for where we find general relativity? Okay, well, where this is good, we'll erase this 2 now for the time being. This here is proportional to S. So we know that area is a measure of geometry, right? It tells you something about the geometry of your system. So we can relate our area to some type of spatial curve, some spatial curvature. Through spatial curvature, we can relate it to the G00 aspect of the Einstein tensor. Einstein tensor, spatial. And then on the other side here, so we have our entropy, modular Hamiltonian through the entanglement first law. And our modular Hamiltonian can be associated with T00, or the energy density of the system. And when you have T00 is proportional to G00 through Lorentz invariance, we end up with G mu nu being proportional to T mu nu, which is just general relativity. That's Einstein. So this is entropic gravity in a nutshell, and why general relativity does work with Everettian quantum mechanics, the many worlds interpretation, but it does not work with other interpretations, which is why people try to sell the quantization of gravity as something that we need to do, but that's only, we don't need to quantize gravity when we have entropic gravity. That's what this is. So what is a way that we can draw this out to more represent, get back to our quantum state here? Well, we can do it with a hyperbolic tessellation, right? So we'll just the red one first. And this will only take a second. So we have this hyperbolic tessellation. On this side, counting all of these nodes in here, it's going to be our entropy. So there's always going to be a certain amount of entropy that fits within any given area. And so we could do this for the whole system, or we could count off any one of these smaller little nodes and make that our system of focus, and this area entropy law will still hold. So therefore, general relativity will also still hold. And just to try to help bring the visualization back to our quantum system, we'll redraw our quantum oscillator, where deeper in the well, it's going to be where your current position in time, which is going to be more near the center of this. And then this becomes our area, and then these become your entropy. So this is kind of a map of one of these slivers. So we can map one to one to another here. So this starts to bring up the question, how does one go about traversing this this object, this multiversal landscape that quantum mechanics seems to provide for us? How do we escape from these? Well, let's turn to Penrose for a bit. So Penrose had some good ideas with this, with his orchestrated reduction. So what is his OR? So it's going to be the order of sign instead of equals, because it makes me more comfortable. H bar divided by gravitational self-energy of the system. So this should look a lot like the H bar divided by E equals T of the Heisenberg relations. Okay, well, what does this mean? So A plus B and AB, as it progresses through time, so there's going to be some gravitational, so I'll go to green now, so there's going to be some energy, the gravitational energy of the system, and this state will be different from this state. So what this tells us is that the time, T, the time, so that this decoherence happens is going to be based on, this H bar divided by E, the system. So the more energetic the system is, the faster it is going to happen. Now, another way that we can write this is that when this separation becomes bigger than H bar is when we say decoherence happens. So that is when the splitting happens. Now, take this, we can rewrite it. Why? Because C equals 1 equals H bar. H bar equals E times T. So because C equals 1, we can replace this with C, replace these with C, and what happens with these branches, as the weight gets larger than H bar, they start decohering faster than the speed of light, which is why we don't normally interact with these systems. You need to be able to go faster than light to traverse between these. Now, that being said, do we know of anything within the framework of quantum mechanics or general relativity that can be used for potential faster than light phenomena? Well, stuff like wormholes and warp drives in the context of general relativity. This is backed up in a 2021 paper by Dr. Yuri Eroshenko, called "Escape from a Black Hole with a Spherical Warp Drive." He proposes the WD equals EPR paradox to go complementary with the ER equals EPR, not paradox, conjecture, excuse me. So essentially that warp drives and wormholes can be used to escape from the event horizon of a black hole, or to jump between one of these eigenstates here. And that they really, because again, we have found that general relativity is a semi-classical approximation of the entropy of or the entanglement entropy of our quantum system here. So anything that we can write in GR is really just a semi-classical approximation of some entanglement. And so that gets, when we start to view a warp drive in that lens, really what we see is that it's an entanglement machine that can jump between these eigenstates because it can go faster than light. So yes, in order to understand a little bit more about warp drives, we are going to need to now take a break from the quantum mechanics and jump into general relativity, what a warp drive means in that context. Some of the things that we can probably start to do with this. We'll keep some of the pictures that we have here in the back of our mind. We'll come back to them later. So if we're talking about general relativity, G mu nu equals 8 pi G divided by C to the fourth T mu nu. So what does this mean? This is literally Greek to me, right? We use that euphemism here a lot. So it's that space-time curvature tells matter and energy how to move, and the matter and energy distributions tell space-time how to curve. So energy affects geometry, and geometry affects energy. same relation as our area proportional to entropy. We have geometry proportional to energy. So what do we start to mean when we say this? Let's do the visual representation first. So we're going to have these map of space-time, G, mu, nu, and then inside of it, T, mu, nu. So energy tells space-time how to curve, space-time tells energy how to move. So if we're going to flatten this back out, you just keep this picture in your head. I'm sure you've seen something, some stuff similar to it. Let's just flatten this out to focus on only one of those geodesic lines. So we're going to have our G mu nu, our space-time well. This is what the people mean by your gravity well. In it is going to be your T mu nu. G mu nu. So this is a way that we could flatten out, a 2D map down to a 1D one, just so you can see. So we're going to say that our G mu nu equal to, and on this side we have the T mu nu. So on your T mu nu over here, you have your T0, 0 is your energy density, like we talked about earlier. Your 1, 1, 2, 2, and 3, 3 are going to be your pressure. These blue ones here are your momentum flux. The ones here are your shear stress. Here you have your energy flux, and here you have your momentum density. I'm not going to worry too much about this today. We're going to worry more about G mu nu, the Einstein tensor. So I'll go back to my blue here for a second. So if we have our space-time axes here, essentially we're making a space-time globe. So we're transferring a map, a globe of like a 3D sphere, and we're projecting it onto a 2D surface and making a map for it. So your TT will be for your time axes. So I'm not going to draw the time axes here. Make it a little too confusing. So your XX, your YY, and your ZZ. So say if this is what like our X, Y axes, this tells us the relative lengths of each one of these squares and what these should be. The reason they go down here is the TT, XX, YY, ZZ. Clock is your T, your T coordinates. Your rulers are your X, Y, Z, and then the protractors between the rulers are these adjacent ones up here. So your 4 Cartesian coordinates and your 6 protractors. So 1 clock, 3 rulers, 6 protractors for 10 PDEs that you have to make. So reeling this back into warp drive, well, in 1994, Dr. Miguel Alcubierre, he inspired both by Star Trek as well as the expansion of the universe for coming up with a G mu nu that was capable of superluminal velocities. Because remember, nothing with mass, according to relativity, can go faster than the speed of light, but space-time itself can. So that's a very good loophole for us to exploit here. So keeping this in mind, just remembering whatever goes in over here will affect the energy requirements over here. So this is what Alcubierre did, is he started with a shape and he found out how much energy is that shape going to require. And we will get rid of this for right now. So if we're going to talk about warp drives, we need to bring this down now. So G mu nu. We can write this in something called a line element. Okay. So we're taking our X or our TT, XX, YY, and ZZ here. So because there's two of each, so it's making our DS squared, our space-time geodesic, what the shape of that. So you have point A, point B over here. You're basically doing Pythagoras' theorem. So this is going to be your dx, dy, and then there's a squared plus b squared equals c squared, but this is for curved space-time, so this is going to have some curve to it. We're finding the length of this curve, so this is going to be our ds squared. ds squared. So now that you know what this kind of is supposed to mean, at least enough for this talk. So it's going to be, so we have to specify a metric. I'm going to be using the plus minus 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 metric for this talk. We could use the minus plus 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 metric. You just have to establish which one. I digress. So dt square minus dx minus dy minus dz squared. Okay, so trying to reel this back into warp drive, we're getting some shape that will be represented by this by a version of this equation here. So what is that shape? What we found out is that ds squared equals dt squared minus bracket dx minus v f r dt squared minus dx minus dy minus dz squared. So what does this mean here? Well, this is for a warp bubble moving with a geodesic in the x-axis with time, okay? So moving with some velocity, v, on the x-axis through time, divided by some shaping function. Now, Cuvier, has r be a shaping function to denote pretty much a spherical warp bubble. And so if we're going to go back to our 1D map of the G mu nu and the T mu nu, what might this look like? So we're going to have our space-time geodesic, positive well, flat space-time, negative well, positive, negative. Yeah, inside of it is our T. And this is your warp drive in a nutshell. You see that there's we're going to draw some line of energy gradient. This makes a hill right here. The ball rolls down the hill would be a kind of a bad analogy to use, and what gives you your velocity. So this is our warp drive. Which, remembering from earlier, is actually a semi-classical approximation of some entanglement structure, right? There are some problems with this, though. One of which being it violates the positivity conditions, which may or not be an arbitrary constraint put on by Hermann Bondi in 1957. That's a different talk. But also it needs like 10 times the amount of observable mass in the universe, or mass in the observable universe, which is problematic to say the least. Now there are, because this came out in 1994, we're in 2024. There's been 30 years of various academics and PhDs have been working on this to really drive these energy requirements down. So I guess we could either look at what some things are that people have done to lower these energy requirements. Actually, let's do that first. We'll get rid of this because we don't need it anymore, but we do maybe need this. So one of the first things that people have done. So Dr. Harold Sonny White of NASA Eagle Works Laboratory. He played with the equations a lot, and he figured out you do two things. One, you make the bubble thicker. So I'll redraw this to be a little bit more accurate to Alcubierre's representation, so we can see a little bit better on how some of these people have said to improve this. This would probably be a better representation of Alcubierre's bubble. So what White did, he did two main things. First thing is, this is too thin. We're approaching 100 times by the magnitude of the plane length, which is really thin. And then if you know that you're going to have energies commensurate to fill that. We're not going to get too. I'm digressing. So just going off this, first thing that he does is he makes the bubble wider instead of thinner. So the actually, the distribution of the energy in the bubble isn't as concentrated, and actually this helps to lower the energy requirements. The second thing that he did is he pulses the bubble. Actually vibrates it, and apparently this softens the stiffness of space-time and makes it easier to engineer. According to him and his work, I can link his papers in the description for you guys. So it's already two things that he did to get the energy. Just doing that, he got the energy requirements down from 10 times the amount of observable mass in the universe. Natario got it down to solar and planetary size masses. He gets it down to about 700 kilograms worth of mass energy via this method. Now, this isn't the only method. So we're changing the shaping function. We're making it more complex. We're vibrating it through time. We're changing the shape of it a little bit. We'll keep going with this intuition to alter the shaping function. So Charles Barcelo, he came along and he made another observation. He's basically said, well, the choice for a spherical bubble is really it's an arbitrary choice. There's no reason to choose one or not to choose one. It's just again arbitrary. The decision to use a spherical bubble it makes the equations a little bit more handy to work with. It's like the old jokes. Assume a spherical cow. But so what does Barcelo does? So we're gonna rewrite our warp drive metrics of ds squared equals dt squared minus dx minus vf, our shaping function. Instead of r for a radius, makes it an x, y, z. Technically, it was x, y, z, kt the whole time. Each Alcubierre chooses to make it a spherical bubble. K being the scalar constant up here, by the way. dt square minus dy square minus dz square. So what does Barcelo find out? Well, he finds out that if you just change the shape of the bubble now, not only does the energy requirements go down a lot, so does the need for negative energy starts to go down a lot too. Now there are other people like Chance Glenn, Eric Lenz, Lithuania Heisenberg. I can name quite a few that have gone and shown that you can actually have positive energy only energy requirements. But so what Barcelo does is he goes with a tic tac or elliptical shaped warp bubble. Actually, I'll make it red to keep it consistent with our team theme here. So instead of a sphere, he makes his elliptical. That again lowers the energy requirements even more. Lower the energy requirements from Alcubierre's and Natarios. He didn't plug this into White's, though I do believe Fernando Loop has, and that did work. As well as Preciano's. So there's actually quite a few ways that we can get this down. So yeah, so we start to combine all of these, some of these different various methods. You change the shape of the bubble, you change the thickness, you pulse it. All that's already doing a lot to really lower our energy requirements into something that's probably a lot more attainable. So Parisiano introduces another term in here. A X, Y, Z, K. Adding this in again to make the bubble more dynamic. Again, he claims that you can get it down to arbitrary levels, and I think if you're combining all of the above, you probably can get it down to really a lot lower energy levels than is thought of in the mainstream now. On top of this, we can also look at Sarfati's model. Now, what does Sarfati say in essence for what to do with this? Actually, before we go to Sarfati, I will change this to a positive. Well, because we can now, because we said we can. So energy requirements are already a lot better just off of playing with the shaping function. Now, if you look at Sarfati's work, if we're turning into here, well, what is the speed of light? C, electromagnetism, is 1 divided by the square root of epsilon and mu. Or you can say is epsilon, E not epsilon, epsilon not mu not squared. So if we're doing this, we can plug this back in and reformulate Einstein's equation. And I can do that right now. So G mu equals 8 pi G. And then because how we're reformulating this, it's no longer divided by C to the 4th. It's times epsilon, or it's E on epsilon. Epsilon not mu, not for the permeability of the vacuum. And normally you would just square this here, pop this off here, and put the T mu back in. But he's taking it even a step farther and is saying, what about general relativity in matter itself? Especially things that might have a tunable refractive indices, like certain metamaterials, which metamaterials is his whole thing. But there's might be. I'm digressing. We'll just stick with this. So this here, and then we'll put another bracket in because we need to. He talks about from warp drive. You want to do the near fields of this. So he writes. So we put another 1 plus near field of epsilon 1 plus mu. So this is what Einstein's equation then becomes. So the K here is this scalar constant term. So when we plug this into here, and I could rewrite out the whole, actually, you know what, I will rewrite it because I have the power of editing. So our equation starts to become something more like this. And again, this is going to start to drastically alter the energy requirements for on the T mu side of our equation over here to get the warping of T mu. So when we start to combine all of these various improvements, Sarfati, Barcelo, White, we can't just look at one modification of Alcubierre. We need to look at all of them. Start to combine the best ones that are compatible. When we do that, we start to view that Sarfati might be actually very correct in the sense that we could probably do this with pretty low energies if we have the right material. Now, if we don't have the right material, we can still do this. We just need a shitload more energy. Excuse my French, it's just the reality of the situation, but not impossible if we get something like fusion or 0 point. If 0 point is even a thing, there's the caveat on that. But let's just say we get fusion unlocked right now. You can do this with fusion. If you need fusion and superconductors, you could do this. But then we could use the profits from that to start, getting better and better optical properties of metamaterials, so we can start to do the thing, right? So we've gone over the multiverse, the quantum multiverse, and warp drives, right? Because we need again. So where does the warp drive? Where does this become back into our quantum mechanical multiversal picture? It's because that for traveling, this is the mechanism that we need to travel faster than light, and faster than light travel is the mechanism that we need to jump between the eigenstates, or between the various branches of the quantum multiverse here. So what might that look like? So let's erase this here. So I guess we'll draw back out our quantum well over here. We got our energy, our different energy states. We're farther in time here, is closer to the center of our visualization over here, and each one of these nodes, the entropy of what these different systems are. Well, let's repaint this picture. It's sort of something a little bit closer to like a space-time diagram. So you're looking at something like a block universe now. So this is going to be our. We'll come over here first, and we'll do some more caveats. And I know there's people that are going to say this is wrong because you just shut up and bear with me for a second. We need like our Minkowski diagram, which people are going to say is wrong for this type of thing, but just bear with me. You guys will know what I'm trying to represent, and we'll get the nitty-gritty of my visualization later. And often, and the Yuri Oroshenko paper that I mentioned earlier does use this this graphic. So faster than light travel, point A, point B is going to be outside of your light cone, and you're going like that, right? Now, I know there's going to be people screaming at me in the comments already, no, that's wrong. There's going to be two different answers to this. There's going to be some people that are going to say that our null GOD6 are actually skewing, like scissors as our velocity becomes relativistic. And then there's going to be other people that say that that you're actually rotating your light cones to get them to overlap. I'm aware of these caveats. This is just makes for easy visualization. So for those people that are more comfortable with those graphs, just know that when I'm drawing something like this, we are using it to represent that. Okay, so now that caveat's out of the way, really, a straight line would be for a constant velocity, right? Well, we know that it's not going to be a constant velocity because you're starting you're resting in your local frame. So you need to accelerate away from wherever you are, slower than light, and then eventually you cross some transition to the superluminal regime. So again, these are our null GOD, so light always goes on these 45s. And coming here, and then eventually we transition. And we go into this tachyon regime. And we start going faster and faster than light until we want to slow back down again to our wherever our target location is. And you will see that this made something sort of like reminiscent of a wave. Keep this in mind. We're going to transfer this over to this. Because remember, this was just for one space-time coordinate. We're trying to travel between the coordinates in the multiverse because we're taking serious the notion that we can travel outside of our light cone. And when we say traveling outside of our light cone, we mean getting our light cone to overlap with another adjacent light cone. So say that we are in this branch over here. We want to go to this one. So we're going to start here, and we're going to go slower than light until we hit our point where we go back. Then we start intersecting through some of these ones, and then we come and slow down over here. Now, how do we get back? We need to make it two jump movements. We need to do two different warp events if we want to get back to the same point that we started, or potentially earlier in the same timeline, and we can potentially explore arbitrarily any of the coordinates in this system. Now, we could also probably say that time is closed. If this is a closed universe, you could probably, much like you go the same way in a globe, you'll wrap around the circle. You could probably do something similar where you go all the way, extrapolating out through here. Or you could come back and travel that way too. You could probably do either. I don't know I'm sure fuel would dictate, what your what geodesic you decide you want to travel. So that's probably a good segue. So really, if we're going to expand this here, we can start to think of let's erase this. We're going to transfer over. If we apply this concept to our blow sphere here, really, what each one of these becomes is an S2 sphere, a 2 sphere embedded in the 3 sphere connection. And again, this is where the picture starts to get interesting. Remember, we can apply this spherical coordinate into this system. All right, so if we put some line in here to go off as our baseline, any one of these points on here, at least in this 2D circle, can be represented by an r theta, because it's becomes like a phase space almost. Well, this becomes our time fiber, and really soon, so time becomes a U1 or an S1 fiber. So you'll have this. So R becomes T. So our R over here becomes our time parameter. So theta angle. And again, so this extrapolate this out to a sphere also. This is a S3 hypersphere. So spheres embedded in a hypersphere via the one sphere. Because remember this, we said this is like a lot like a spinner, where once you get out here, you kind of teleport, even though it's not actually a teleport. It's a topology trick. I'm sure the PhDs in the audience probably going to know what I'm talking about. The people who don't, just look up spinners in the Dirac equation and mass shells, and you'll see what I'm getting at here. So this becomes our S1. So when you have your your S2 spheres being connected via S1, so your S2 spheres being embedded within your hypersphere with your S1 fiber being the connection, being the connection that makes up the phasor. We see that the phase space of the multiverse is in essence like the Hopf vibration. So each timeline can be considered one of the S1 fibers in the larger fiber bundle. So as we're looking at time now, is our R parameter on our blow sphere, as well as being a U1 fiber or an S1 fiber, we can rewrite again Einstein's equation a little. We're going to add a term to it now. So we're going to look at specifically we're going to look back at the line element. So our ds squared equals dt, and because t is now the r coordinate in our spherical coordinates for our blow sphere, we're going to add a theta phi parameter to our line element. So that the t parameter, being our r, will tell us which layer of the onion we are in, and then the theta and the phi parameter will tell us which sphere in the hypersphere, so which part of the onion we're in. So we get the layer and the part of the sphere, and then within the two spheres, when our regular x, y, z Cartesian coordinate parameters are going to come back into play. So this starts to give us a very basic framework in how we can traverse our multiverse here. Because if we're going to go back to this diagram that we made right here, well, if we put an arbitrary line here, there's going to be an extra distance that's put in, because these will have the same t coordinate at this level, but in this case, the theta angle would be different. So we have to add this into our geodesic to help give us the distance, and then that'll help give us the energy requirements for what the warp drive is going to need for that particular warp event. And what we would normally consider as a travel between different branches, well, we need to consider a Lorentz transformation now for the system. What might a Lorentz transformation for the system look like? It will look about like this. So you'll see the hyperbolic tessellation here with being represented in the VR, and as you walk through it, you'll notice that the shell wraps around you and the observer always stays in the center of the system. This is very reminiscent of Einstein's equivalence principle, where whether or not you're moving the universe through you or pulling the universe around you, it's the same amount of energy. There's no difference. So, really, when you're running a warp drive, you're to travel between these different eigenstates, these different branches of the multiverse. You're performing a Lorentz transformation, sort of like that visual that I just put in here. So where are we going to go with that? So we covered the essence of multiversal travel, the basics of quantum mechanics, how you can find general relativity in quantum mechanics, and then how you're going to use a warp drive to travel between these branches, what a Lorentz transformation might look like, and a plethora of different ways to lower the energy requirements for a warp drive. It explains a lot about like the UAPs and the recent science around them. Some of the quotes, like Burleson saying that they were told in this gift that they phase into our reality. Well, this is the phase space of the multiverse, so that makes sense. Yeah, no, time travel is multiversal travel, and you need a warp drive to do it, and it's all semi-classical approximation of some larger quantum entanglement. I guess we'll cut that there.
There we go. Okay. Let me see.
There we go.
How's that? That's working. Okay. It ended abruptly. You're like, cut that there. So let me, Dan, let me apologize to you. So I took my earbuds out to call Mark about lab time, and it paused. And then I was like, okay, I'll charge them while they're out. And then it paused again. And I'm just like, okay, that does it. I'm done. So, but let me do this. I want to bring everybody in here. We'll get the whole gang. And let me see. Yep. Everybody, please put your hands together and give Mr. Daniel Davis enormous applause. Enormous applause. And again, if it's okay to skip the Q&A time, Dan, I'm glad you were here with us. So a lot of folks like to record stuff because it reduces the pressure for error, like I make like all the time, right? When you're live. So you're able to do that. And that was why Dan recorded in advance. And as folks can see, you did a ton of editing. So thank you very much. And again, and this would apply to yourself or Shiva or David Chester, or really anybody. If you guys have more, if you have extended versions of these, because I know that you did cut a lot out, come back in, do more presentations. I'm pestering Shiva to do an entire series. So
this is all the base work that I'm basing my stuff on. Is that those are all white papers I printed out.
Yeah, no, it's amazing. It is amazing. You guys are doing incredible work. I mean, everyone is. I'm humbled and honored. And I know I sound like a brown noser saying that, but it's totally true. Just to see everything that's happening. Like on the theory side, you guys are pushing forward into new ground. And then on the experimental side, and we'll get to that now, the lab guys are doing tremendous, tremendous work. So let's do this one more time. Put your hands together, not only for Daniel Davis, but also for Shiva and David, Russell Anderson, and all of you, because this community is kicking butt right now. So okay, and I see Drew. Drew is making motions. So let me do this. Let's go into lab time then, because we're a little bit over. What I'm going to do is I'll take everybody out, and I will go. Let me see. Should we start with Mark or Drew?
I guess I'm ready if We got Mark loaded.
It's okay. Let's if it's okay, let's start with Mark. Mark has been asking me for a couple hours, and he's juggling a couple of things today. So here, I'll take everybody out of the studio except for Mr. Sokol. And oops, how did I get over there? Okay. Oh, I'll take myself out too. Take it away, Mark.
Okay. I have the back camera of my cell phone activated, so I'm going to flip things around in a moment and show you guys what we've been working on. We haven't done a lab update in a while, but we have been working on a lot of different projects. So first things first, this is what's new in our X-band Alzafon experiment. I picked up this pin modulator from George Hathaway's lab up in Canada. And what this does, it basically allows you to shut off the RF extremely quickly. So apparently when you shut off the RF from the signal generator, the wave tube amplifier still puts it out for a little bit. We're talking microseconds, milliseconds, like really short amount of time. But when you're pulsing stuff, you know, at a couple hundred hertz.
Mark, sorry. Let me interrupt really quick. Can you flip your phone sideways? Because it's doing portrait view. And yeah, there we go. Sorry about that, man.
Oh, no problem. Okay, I can start again if you want. So this is basically the X-band system. The update that we have for it right now is our pin modulator. It allows us to cut off the RF extremely quickly. Although it is capped at around 1 watt. So what we're doing here is we got a load coming straight out of the amplifier. That also protects the amplifier. Our previous attempts, we've burnt out our amplifier. So that lowers the amount of energy coming out. It also lowers the amount of energy going back in if there is any reflected energy. So this signal generator actually is what creates the pulses. So we can control the pulses over here. We're going to be both pulsing it from the signal generator and the pin modulator simultaneously. And that's feeding directly into the output is feeding directly into the traveling wave tube amplifier, or the tweet as it's called in the industry. So we should be able to get maybe like 2 or 3 watts of pulse power going into our waveguide setup. Now on the other side, we're also going to have an output from here that's going to feed into our nitrogen laser, which I have set up over here. The nitrogen laser is has an output over here, but this allows you to pulse microwaves into the sample cavity, and together with the pentasene, we'll be able to make triplet state electrons pairs and hopefully excite the sample quite a bit more than was normally allowed. There's a paper that claims about a 250,000 times increase in the nuclear magnetic resonance signal to noise ratio versus the noise floor. So using this process, so we hope that it will increase also our weight loss using dynamic nuclear polarization. Next up, this whole setup over here, we picked up as well from George Hathaway. This is the S-band or 3 gigahertz setup that Daniel Alzafon and George Hathaway built in Canada, up in Mississauga, which is like an area of Toronto. This thing is probably the most complex Alzafon experiment ever attempted, and they never actually ran it up. What happened is they got probably, I would say, to the 99%, line, to the 99th yard, and ran out of funding. And there might have also been a loss of interest at that point as well. I know people tend to procrastinate when things like that happen, because it either works or it doesn't sometimes. So it was kind of scary. But this thing is freaking a marvel of engineering. Let me run you through what's going on over here. So these are S-band waveguides. So the feed is from here. It comes in, splits. We have the matched load over here, reading off of the load for power meter. This is some crazy heavy duty 100 kilowatt peak load. I don't know what you need that for. Everything about the system is overkill. That basically is a circulator or an isolator that allows only the energy to go in one direction. Then it takes a curve, goes through this little flexible joint, and goes into that little waveguide or tuned chamber over there. Let me move the aluminum foil out of the way. Now, what we got going inside that waveguide is astounding. We have the ability to run a sample on the Alzifon experiment at liquid helium temperatures inside of a vacuum. It's with a window, actually. There's a camera on the other side. You can see it at liquid helium temperatures in a vacuum. Now, how this is done, it's pretty crazy. So this is the chamber that allows for the vacuum. There's a fitting that goes up over here. This glass over here is fed the liquid helium from the other side. Of course, you start off with liquid nitrogen first, pre-chill it, and then you go to liquid helium. They use liquid like a vaporized helium inside of the chamber first, inside of the vacuum chamber first. That allows the liquid helium to cool off the sample, because helium is a very good conductor of heat. Then a vacuum is pulled again. Now, the vacuum pump over here is massive. This turbo, it takes about 2 people to lift it. It's freaking huge. This is the roughing pump that's going to go with it. Now, over on the other side, I can show you guys some more stuff. Again, there's a camera here where we might swap this out with something else. And this is all the liquid helium, liquid nitrogen stuff. There's temperature sensors. There's an ice bath that goes on the top, so you have a reference of 0 degrees for your temperature sensor, so you know exactly what temperature you're at. These are control valves for the flow of the nitrogen or the helium. It's overall an astoundingly complex system. Now, the weight measurement is taken using a thermogravimetric analyzer's head. So a thermogravimetric analyzer basically takes a sample and inside of a vacuum heats it up, and you watch the weight of it change as it vaporizes. So with a known chart of what temperatures things vaporize at, you can say, oh, it's got 10% calcium, it's got 5% nickel, because as we heated it past those points, it suddenly dropped out. So that's a very accurate balance system, and that allows you to stick sample inside here and get weight measurements. I don't know if we're going to go with liquid helium. Helium is pretty hard to get these days, but we're definitely going to try the nitrogen laser version of this, and with the pentacene. So we're gonna use this for many different projects in various configurations. The water chill over there is under maintenance. That will chill out everything in the system, including the magnet and the turbo pump. Okay, here's what else is going on. We have our vacuum pump over here, our vacuum system over here with the acrylic chamber. This is waiting on, what's his name? That guy who offered Michaels. Yeah, Jesse Michaels is going to be coming down here probably in July, and we're going to be running T.T. Brown experiments. This is one chamber that we have set aside for him for that experiment. We also have another chamber that just came in. We're waiting on the base plate and the fittings, but this is glass, 28 inches tall, 14 inches wide, massive piece of glass. They don't make them like this anymore. It was made in 1967. So we're going to have that ready sometime later this month. And this is one more experiment that we've been working on. So if you guys watched our live stream a couple of weeks ago, we did what we called the invisible wall experiment. It didn't work, but we did build up a pretty strong static field, and the person holding the lead, or the high voltage lead, to energize that spinning bowl on the ceiling, did feel some strange anomalous forces. The critics came by later and said that we should have had our the edges of the bowl perpendicular rather than they were almost at 90 degrees to each other, so the field probably didn't propagate correctly. I accepted that criticism, and we then proceeded to try and make a polypropylene 3D print. Now, for those who don't know, polypropylene is extremely difficult to adhere to the base plate. So what we ended up using was a PLA plate for the base, and then the polypropylene edge shroud, which is the only part that really is active in this experiment, was then printed separately and glued on. It went through many iterations before we finally got to this level of perfection. The motor over here is a 24-volt DC motor. We're going to be able to spin this up and run this in a humid environment or as a leaky dielectric without heating up the entire lab. So that's going to be very nice. We're going to plan on running this experiment when yours truly, Tim Ventura, comes by here later this month. These are some other things that I picked up from George Hathaway. I didn't even know these things existed, but I was dreaming of building one. This is called a trombone, an RF trombone. Now, let me see if I can do it with one hand. Yeah. So what it's doing is it's changing the length of a coax. Now, this is all done with silver plated or solid silver connections. So there's an internal live connection and an external ground connection. And just by moving this in and out, you're able to change the length of the wire. And for different frequencies, the lower the frequency, the larger it needs to be. So this is probably for sub gigahertz. This is for above gigahertz. This allows you to tune devices to an optimal SWR. We're going to be using that for our warp drive experiments, which I'll show you in a moment. So over here inside of our semi-clean room, we have our laser interferometer, and it is complete. Eric Rivera has been working on this diligently. Now, it might not be possible to view this very well with the with my cell phone camera. Yeah, you can kind of see them. You see those little lines. Those are the interference patterns. Now I'm going to tap the table a little bit, and you can see them disappear for a moment as I tap the table. The reason why it recovers so quickly is because there's actually a vibration isolation table underneath it, and the pressure for the vibration isolation table is provided by this little Tikes ball, which probably needs to be inflated again. So our first warp drive experiment we're going to try is a fractal array antenna. Again, our concept of warp drive over here is basically a standing RF wave in space, similar to what David Perez has achieved at QED with their amazing results. So we'll try powering this up and sticking it inside of the inside of one side of the laser, and we'll see if there's any changes to that diffraction pattern. And last but not least, we have what we call the 875 experiment. Now, to many of you, this might look like a little ball, but actually what's inside of it is a very powerful magnet, which we have spent quite a long time profiling to the nth degree. This is version 1.1. You can see in our notes. I think we threw out most of these notes. Basically, what you're looking at is a profile, a 3D printed profile that we printed out, and then we measured with an ultra-sensitive Gauss meter the strength of the magnetic field at different points. And we kept on tweaking it until we got every point along that profile to match roughly 875 Gauss. It was then extrapolated out to a circle, 3D printed, sanded down, smoothed out, and aluminum plated inside of our chemical vapor deposition machine. Well, what this is right now is a sphere that at every point on the cover of the sphere is a thin aluminum layer sitting at 875 Gauss. Now, what's special about 875 Gauss is that at 875 Gauss, the gyromagnetic ratio puts the Larmor frequency at 2.45 gigahertz. That is a standard magnetron for a microwave oven. So it's a pretty standard frequency. I don't think I'm just going to stick this in a microwave oven. It will probably burn up if we do that. We need much lower energies. But assuming we do this correctly, with the magnetic field on board, there can't be any argument made that there is magnetic coupling, because there's nothing for it to couple to other than the magnet that's inside of it. So if it couples to the magnet, you shouldn't see any weight change. So this is exciting. This is probably the first proof of concept of a craft with an onboard magnetic field. My only hesitation about this experiment is that the magnetic field lines are not homogeneously directed. They're homogeneously in amplitude, but they're not homogeneously directed. So field lines over here can be vertical, but the ones over here are more horizontal, and in various configurations, because it mostly is more of a toroid. But yeah, we'll see what happens when we stick this inside of a magnetic field. And yes, that's what's happening with our 875 experiment. We've been calling it the black boob because we're printing it at a black PLA, and it kind of looked like that when it was printed out. But over here you can see many iterations. This was the culmination of several weeks of work to get a magnetic field perfectly aligned with a internal magnet. And one last thing, this is something that David Chester might find interesting. You were talking about magnetic monopoles. Well, we know that of a one magnetic monopole, a Halbach array of magnets. This is a Halbach array coil. So if you can make a prediction about what this would do when energized. The last few times we tried it, it exploded. So now it's been encapsulated in epoxy completely. So maybe when tin comes by, we'll try to explode it again and see what happens. But that's pretty much our update from the lab, guys. Tim, are you there?
Yeah, sorry about that. I was having trouble with the controls. Okay, Mark, thank you, sir. Thank you. Okay, so yeah, I think we're all set. Again, for everybody, Mark, you were doing amazing work, absolutely amazing work. You were just at George Hathaway's, you were just at the conference. So you were driving, running, traveling, it's the whole 9 yards, and you're doing experimental work at the same time. So thank you, man.
And we're going down to Florida and to Todd's place. So we're going to hit pretty much everyone this year.
Yeah. No, it's really, really, really exciting. So let me do this in terms of labs. Thank you again. Let me see who else is ready here. Let's go to Drew. Drew has been patiently waiting.
Hey, Tim. Can you hear me?
Okay. Yeah. Sorry, I took myself out instead of Mark.
Well,
take it away, man. Go for it with the lab.
I can't go out and just walk around my shop like that. Everything's in disarray out there. But what I want to show is we're getting ready for some big demos, and we're most comfortable demoing and showing off technology from, say, 3 or 4 years ago. Actually 4 years ago. And although it doesn't look like much, this little cube of styrofoam, which I have a version right here that I'm going to open up and show you what's in it. This makes about 125 micronewtons of thrust at around 40 kV. So lethal voltages, little tiny bits of thrust, but this is where we were 4 years ago. So what I'm thinking about doing is making a video that shows how to manufacture a thruster that you can actually replicate our successes or, whatever from a few years ago. And they're particularly stupid simple. If you went to the patent, you'll see that there's a kind of like a heat sink, if you will, kind of a three-dimensional structure and a plate. And what's going on is the plate is ground, and this is the high voltage. So if you look at it from this, you can see here's the fingers that are sticking out in true 3D space, and these are the wells. Inside there is the wells underneath it. And in order to make thrust, you would go get yourself a ground plate, and you would put it like that. So, and the reason you do that is because at 40 kV, the field would blow right through anything smaller. So you need about this much styrofoam. And what I thought I'd do is just go through real quick how this thing works. And basically, when you charge this little grid of metal up, what's going to happen is you're going to get real high electrostatic field along these sharp lines, because all this is copper foil tape. So you're going to get super high electrostatic field lines coming off of these really sharp edges right here. And as you go down into the C channel that's down inside there, you wouldn't get any field because it's kind of like a half pipe. And if you have a structure, if this is all metal, then there's no electrostatic field inside of a hollow pipe. Even if you cut the pipe in half, there's no electrostatic field down inside the well, but there'd be electrostatic field on this edge and on this edge, which is what you have here. You have no electrostatic field down inside the trough, in any of these troughs. There'd be no electrostatic field down there, but you'd have super high field right along these edges. Then the way that works is you would have electrostatic field up against this surface here. And if you go to the patent and take a look at it, I don't know how to do this without it looking stupid, but what you have is you have a whole bunch of little thin surfaces. So at the tip of every one of those, these little sharp edges, you have an incredibly high electrostatic pressure, but you have a very, very small area. And then over here on the back side of this surface, you have a very small field, but you have a very large area. And when you do the math, the small field times the large area wins. So what you end up with is a tiny bit of electrostatic pressure pushing this way, very small, and a very large amount of electrostatic pressure pushing this way. So this is trying to go that way, and this is trying to go that way. And because these two things are sandwiched together, the whole structure goes this way. So I was going to put together a little video on how to manufacture one of these bad boys. And I don't know how you're going to test it because you need 40 kV DC positive voltage. But if you did, and you seal it all up, and you put Kapton on the edges so you don't get corona on this ground surface, then you would be rewarded with a little tiny thruster that made about 125 micronewtons of thrust. And if you put that on a great big block of foam and hang it from your ceiling and very carefully put the energy in, you would make yourself a little toy rotating warp drive thruster. That's what I've been up to. I've rebuilt the chamber a couple of times in the last couple of weeks, but that's not important.
And I'm muted. Drew, that is amazing. That was what I was saying. That is amazing. And man, I'm looking forward to coming down there. I'm looking forward to coming down to your lab. I'm so excited to finally meet you and hopefully Charlie in person. And,
yeah,
and again, I want to be able to get like
Tim, when you come down, we play with this one. This is the This is the prototype to the 100 millinewton thruster.
Ah, okay.
So
awesome.
By the time you
awesome.
get here, I'll have built a few of these plates, and the beginning of the 100 millinewton thruster will be sitting on my workbench.
That's so cool. That is so cool. Well, Drew, thank you again, man. Let me see. Let me go to who else had lab updates. I think Jared did.
I got a question for Drew.
Oh yeah, go for it.
Do you have any of those tungsten vapor deposition, one-use things? The heating elements?
I sent you. I responded to
your
your text.
Okay.
Basically, I have dozens
of
heavy-duty tungsten coils, and hundreds of the little aluminum candy canes. And then I don't know. You got a power supply? How many? You got a nice big
500 amps.
500 amp, but like 6 volts, 12 volts, something like that.
Yeah, 6 volts probably.
Yeah.
Okay.
Okay.
Well,
I've got
guys,
a,
let me go
Oh.
to Curtis if it's okay for lab updates.
Yeah.
Okay.
Curtis,
If he's
turn on
here.
your camera.
Curtis, he might have stepped away from his machine.
Yeah.
Okay. Well, you know what? We might have to go to Jared next. Jared was the one who told me. Jared, you're busted. It's your turn.
Yep. So I have a minor update. It's not the best thing, but at least it's something. Back here behind me, you can see my third iteration of the Graviflyer as I continue to try different things to modify one parameter at a time to see if I can make this thing lift off the ground like the inventor did. The special thing about this is that because I have cut the dimensions, the diameters of these discs in half, that means that the magnets on the bottom here are much closer together. And because they're closer together, I can spin these things a lot faster. I can make a lot stronger magnetic fields as well. But it does lower the overall amount of charge that these discs can hold. So unfortunately, that's not something I can really control. It's changing 2 parameters at once instead of just 1. So on this one right now, how I have it set up, I'm trying Alexei's very first thing he did, where he had magnets on the top disk as well. I don't think that's actually what I'm going to end up wanting to do. I suspect that the inventor figured out what works through lots of iterations, and not having magnets on the top does make it easier to lift. The reason why I say that is because I've been doing some tests with the piezoelectric buzzer here up on the top. That piezo buzzer, it is very critical to lift because the inventor, the very last step he does is he has this circuit over here that is controlling the frequency of the ultrasound, and he hits this button. And this button is a normally closed button. So when you push it, it disconnects the circuit, which ends up releasing all of the stored energy in this ferrite core. It releases all that energy in a transient pulse to this piezo buzzer. So the tests that I've been doing on that recently have shown that by just tapping that button like the inventor does, you can pop that piezo buzzer. Let's pick that piezo here for you. You can pop this piezo buzzer into a different resonant state. And when you do that, some of its characteristics change. And I think it's that rapid change in characteristics that might be what are causing the whole thing to enter a lift state. So when I hit that button, what I was observing on my scope over here is that just by changing the frequency, I can get this thing to enter up into that state, right? It'll enter that without hitting the button. But if you get it right on the edge, but not into that higher resonant state, then when you hit the button, it will pop it up into that state, and it's not necessarily stable. It can, if you don't have it tuned just perfectly, it'll pop back down into its original state. But it seems like the characteristics, and this is like just as of this morning, I was testing this, so I take this part with a grain of salt because I haven't fully verified it. But it seems like in these different resonant states, its impedance changes. It seems like, again, I'm not very certain of this yet, but I'll say it anyways. It seems like it's going from a negative inductance to a positive inductance, which means that it's going from absorbing magnetic energy to releasing magnetic energy when you hit that pulse, which, because this thing is so small, if it's releasing a big pulse of magnetic energy that is directed downwards towards this center eddy current, it may be strong enough of a pulse to take the shape of that magnetic field and that eddy current, which is north up here and like south down here, and it hits that and it pops that. This is my current going hypothesis, is that when he's hitting the button, he's causing a change to the magnetic state of what's going on here between the spinning disks with all these multiple fourth order eddy currents going on. So he hits the button, it changes the magnetic state. Now you have an inverted magnetic field, and that's where I'm at now. I'm still testing a lot more, and last thing I'll say is, so I tried putting a stack of piezos up here. So instead of just one of these, I took 5 of them and put them stacked atop each other within small containers for each of them, right? That ends up being a bad thing because you can't get this to enter that higher harmonic state if it is coupled in parallel with other piezos. It has to be just one piezo by itself. You might be able to do it with 2, but I suspect that you need to do it with just 1. And this higher harmonic state, again, just a guess, but our COMSOL guy did some modeling of this, and it suggests that this thing is going from a circular membrane mode that looks like a sombrero, kind of like that one of the last videos that Shiva shared earlier in today's talk, where it shows the water droplet like bouncing and it's doing like this toroid thing, right? So that's the natural resonance mode of a piezo. But when you enter these higher harmonic states, the resonance mode changes and it becomes like a star pattern, like a 6 or 12 pointed star emanating out from the middle. Which again, when you have a shape like that, you're concentrating electric and magnetic charges and whatnot. Yeah, I don't know, but fingers crossed. It's all about the piezo.
Awesome. See, I muted myself this time. I'm good. Jared, thank you, man. And so again, the alt propulsion channel on YouTube. So I went down to Jared's and I'm begging him to come back down later in the year. We did we shot several hours of video. Some of it I still haven't processed, but in terms of the Graviflyer, so he did an amazing walkthrough that's like at least an hour. And then we did testing, and we did 3 separate complete test runs, and he ran through all the parameters for this. That was like 2 hours. And we shot all of that. That was all 4K footage. And the reason I put that up was because people are trying to build these and they want to know more about the Graviflyer. And so the goal was like, here is everything that we're able to kind of get out there, right? And this is Jared's focus. And then Charlie's also working on it. Charlie's the one who started this ball rolling. Then Nathan Bunton is working on it. And Mike Gamble is experimenting with it as well. So you've got, several people that we know of, as well as others out there in the community. But, the hope was just to get the information out there for people to use. So, well, thank you, Jared.
Tim, if I can just put one last little addendum to this piezo thing. So it seems like the reason why this thing is so stinking hard to tune and to get lift is because in order to get this piezo to interact with that magnetic field there, it has to be matched both in distance and in field strength, right? The field strength of the eddy current down here needs to be just slightly weaker, still strong enough to cause lift, but weak enough that this thing can affect it, right? And the adjustments with this potentiometer knob over here, the slightest adjustment, we're talking like a 64th of a turn, you just touch the thing, and it's enough to significantly change the parameters of this piezo, which, again, that supports this idea that this thing is not just turn on everything, turn on the knobs, and why doesn't it lift, right?
Yeah. Well, and I guess Jared, if I could put this out there, I don't know if I'm considered a neutral third party or whatever, right? But like, I'm definitely not into this as deep as you are. But when I came down, you ran me through a list of claims that Alexi has made about, when you change this, you'll see this. And there were probably about 30 or 40 different little bits and pieces, if not more. And as you walked me through that, you would change those. And I saw all of those things happen, which was just absolutely insane, So this, for me, this runs against a lot of people think, is this for real? It's too good to be true, the whole 9 yards. But short of lift, which we didn't really see, everything else that he's predicted, he's like, okay, you change this, you'll see the voltage change here, you'll hear a sound there. And it's like, then you would do it. And it was just amazing. So yeah. So, you're on track of something, dude, Okay. Well, let me bring Curtis in really quick. Curtis, do you have a lab update for us, sir?
Yes, I do.
Okay. Wonderful. Let me take myself out. And then I think after that, we'll just do open discussion for a while.
Okay. There we go. Did that start?
Oh, sorry. It's not. It may have started, but I think you may have to finish sharing. Wait a minute.
Here.
There we go. My fault. I need to put.
All right. Thank you. Okay. So lab update. So this is a recent run from June 2nd. And we are getting still getting good repeatability and doing pretty long sweeps. And you can see here that to describe the traces, the red trace is basically the torsion arm, the fixed torsion arm that moves. That's indicated that kind of red purplish cross on the right. And then the green trace is that green dot that's following the actual device itself. What I call the device is the brass mass and the piezo stack and the aluminum cap. That's all coupled together, riding on bearings on rods. And so you can see that undergoes some big motions. Now, some of these motions are stick slip. You can tell those motions when you have large opposite directions of the green and the red trace. That kind of purplish blue trace, that is a calculated, I would say, rough center of mass type calculation of both of those. So you can see that the device actually moves one direction. It's a torsion arm, so it has a centering kind of forces. But what you'll see here is that, let's say, looking at between 20 seconds, 22 seconds, after that large stick slip event occurs, there's actually quite a bit of a what looks like a movement of both the device and the torsion arm moving together in the same direction. It's possible, you know, that we're getting forces there that are transient. And so again, this is a sweep, and here's another run. This is a little bit nicer. Well, maybe less nice if you're looking at the stick slip part, but you can see the repeatability is there pretty much, where you have places where the reaction mass is moving and the torsion arm is moving in the same direction, and you get that momentum push. So let me share my screen, and I will show you guys, let's see, entire screen, share this screen, and I'll show you guys some videos. Can you guys see that? I'll play it.
Yeah.
So
it's up now in video mode.
Okay, good. So this is the run from June 2nd, the third run, the first slide I showed. So you'll see, I'll run this through, and you can see the device moving. And the thing you want to look for is the torsion arm, which is like the dot on the right. When that moves, that means we're actually pushing and getting some net momentum going on. So this is one of the nicer runs. And then I have another video. This is the second slide I showed. This is the run from the 5th, 7th run that day. And you can see the device pushing again. You know, there's some motion, and you can see some rapid kind of back and forth when the device is kind of just sliding back and forth from all the vibrations that are going on. Remember, this is a piezo stack vibrating pretty violently, and well, with small distances, but it does seem to push. So So again, these are sweeps through a frequency range. And let me go back to the presentation. Stop screen. Let's see, where's that? There we go. So those were the video runs. So the current effort is we're working on sourcing more materials. I won't go into that too much. We're also testing other bearings. We moved to composite bearings, but there's a bunch of different designs and other things that we can look into. So we're doing that, and we're working on basically what you see is a sweep through resonance happening, and us getting a kind of transitory thrust. So right now we're using basically a basic function generator to do that sweep. So we're working on two things. One is improving the real-time data collection. So I've already upgraded the video card, the monitor, but we're still not getting real-time updates from the instrumentation and to match the video. So we need to get that, because that will let us know what frequencies are actually, where the magic is happening, right? So, so the other thing we're working on is driving the signal with some feedback, so that we can reliably repeat, not just a sweep, but reliably repeat the force for a given amount of time. And while it still might be a sweeping type of signal, it should be. We're working on something where it's like a lot closer and it can track for a time that resonance. And so the forces are potentially a lot higher if we do that. So now testing, I mentioned last time, there was a thought of testing a lighter than air vehicle, upper atmosphere testing. But as we discussed, one thing that we might do once we're able to get reliable forces that are repeatable and pretty significant, is to do a floating test bed, right? Like an enclosed pool or something, with something that floats, where the power and everything is on the same test article, and seeing that move. I think that's something that we don't have to do it in space, right? If we're getting enough force, then we can do do that. And while it might not, overcome gravity, if you can move something where there's no other propulsion, then it's pretty obvious you have something, especially if things are in vacuum. So that's kind of like an intermediate goal, I guess you would say, once we get some of these other things sorted out. And as I mentioned last time, we're looking into NSF SBIR proposal. The next thing I just wanted to, there was a lot of presentations today about theory, and as you guys know, I've given presentations about a potential theory and a different path than others are taking with so-called unification, or just like advancing our understanding. I don't necessarily think we can claim theories of everything yet. We still have a lot to learn of what's out there, probably. But there's things that we do know, that things that are experimentally verified, principles that are higher level, that we probably don't want to let go. And that this is like the list I've had the last couple of weeks. I know I wasn't here a couple of weeks ago, but yeah, this hasn't changed. And as you guys, that have been watching my presentations know, that I was one of the reasons I got back interested in Sachs's work and reformulating GR to take into account parity symmetry, was because of the large scale structure kind of, you can call them observations. They're not experiments, but they're observations of a large scale structure, and that there is some kind of a parity violation traces going on. So that really, to me, speaks volumes about, how we should be formulating general relativity, and starting from, if we're making a field theory, you start from the beginning. You don't just take G mu nu and plus something else. That's not really not really adding a symmetry or taking into account the symmetries correctly. The other thing I want to say is in terms of quantum mechanics, I want to again encourage you guys to go look at Carver Mead's talks, especially when he talks about quantum mechanics. He was one of the people that drove through his work, drove the semiconductor industry, and actually proved that getting smaller in device size would give us the benefits that it did. And it's astounding, what he has to say about quantum mechanics. So one of the things we need to be careful of is in physics, the concept of quantum mechanics, treating it as fundamental, or any concept treating it as fundamental. We got to be careful there, because as we know, quantum mechanics strictly, right, the strict version of the Heisenberg type of equation, doesn't work. It fails when you get higher energies. So we know that already. That's common stuff. But the question is, does it now? Is there a higher energy other theory? And that's something that that's why you're building larger colliders, because you're trying to look for higher energy theories that break the standard model and quantum. So standard model is beyond quantum, right? There's symmetries that are broken. There's higher energies, and you have other things that you're taking into account. So keep that in mind when you're looking at these things. So Carver Mead, if you go through his talk, I highly recommend it. You will see that he speaks about matter as waves, basically, in that kind of in vein. So this was an experiment that I'm showing right here that they did in the 70s. Is a single neutron or single crystal neutron interferometer experiment. And what they were able to do is show that depending on as the Earth, the Earth rotates every day, and depending on the angle, you would actually see a different phase shift due to the Earth rotation, which is an indication that the neutrons know where they are in the universe, right? The Mach effect is basically kind of proven here as from this experiment. So there's certain, when I say the Mach effect, I mean to say the Mach principle, right? That matter out there or something is giving local inertia its properties. So that's something that I want to emphasize. And again, like field theory is something that was made popular. That's what I think we probably still want to pursue, is the field theory. And I'm more inclined, as a lot of what Shiva was saying, I'm kind of with that, because I'm inclined to not treat gravity as just some kind of geometry or mathematical thing. It's a physical concept, and to me, the physical concepts have to motivate the mathematics that you're going to put in, right? So the symmetries need to motivate the algebra that you use, for example. So anyway, and then the other thing is, I think I talked about this last time. There's a few other points of view out there, and there's others if you explore. But one is that I found recently was a quasi-cycle, which is a whole theory that's based on particles being made out of light that is not just, we talk about waves that are longitudinal or or can go either straight or have that kind of compression type wave. Well, this is something where they're saying that you have a momentum where the electron, they postulate that it's actual light kind of spinning on itself. So it's a very interesting theory. I don't necessarily know that I 100% agree with it, but it is thinking outside the box. So, and then the other one that as I mentioned before about quantum mechanics being a low energy approximation. So this is I put onquantum.net here, but there's another website, but everything's on his website. This is an experiment that he shows that that you don't get the quantum effects at higher energies with these gamma rays when he does this interferometry type experiment. So it's very interesting. I think it needs to be replicated. I mean, if someone's interested in doing replication, it doesn't look like it's that difficult. You know, I'd be happy to be involved with that as well. I've used scintillation detectors before, so it's been a long time, but you know, I'm familiar with them. And so I think that's something that we probably should get out there and publish. And the other thing I want to mention, the last thing is that, and I mentioned this before, is that there is an experiment to probe the quantum vacuum, which is a large gamma ray experiment, and it was made popular by a YouTuber. So I'll put that link with the chat. So that's all I have today.
Awesome. Okay, well, there we go, Curtis. So let's go to open discussion. And you know what?
I got a question for Curtis.
Okay.
Are you guys going to send me a copy of that thruster? We want to do the high-speed camera experiment.
I think that's everybody who's here. We got Russell, but I don't think he's here. So but you know what? You guys should give yourselves an applause. I will applaud for you. I'm going to applaud for all of our lab people and builders, especially. I mean, again, this summer you guys have been just surging forward. So thank you.
Mark, we have that's why I mentioned the sourcing issue. We have to source some materials.
I'll be right back, guys.
To get out some samples.
So yeah, it's open discussion. I would say just shoot, go for it.
So Curtis, you don't have one on hand?
On my hat?
You're going to ship.
My coat. There we go. Look at that.
We're working on that because there are currently some stacks made, but it takes Jim time to go through and validate them and for us to test that it's working. So we're going at Jim's pace. That's, you know.
I mean, listen, I'm flexible. If you guys want to bring one in, you know, a setup, I can run it and send it back to you guys, or somebody wants to fly down here. You know, I'm flexible. I'll work around your schedule. We have the vacuum stuff set up already, so
yeah.
Do it.
Yeah, there's only a kind of a hand, like not even a handful, like a couple that we've been working with, a couple of stacks, and I've been trying to push to get more. So we've ordered some more materials, but like I said, there's a sourcing issue with getting more materials to make the stacks. And I don't want to, in a public forum, I don't want to go into too much detail.
No problem. Yes, let's keep the proprietary stuff offline. So me and Shiva are actually having a conversation on the side. Shiva, why do you want to go to terahertz? Why can't we just do it in gigahertz or megahertz? What's so special about it?
Well, okay, so the terahertz range, you can
let's back up a second. We're talking about the bismuth, zinc, and what's the last
iridium
part?
oxide.
Oh yeah, and the iridium oxide you want to throw in there too, which is extremely hard to work with. But why not just make it a little thicker and go to lower frequency?
Well, yeah, you could possibly go to lower frequencies, but to just work with harmonics, that does make sense to make it more engineerable. But yeah, basically, what you look at research around terahertz waves and especially biological activity. There is. Are you familiar with Froelich coherence? It is a.
When you say terahertz, what do you mean? Are you talking about 1 terahertz, 5 terahertz, 150?
Terahertz range. It has yeah. It would have to be. It's a large range. I realize.
It's a large range. You have to be a little bit more specific.
Well, that's where experimentation comes in.
No. You got to theory that out, because some part of the terahertz range you can buy equipment that does it right now. Your eyesight is in terahertz range, so yeah. When you light, infrared those are all terahertz.
Yeah. Well, yeah. Well, you don't really see it there, but yeah. So the some part of the terahertz range, because of its biological activity, it's been found. First of all, it's found in the brain. It's found in instantiating coherent states in biological molecules, which instantiating coherence in complex shapes like biological molecules is an interesting effect that probably has to do with, like I said, perhaps has to do with atomic binding radius. I don't know exactly what it
The,
is.
the atomic binding radius and the thickness of those layers are several magnitude, orders of magnitude apart.
Right. Okay. So there's a thing with it's going to get back to fivefold symmetry and the relationship between what's it called, the golden ratio and the Fibonacci sequence. So the golden ratio is basically, if you work it backwards, you could believe that the golden ratio may actually end at where the Fibonacci sequence starts. And so there's a point at which it gets down to the 1 1, part of the beginning of the Fibonacci sequence. Kitty, not right now.
Oh, they always come in when you're on camera.
He decided he is coming in. But so the thing is with the terahertz range, why the terahertz range is it's one of those things where finding that it behaves in a variety of ways. Like right off the bat, when the only way in which the new upgrades to the various modems and all that, like worry about 5G and all that, the only reason that was actually in any way dangerous is because it's been found that some frequencies of terahertz actually can disrupt vitamin D production in the skin. There's a host of studies I could send you on the ways in which specifically the terahertz range impacts a variety of molecules in a way in which, when you're talking about something that's a complex shape and it's not a simple crystalline structure, the ability to cause it to resonate and produce coherent effects is by itself extremely interesting. So yeah, it's a huge range. I understand that, and attempting to find where within that range you might find something useful. I'm not saying I know exactly what's going on here, but one of the things that what I'm talking about here with the original thing that I forget who it was who brought up these layers of bismuth, zinc, and iridium, and I'm specifically adding iridium oxide because that's going to play the role of the that would normally be played in a voltaic pile by the electrolyte, and so the point here is that perhaps the anomalous Hall effect may lead to a feedback loop, and in which where it's a self-strengthening current produced, and so like I said, I'm just this is spitballing experimentation.
Yeah. I mean, what are you going to use as your binder? Iridium oxide, it's a powder.
The engineering part of it, I realize it's probably very difficult to do the engineering, and probably the first thing to do would be see what kind of effect you can have at much lower frequencies, and therefore much thicker. When you're starting the engineering, what you want to do is find something that is going to be one of the harmonics of an interesting frequency, and then make sure that you are tuning it to the speed of light in the material itself, which is going to that's also going to be very important to be able to set up anything that is a standing wave in it. And each one of the materials is going to have a different speed. So you have to tune all of them to be able to have any hope of maybe causing some sort of feedback loop like I'm talking about. So.
You got to deal with what's available on eBay and Amazon in order to have any chance of actually building anything. And the only thing that's available there in the terahertz range is anything that's in the infrared or light range of
so in your experimentation, just keep in mind that your target eventually would be something that is in the terahertz range, and so simply look at what if you're using some harmonic of it, then just be aware that your eventual so you may get a change if you see any effect at with one build of it, you may see a significantly larger effect in a build that more closely matches the material found on these UAPs, and I think I have good reasoning for why it is that it is having any effect at all. What is the usefulness? I mean, it also may require some.
Get into the theory. Why would that make any difference? Why would that do anything?
Why would it do something? Is because you're creating a voltaic pile. So in other words, it's you're.
Why doesn't a voltaic pile fly?
Say again.
Why doesn't a voltaic pile fly? For creating a voltaic pile, we already have them.
Okay, because it first of all, it doesn't have a self-sustaining feedback loop. Secondly, it doesn't have the anomalous Hall effect.
So what if we attached a self-sustaining feedback loop to a voltaic pile? I think you're talking about LC circuit.
No, not exactly. The feedback effect that I'm talking about is with the anomalous Hall effect and the production of ions in the way in which they're interacting. Like I said, this is one of those things where I'm guessing at something that is a material that is supposedly useful. I don't understand why you're still against this. Can you tell me
I'm
why?
not against it. I'm just trying to understand it. Maybe David can translate.
Okay, because I've given you a number of things that are valuable, effects that may be, at play in such a material, and it might actually require much more detailed, where you're actually turning it into a metamaterial at a certain layer to be able to get the effects that you want. But what I'm talking about is a first, step at a reasoning behind why it is that you would layer any given set of materials, and that is because of the similarity to a voltaic pile, and specifically because the bismuth has the anomalous Hall effect. And what would the combination of why would you build it that way? So ask yourself, what would be their theory if it is in fact material from a spacecraft? Their theory would be the fact that you can create a voltaic pile-like effect and exploit the anomalous Hall effect from the bismuth. That's the only thing I can see why it would be engineered in that fashion. So that's where you start. And
Well, what if they're trying to overcome the skin depth problem with an Overhauser DMP setup? So you have sympathetically layered materials with dielectric in between them. You excite one at gigahertz, and then it'll excite the layers below it as well, and you'll be able to build up some sort of DMP.
Mark, I think the question would be, because there are a couple different potential reasons, right? So then the question becomes, how is the best way to replicate this with maybe a substantial, like, I don't know how big you'd want this to be, right? But those little tiny fragments might not do what you want. Like, one of the things you proposed was maybe the issue, especially with skin depth, is that it needs to go in between the layers and not through them, right? So
I mean, that's kind of what Shiva is trying to say, that you have longitudinal waves coming through the material, and that each layer is at a different peak and node. That would indicate, probably terahertz, depending on the thickness of the material.
Yeah. So then the question becomes, how do you build the material?
You have horizontal waves along the surface, that they would be sympathetically excited one to another, and you'd have a homogeneous magnetic field going through that sample, so that all of them are at the same gyromagnetic ratio, and then you'd be able to have one layer of excitation, a DMP excitation, enhancing the effect, and then that will surround the entire craft and get it all in a nuclear polarized state.
Okay, so then the question
different
would
ways
be,
of looking at the same, why it's doing that.
so then the question would be, how do you create that material to test it? Because you're just,
I
I think
already
you're
made
reaching,
it. I have it right over here inside this room. That's not the problem. The question is, what do you do with it?
well, and I'm like, how close is this to your suspected samples, right? Like the arts parts and the other. I mean, I don't. I think
We're
you're getting
talking
to the
about
point.
parts, pretty much. That's what it is.
Yeah. So,
Shiva wants to throw in
And
a
I was told it
diagram.
was specifically iridium, and then I had to extrapolate that it must not be just iridium, but iridium oxide. So it's and you're probably saying that's very difficult to work with. Makes sense, it would be, but maybe that's part of the the secret sauce that we're not getting, and it would be something to experiment with in some way, and who knows what might come to that. But
yeah,
that is
it
not,
seems. It seems to me like you're reaching the point where the rubber just has to meet the experimental road.
Mhm.
Yeah,
So,
yeah.
exactly.
Because I think Jared posted in here that the arts parts experiment material was tested at 1 to 4 terahertz. Is that true?
see, but this is why building stuff is so ultimately important, because I've seen this a number of times. Like, there are 4 or 5 different models that kind of support things, and then you don't know. It's like, why is it supposed to work? Could it be X, Y, Z, or something else? So it's a challenge, right? But the arts parts things is interesting, though. You make national headlines if you can figure that one out, like global headlines.
Yeah, supposedly they tested it down in that, super low, super infrared range. And that's where they said they noticed that it did the wiggle.
And just getting back to I was talking about these vastly different sized ranges. There's when you look at the way in which the golden mean works, there's a way in which it can you could set up a type of wave that which reverse scales. So in other words, there's the possibility that using the golden ratio will allow you to set up a variety of frequencies that will traverse scale. Do you understand what I mean by that? In other words, it will make smaller and smaller and smaller and smaller frequencies and larger and larger and larger.
So you're talking about like higher and lower harmonics coming out of, yeah, okay.
Right. It's like, for instance, one of the things that I'm surprised that people don't recognize is that that in a right triangle, there is the golden mean is in just a typical 2-to-1 right triangle. You can actually find that the path around the short leg and the hypotenuse compared to the path just down the long leg. There is if you set up a frequency that is according to the golden mean, you'll actually create these sets of nodes along it because there is a golden mean relationship between them. It's just something you can explore on your own. It's one of the reasons why for instance they've taken the shape of the pyramids and been able to create a lens type of effect with it, where it can it can project certain frequencies of it will actually accept certain frequencies and then concentrate them or collimate them. I'm not exactly sure, but it's been a while since I've looked into that. But there's basically an effect of resonance that can traverse scale related to the golden mean. That's why the golden mean is important. It has to do with multidimensional. So it's about traversing both scale and dimension. So, but like I said, I'm not prepared to talk extensively about that right now because I'd have to point out a lot more about it.
You can actually find the golden ratio by taking an equilateral triangle and putting a circle around it. There's a way to get it there too, which is pretty nifty. I actually looked at making music scales by using the golden ratio. And so basically the golden ratio is the most irrational number. So if you combine multiple frequencies that are in golden ratio to them, they'll have the most chaotic overtone structure possible. So like the harmonics are always based on very rational numbers.
Right. So you get down to smaller. In other words, your wave packets or your interference patterns, as you would go to smaller and smaller and smaller and smaller interference patterns is the best way I can put it. That was
yeah. If you listen to it, like you feel like the wobbling of the overtones, like it's kind of wild. Yeah. I don't know if that has applications for electronics, but if you wanted like a very chaotic overtone spectrum, you could use golden ratio frequencies.
By the way, David, I had a question for you. You mentioned virtual particles in general relativity.
Yeah.
Could you elaborate on that? I thought that was interesting.
Yeah, so if you study the post-Minkowskian and expansion of general relativity, you can use Feynman diagrams to discuss those processes. So you can actually calculate gravitational waves in the classical theory with Feynman diagrams, and you end up getting loop diagrams. And so the Feynman diagrams with the loops in it typically count the number of orders in perturbation theory going out. And so in QED, it's with quantum corrections. But now you're just doing perturbation theory in a classical theory. And so you can still get loop diagrams in classical general relativity, and you can still have virtual particles in the classical theory.
Okay. Does that worked out in Feynman's gravity book?
I don't know. I worked it out in my thesis just because it ended up being important for what my advisor wanted to do with gravitational waves.
Okay.
So there's this guy, Walter Goldberger, who is an expert on that. I mean, because Feynman was more interested in looking at quantum gravity. So he was trying to start with linearized gravity and go into the quantum theory. I mean, obviously Feynman did a bunch of stuff. I haven't read everything, but I know that he was trying to approach quantum gravity from the perturbative route in that way.
Yeah.
So it depends if you look at it as the gravitational constant as being small versus h bar. You could perturb with either one.
Yeah. Because when you mentioned that, it reminded me of the background pairs that Sachs ended up deriving.
Well, yeah, except since gravity is nonlinear, it can interact with itself. So you could just have a loop of gravitons, if you will.
Yeah.
And you don't even need electron-positrons pairs. Those are used to interact with the photon. So you have a trivalent vertex where you have an electron, positron, and a photon. But here you can just have a graviton, graviton, graviton. Or, I mean, it also interacts with matter and light as well. You can have a graviton get emitted off of a photon as well. So, or off of an electron. So different interaction vertices.
Okay. Can I pitch something very quickly? Well, Tim is not there, so I'll just go ahead. I'm not sure if you remember my quick presentation I did 2 weeks ago about the atomic forces and things like that. Actually, I expanded on that, and it's very interesting. It's really cool. 1 second. Share screen. Player screen. So, can you see the screen?
Yeah, I got it, Phil.
Okay. So I had a curve that looked like that, and the slope that looked like that. Actually, it turns out these are exactly the atomic forces. You have gravity, electric, magnetic forces, and then you have the weak nuclear force and the strong nuclear force, where the x-axis is the distance from the center of the atom, and the y-axis is the forces in Newton. So this is not exactly correct graph, because gravity should be on the same side as a weak nuclear force, but it gives you an idea that the weak nuclear force is the opposite of the strong nuclear force, and so on. And so yeah, that's the Wikipedia graph here, and that's what it represents. You have all these forces at the atomic scale, and actually I did some retrofitting of these graphs, because I wanted to figure out the strength of the forces, to see if they were making sense. So what I did is I did retrofit the gravitomagnetic force, the gravitoelectric force, the magnetic and the electric forces, to see what charge or mass or magnetic moment or gravitomagnetic moment I would need to represent the same scale of the forces. So I need something that goes around, I don't know, 10,000 Newton, and it needs to be within the range of 1 times 10 to the minus 15 meters, which is a femtometer, something like that. So I need something like that. I need to have a graph that are within this range. So just while you guys were talking today, I just retrofitted these values. Well, the first column here, the first column is kind of the ambient force, and the second column is the mass or the charge or the magnetic or the gravitomagnetic moment of the particle. So I got these numbers actually while you were talking today, and to see if what strength of gravitomagnetic force I would need to get that graph. And I kind of have unrealistic numbers for the gravitomagnetic force, which is way too strong, like 8 kilograms per second, 8 kilograms meters per second, which is quite strong for some sort of particle. So I kind of reject that gravitomagnetic force has an impact at the atomic level. The magnetic force is very close, because the magnetic moment of a particle is 1 times 10 to the minus 26 coulombs meter per second. and I get 7 times 10 to the minus 10 coulombs meters per second. So it's very close, but there's still a big gap in the order of magnitude. And the the gravitational force, actually, I would need the mass of the particle to be 2 times 10 to the minus 8 kilogram. That's actually a kilogram here. So, which is way too big, because the mass of a proton is 10 to the minus 27 kilogram. But if I use the electric force, then I get exactly the strength of a charge, which
Be
is
down a little bit.
I get exactly the strength of a charge, which is 10 times 10 to the minus 19 coulomb. I get to the minus 18 coulomb. So this is the graph here. I'm able to explain the atomic forces just with the electric field. It's pretty cool, and I get the exact ambient coulombs per meter as well. So yeah, I mean, just with the electric force, I'm able to explain all the atomic forces. So I think that's pretty awesome. There's no need for all these extra equations, and so yeah, that's what I want to share. And thanks for your time. Oh, hey,
Okay.
Jake.
Well, we got about 20 minutes left. So, and let me see, we're limited to about 10 people. So I'm going to have to remove a couple. Did somebody give out the link? Well, I'm not going to get into that now, but, so what do you guys have? We got about 20 minutes left for open discussion. James, welcome. Did you have anything?
I did actually have one question.
Okay.
On a slightly different topic. I was curious if anybody's ever been able to get in touch with Brad Sorensen from the Mark McCandless story.
No, I think he's still around, but
okay. Just figured I'd throw that out there. I spoke with him today, and he was definitely not happy to hear from me. So I was just curious if anybody's ever been able to get in touch with him. But
why was Brad not happy?
Oh, I just asked him if he was aware of the Mark McCandless story and if he was interested in speaking to me about it. And he basically said, absolutely not. Can't confirm, nor can I deny if I'm aware of Mark McCandless. So I just wanted to see, this is a group that might have had the opportunity to speak with him at some point in the past. So I was just curious about that.
Yeah, I've talked to Brad a few times. It probably was what you asked him. So I don't know.
Yeah, well, it's fair.
So, okay, well.
Hey, Jared. Jared, you there?
Yeah.
Yeah, I'm sorry. You were talking about switching your piezoelectric circuit on and off, and you're touching a switch and something, and you're seeing a dump of energy. Are you aware that there are actually cost-effective, high voltage, almost instantaneous switches? They're made by a company called Belke, Behlke. Couple $100, you can buy a switch that operates in the 100 nanosecond range and can go up to 40 kV.
That is awesome. Oh,
Yeah,
I am buying me one of those right now.
They've got ultra high DIDT. For a little while, years ago, we were playing around with the whole. It doesn't matter. We're messing around with them. I got a couple of them, but it's Behlke, and for $500-600, you can buy a switch that will give you 50 nanoseconds and be able to handle 10 kV. I don't know exactly what those little piezos.
They're low voltage. It's like 9 volts, but it's when you have these really strong electric fields around it, it needs a little bit of protections. But I'm gonna see if I can make that switch thing happen. That is very helpful. Thank you.
You're welcome.
I was wanting to make one comment and then ask David something. I was just going to say I didn't get to completely finish. We did talk about some of this the other day when we were talking about the ether version of gravity, and the only thing I forgot to mention was how it is relevant to space-time engineering and the things we're trying to accomplish here. It was just wanted to make a note that basically if it's the bulk vorticity represented by the vortex filaments in a local area that is playing the role of gravity by changing the rigidity of the ether, then by manipulating the filaments themselves, you're actually manipulating the centers of rotation and therefore the rotation. And so therefore, if you were able to somehow make it, instead of there being a gradient, which is responsible for the gravity, you could instead cause the vorticity to be equal all throughout wherever your craft is or your bubble or whatever it is that you're doing. That would be a method by which we would be attempting to achieve a level of anti-gravity. So the question I was going to ask you, David, if I can remember exactly what it was, you were talking about some interesting ideas with. Oh yes, are you familiar with the idea that in fluid dynamics, when you have a border? So, for instance, in the model that I'm talking about, you're gonna have like laminar flow layers. You're gonna have a lot of these different border lines that are going to play the role of creating a two-dimensional border. And what that does is it opens up an additional degree of freedom whenever you're talking about fluids. And so what I'm saying here is that this is the way in which there is a entropic gravity component to this perspective, because as you have more of these filaments and you have more of these effects which are opening up spaces, which I was talking about in the chat, that you talked about these little square puzzles that have to have one piece that's open so you can move them around. That would be perhaps at the Planck scale that you would have to have these spaces open, and that might also be part of the electron, the instantiation of electron. Then the point here is that if you have a medium that is very mechanical-like, in other words, it's like locked gears, then the only way in which they can go against each other is by having these openings, and that is the reason why you have the electron flow and things like that, because of these interactions between layers, boundary layers, etc. But the most important part here is those additional boundary layers give you this extra degree of freedom, which then, of course, is a place where entropy would tend towards, and so that is an expression of entropic gravity. And then the final thing I was going to say is, I was hoping you could kind of consider these things and what you're working on. The final thing I was going to say is that looking at, I'll send you a paper on micropolar electromagnetism, where it seems as though the scalar waves would be many orders of magnitude faster than typical transverse waves. But I suspect that this same mechanism, whereby say if you think of some viscoelastic substance, like a big blob of kind of jelly sitting on a counter, when you try to move it, if it's fairly stiff, what's going to happen is you're going to have these little wave-like portions of areas opening up to allow it to go across the surface, to mediate that overcoming the friction. It's going to have those areas where it's basically kind of doing sort of a snaking motion. And so this would be one of the ways in which I would be expressing how, the reason for electron flow. But so just looking at this from the perspective of it having this additional degree of freedom, what was the other aspect of it I was going to cover? Oh, yes, longitudinal. So the longitudinal waves may have an additional mode of transmission if there's indeed a structure to space-time that is made up of these vortex filaments, then it may be requiring and utilizing the two-dimensional aspect of these vortex filaments. And this is where the idea of ER equals EPR plays a role in the fluid dynamic version of space-time. Is that these vortex filaments are actually like small-scale versions of wormholes. So that's just kind of a way to, that helps you some in your work, and that might be a useful analogy. So.
Yeah, thanks for sharing. So yeah, there's a few comments. I mean, there's something about the Whittaker potentials with that that three-dimensional rotational symmetry that's a type of gauge symmetry. So, and then the Maxwell ether model was based on a hexagonal lattice. So I'm curious if somehow choosing that vector relates to the choice about kind of the direction of that two-dimensional plane in relation to how it's oriented in 3 dimensions. And so right now we're kind of saying that, oh, that orientation doesn't matter at all. But one of the ideas would be like, what if that actually is important for something really subtle? Then maybe that could be something that's explored. Yeah, I'd have to, maybe you can send some more references and revolve to what you were talking about, that extra degree of freedom. I don't know exactly what you're referring to there. Maybe probably haven't seen that. And also, yeah, oftentimes in general, longitudinal modes can travel faster than the transverse modes. So Cohn van Vlanderen does have a paper that he put out a few years ago that talks about 2 different types of longitudinal modes. One is the one that I presented on that is at the speed of light, but then he also presents on this other mode that goes faster than the speed of light. So I do plan on studying that in more detail. And so that might end up correlating to some of what you're saying.
Yeah,
Sure.
Yeah, exactly. It seems like there's a strong analogy here when it comes to the, like, for instance, I showed the plasma vortex crystals. They automatically emerge whenever you stir a non-neutral plasma, and the 2-dimensional vortices will automatically arrange themselves into crystalline structures. And that only happens because of the borders that make them 2D vortices instead of 3D. And so it is because of that additional degree of freedom that a new behavior evolves in plasmas. So that's just what if you just start looking into fluid dynamics, you'll find that the 2-dimensional borders actually give this additional degree of freedom, which is what I'm saying. That's the entropic effect of gravity in fluid dynamics.
Yeah, Whittaker also considered these things that he called calamoid, which were, I guess, the relativistic completion of Faraday's flux tubes, but he never connected those to his other Whittaker potentials. So, and I think that really is the origin of strings and string theory without them realizing it. So there's this electromagnetic, and this idea, I mean, they talked about cosmic strings in the 1980s. They like, what if there were like these filaments going through space-time and there's some like vortex math associated with all that. And so I think if you study these Hertz and Whittaker potentials, you'll actually find that if you take them seriously, then it probably will relate to some of those ether models and surprisingly kind of be similar to string theory in certain ways, but they often overcomplicate everything. So
yeah.
Exactly. Tim, I got to cruise, but I got 50 seconds of something fun. If
yeah, fun.
It's fun. Actually, it's fun.
Put it up, man. Put it up.
All right, hang on. Every screen's different.
Should we highlight you?
Yeah.
There you go.
Okay, I presume the audio is going to work. I don't really know. But here in sunny Florida, we have this really annoying thing, SpaceX. They keep throwing rockets in the sky.
I don't think the audio is working.
Can you hear anything?
No, we can't. You can just comment. You can just talk.
Okay. All right. Well, basically, SpaceX just launched about 10 minutes before this. And it shakes the whole building. I mean, literally, my entire hangar shakes like an earthquake. And it because the building's tied directly to the super slab, everything moves in the hangar, including the foundation, which moves my chamber, which shows up as false data. So every time one of them damn rockets goes off, I end up with false data in my test. I want Musk to stop this. This must stop. I have warp drive testing going on, and he's throwing these silly ass rockets in the sky. I'm done with it. Thought I'd let the world know.
He must stop.
Yeah. Yes, he must. Okay, that's it. Really annoying.
Jared's laughing.
I'm dying over here, man.
We get it like twice a week, 3 times a week. You know, minimum twice. And I think there's another one going off tomorrow or something stupid. It's
Time to
really
move,
annoying.
man. Time to move. That or you have
And
to
it's
test
like-
in the bunker.
It's like he doesn't want us to get off the planet. He's blocking us with all the Starlink, and he's blocking progress by shaking your instruments.
The weird thing is when he's chasing going north, it because the Space Center is about 33 miles south of me, so it actually arcs up over the trees, and I can watch the rocket go all the way to the horizon, right from my backyard. It's really nice when they're shooting north, like when the space shuttle was chasing that Russian crap orbit. You know, we had to go chase the ISS down. It's really it's a nice place to be, 30 miles north of the Space Center.
It's funny.
If you like watching rockets.
One of the common like dystopian future ideas is that anything happens with a bunch of satellites, and what you end up with is tiny little bullets just littering the entire area around any kind of space, so that you can't go into space anymore. And so like there's these Chinese satellites that are going and like attacking other satellites, and just one cascading event, we can't even go into space with normal technology anymore.
Actually, if I remember correctly, there was an issue with Russia. I'm kind of blurry on the details, but Russia, they blew up one of their own satellites, and they claimed it was, for innocuous reasons, but if I remember right, it created a debris cloud, and everybody was upset about it.
Called Kessler syndrome is the scientific name for that. I had a recommendation, actually, a way to remove that is to send a rocket or one of Elon Musk's rockets up in retrograde or opposite of Earth's spin, and just send the plume into orbit. So if you just send the rocket fuel, going the other way into orbit, what you'll do is create a nebula that's going the other way around the Earth, and it will slow everything down that's in that orbit and basically deorbit everything. The regulations to set something like that up will probably be pretty bad, and lots of people.
They've had some extreme ideas. I mean, I remember one person was talking about some kind of a big net, like space net, like a fishing net, right?
I mean, in terms of actually getting something done, this is very simple. Well, you send a rocket.
It'd probably work better too.
Yeah, and then the plume would deorbit
that's
the rocket.
Not a bad idea.
Yeah, the plume would deorbit the rocket too. So
well, the plume would be much better than a big net, because
it would basically be a nebula that's going around the Earth in the opposite direction.
What you'd want to do is you'd want to gently decelerate. You'd want to increase the drag on the satellites, and then they'd come down.
Right.
That's actually not a bad idea.
They do, there's currently, I mean, the DoD considers this, but they said there's currently what they call a gray war in space. So they mess with each other's satellites, and it's interesting. Like when you dig into it, because I've done a couple podcasts on that. When you dig into it, they seriously do, and it's like they don't have great visibility on these, right? It's mostly just radar, and so you can get away with a whole lot. And according to DoD, like several of these adversarial nations they're messing with each other's satellites in orbit. So
yeah, imagine if you had a satellite that you could just maneuver without regret because you never ran out of fuel. You could go up there and you could help people that you wanted to help, and you could hold other satellites hostage, and you could just flat out be mischievous, and
and they are the example that the guy gave me was, if you spray paint black one of the solar panels, it will cause it to absorb more light. His theory was it would cause the satellite to eventually spin out of control.
It's very true.
I'm like, so you're up, but then I took 2 steps back from that, and I'm like, so you're basically talking about tagging satellites in orbit. I was like, it doesn't get more juvenile than that,
But what about the blue? If you color it blue, then lasers don't affect it.
Look
Well,
at that,
whatever
Mr.
happened to
Mr.
that one?
Graffiti Art. Mr. Graffiti Art's thinking. He's like,
That test needs to be applied.
So there's Bernie in space with a rattle can. That's how it
Hey,
started.
and in Canada with lots of forest fires. So if I can paint my house blue and somehow magically it doesn't burn down, I'm all for it. And speaking of which, the Stanley Cup Finals are about to start, so go Oilers, because I'm in Alberta, and yeah, gotta tune into that.
There you go.
Yeah, the good old. It reminds me of the days of Wayne Gretzky in Edmonton. You know.
FCA and
Yeah. Well, guys, we got about 2 minutes left. Why don't I shut things down now? I'll end the live stream. I think we've just about done everything that we can for today. So this has been APEC for June 8th, 2024. And I want to thank everybody for watching. And again, it is amazing. There is so much going on. It is
How about a round of applause for Tim for putting this together? How about that?
Oh,
I think,
thank you, guys. Okay.